Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Faidullah and you are watching Easy Mathematics. In this video, we shall study a full course of linear algebra and ODEs with code Math 121. These are the contents of this course. Let's start from the first one. We shall present a quick introduction to matrices. In this video, we shall study these topics which you can see on the screen. Let us start from the first topic. Matrix, a rectangular arrangement of numbers enclosed by square brackets, is called a matrix. Matrices are denoted by capital letters, just like capital A, B, or C, etc. Generally, a matrix can be written as A is equal to a 1, 1, a 1, 2, up to a 1n. Similarly, a 2, 1, a 2, 2, up to a 2n, and up to so on, then a m1, a m2, up to a mn. And now if I enclose it by square brackets, then this arrangement is called a matrix. The horizontal arrangement are called rows of the matrix. For example, this one is first row. Let us say this is row 1. This one is second row, row 2. And this one is up to m row. So we can say this is row m. The vertical arrangement is called its columns. So for example, this one is column 1. We can say this is C1, all elements on this column. This is called column 2, C2, and so on. Now, the elements A1, 1, A1, 2, A1, 1, A2, 2, A3, 3, up to so on. These elements is called principal diagonal. This is called, we can say this is principal diagonal. Now, what we mean by order of a matrix? So, if there are R rows and C columns in a matrix, then R cross C is called order of that matrix. Let us say we have a matrix A, just like we can see above. So what will be order of this matrix A? Its order is rows into columns. So we can see there are m rows and there are n columns. So order of this matrix is m cross n. Let us say there is a matrix B, 1, 2, 7, 3. Now we can see the order of this matrix is rows into columns, and we can see there are 2 rows and 2 columns. So order of this matrix B is 2 cross 2. Let us write another matrix D, which is given by 1, 2, 3, 4, 7, 3. Now let us find order of matrix D. So there you can see there are 2 rows and 3 columns. So order of this matrix is 2 cross 3. Row vector. That matrix which has only one row is called a row vector. For example, let us write a matrix E. Now, matrix E is 1, 2, 7. We can see there is only one row in this matrix. That is why this matrix is called row vector. Row column, a matrix with only one column is called a column vector. For example, let us write a matrix F. And in this matrix, we have A, B, C. So there is only one column in this matrix. That is why this is called a row column. Equal matrices. Two matrices are said to be equal if they satisfy two properties. The first property is they have the same order. The second one, their corresponding entries are same. Let us write an example in which we have a matrix A. In matrix A, there are 1, 2, 2, 1. Let us write another matrix B. In matrix B, we have 1, 2, 1, 2, 1, 0. Let us write another matrix C in which we have 1, 2, 2, 1. Now you can see A is not equal to B because they don't have the same order. But you can see A is equal to C because they have the same order and their corresponding entries are same. First entry of A and first entry of C, they are same, 1, 1. Similarly, second entry of A, second entry of C, they are equal, 2, 2, and so on. Zero matrix. A matrix whose all elements are 0 is called a zero matrix. For example, we denote a zero matrix by O. So if I write a matrix with 2 rows and 2 columns, 0, 0, 0, 0. This is a 2 cross 2 matrix and all entries are 0. So this is called a zero matrix. Square matrix. A matrix having the same number of rows and columns is called a square matrix. Otherwise, it is called a rectangular matrix. For example, let us write a matrix A. And in this matrix, I have 1, 2, 3, 4. There are 2 rows and 2 columns. So number of rows and number of columns are same. That is why this is a square matrix. But if I write another matrix B, in which I have 1, 2, 7, 7, 8, 9, there are 2 rows and 3 columns. So number of rows and columns are not equal. So that is why this is not a square matrix. This is a rectangular matrix. Diagonal matrix. A matrix whose all entries are zeros except on the principal diagonal is called a diagonal matrix. Let us see an example. In this example, we write a matrix A which is equal to 2, 0, 0, 3. And we can see that this one is the principal diagonal. So all entries of this matrix are zeros except the entries on the principal diagonal. So that is why A is a diagonal matrix. Let us write another matrix B. This matrix is 3, 0, 0, 0, 4, 0, 0, 0, 3. Now again we can see that all entries of this matrix are zeros except the entries on the principal diagonal. So this is called a diagonal matrix. Identity matrix. That diagonal matrix whose all entries on the principal diagonal are 1 is called an identity matrix. Identity matrix is denoted by I. I2 mean 2 cross 2 matrix. So let us see an example of the identity matrix, which is 1 0 0 1. So we can see entries on the principal diagonal are 1. So this is an identity matrix. Let us write another matrix I3, which is equal to 1 0 0 0 1 0 0 0 1. Again, entries on the principal diagonal are 1 and the remaining are zeros. So this is an identity matrix. Upper triangular matrix, a matrix whose all entries below the principal diagonal are zeros, is called an upper triangular matrix. So let us see an example. Let us A is a matrix. In this matrix we have 1 2 3 0 1 4 0 0 2. And now we can see that all entries below the principal diagonal are zeros in this matrix. So this is called an upper triangular matrix. Lower triangular matrix, a matrix whose all entries above the principal diagonal are zeros, is called a lower triangular matrix. So let us see an example B. We have a matrix B, and in this matrix we have 3 0 0. Then we have 1 2 0. Now we have 4 3 1. Now we can see that all entries above the principal diagonal are zeros. So this is called a lower triangular matrix. Transpose of a matrix. So if we interchange rows into columns or columns into rows, we get transpose of a matrix. Transpose of a matrix A is denoted by AT. So let us see an example. In this example, we have a matrix. The matrix is 3 2 1 7. How to obtain its transpose? To obtain its transpose, let us write its first row in first column, 3 2. Its second row in second column, 1 7. So this is transpose of matrix A. Let us write another matrix. In this matrix I have 1 2 4 3 2 1 7 4 2. Now what is transpose of matrix B? Let us write it first row in first column, 1 2 4. Second row and second column, 3 2 1. Third row in third column, 7 4 2. This is called transpose of matrix B. Conjugate of a matrix. Taking conjugate of each number of a matrix is called conjugate of a matrix. If we have a matrix A, then its conjugate is denoted by a bar. Now we know that conjugate only changes the sign of an imaginary part of a complex number. So let us see an example. We have a matrix A which is equal to 2 3 iota 1, 2 plus 4 iota. Now let us see how to obtain its conjugate. So A conjugate is a matrix by taking conjugate of each number of this matrix. Conjugate of a real number is again a real number. Now 3 iota is an imaginary number, so it will change sign. So its conjugate is minus 3 iota. Again 1 conjugate of 2 plus 3 plus 4 iota is 2 minus 4 iota. So this is called A conjugate of matrix A, which changes only the sign of an imaginary part. Symmetric matrix. A matrix A is called symmetric if A transpose is equal to A. So if we take transpose of a matrix and as a result we get the same matrix, then A is called a symmetric matrix. Let us see an example. I have a matrix A which is equal to 3, 4, 4, 3. Now let us take its transpose. So A transpose is equal to, let us write first row in first column and second row in second column. And you can see this is again equal to A. So A transpose is equal to A mean A is a symmetric matrix. Skew symmetric matrix. A matrix A is called skew symmetric if A transpose is equal to minus A. Let us see an example. Let me have a matrix B which is equal to 0, minus 1, 1, 0. Let us take its transpose. So B transpose is equal to, write first row in first column, second row in second column. Now let us take minus as common from this. We will get 0, minus 1, 1 and 0. And we can see that this is the matrix B. So B transpose is equal to minus B. This implies that B is a skew symmetric matrix. Hermitian matrix. A matrix A is called Hermitian if we take conjugate of A and then we take its transpose and we get the same matrix A. In that case, A is called Hermitian. Let us see an example. In this example, we have a matrix A which is equal to 1, 2 minus iota, 2 plus iota, 0. Let us take its conjugate. Its conjugate is 1, 2 plus iota, 2 minus iota, 0. And now let us take its transpose. So A conjugate whole transpose is equal to 1, 2 plus iota, 2 minus iota and 0. And now we can see that this is the same matrix A. So A conjugate whole transpose is equal to A. It means that A is a Hermitian matrix. Skew Hermitian matrix. A matrix A is called skew Hermitian if A conjugate whole transpose is equal to minus A. Let us see an example. In this example, we have a matrix B, which is given by iota, 1 minus iota, minus 1 minus iota, 3 iota. Let us take its conjugate, which will change the sign of imaginary part. So we can get minus iota, 1 plus iota, minus 1 plus iota, minus 3 iota. Now let us take its transpose. So B conjugate whole transpose is equal to, let us write first row in first column, minus iota, 1 plus iota. Second row in second column, minus 1 plus iota, minus 3 iota. Let us take minus common from this. We get iota, 1 minus iota, minus 1 minus iota, 3 iota. And you can see that this is the same matrix B. So we can see that B conjugate whole transpose is equal to minus B. It means that B is a skew Hermitian matrix. Addition and subtraction of matrices. So the first rule for addition and subtraction is two matrices are capable for addition and subtraction if they have the same order. It means that if we have a matrix A and another matrix B, and if they have the same order, then we can add and subtract. If they have different order, we cannot subtract or we cannot add these two matrices. How to add two matrices? Let us see an example. In this example, I have a matrix A, B, C, D. Now I have another matrix B, which is L, M, N, P. Now to add A and B, we must add the corresponding elements. The first element with the first, the second with the second, the third with third, the fourth with fourth. So we should add the corresponding elements of matrices. Similarly, to subtract B from A, we must subtract the corresponding elements of B from the corresponding elements of A. Just like A minus L, now B minus M, C minus N, D minus L. Scalar multiplication. Multiplying a matrix by a scalar number is called a scalar multiplication of a matrix. And it is obtained by multiplying each element of the matrix by K. So let us see an example. In this example, we have a matrix A, which is equal to A, B, C, D. And now let us obtain 5A. In this case, K is 5. So to obtain 5A, we should multiply each element of A by 5. So we can multiply A with 5. We can multiply B with 5. We can multiply C with 5. And similarly, we can multiply D with 5. And this is 5A, which is scalar multiplication of a matrix A with a scalar number 5. Multiplication of matrices. First of all, we have to keep in mind that we can multiply two matrices A and B to obtain AB. If number of columns in A is equal to number of rows in B, and if number of columns in the first matrix is not equal to number of rows in the second matrix, then we cannot multiply AB. So let us see an example. In this example, let us take a matrix A. Again, I take A, B, C, D. And let us take another matrix. Let us say this is matrix B. Now, in this matrix, I have E, F, G, H, L, M. Can we obtain the multiplication AB? So look, let us see the number of columns in A, and we can see there are 2 columns in A. And now let us see number of rows in B. So there are 2 rows in B. So as the number of columns in A is equal to the number of rows in B, so we can obtain AB. And now to obtain AB, what we have to do? We must multiply first row with first column of B. So we can obtain A into E, this will be AE, plus B with H, BH. Now we can multiply first row with second column. So this is AF plus BL. Similarly, we can multiply first row of A with third column of B, and we can obtain the third element. So this is AG plus BM. Now let us multiply second row of A with first column of B. So we can obtain CE plus DH. Now we have to multiply second row of A with second column of B. So we can obtain CF plus DL. And in a similar way, we can obtain CG plus DM. And this is the required solution. Now, let us see another example. In this example, I have a matrix. Let us say I have a matrix A. In this matrix, we have 1, 2, 3, 1. And I have another matrix B in which I have 2, 1, 1, 2. And we can see that we can obtain AB. Let us obtain the multiplication AB. So to obtain the multiplication AB, we must multiply first row of A with first column of B. So we can obtain 2 into 1 into 2 is 2 plus 2 into 1 is 2. Similarly, 1 into 1 is 1 plus 2 into 2 is 4. Now let us multiply second row of A with first column of B. So we can obtain 3 2s are 6 plus 1 1s are 1. And now we have to multiply with the second column of B. So we can obtain 3 plus 2. And if we simplify this, we can get 4, 5, 7, and 5. And this is the required solution. Periodic matrix. A square matrix A is called periodic matrix if it satisfies A power k plus 1 is equal to A, where k is a positive integer. Now, if this k is the least positive integer satisfying A power k plus 1 is equal to A, then k is called period of A. If k is equal to 1, in that case, we can write A square is equal to A, and in that case, A is called idempotent matrix. Let us see an example. The example is, we have a matrix A which is equal to 1 0 1 0. Now, if I obtain A square is equal to A into A. So let us write A, which is 1 0 1 0, multiply with A 1 0 1 0. Now, when we multiply this, as a result, we get 1 0 1 0, which is again matrix A. So we can see that A square is equal to A, and that is why A is called idempotent matrix. Idempotent matrix. Nilpotent matrix. A matrix A is called nilpotent if A power P is equal to 0 matrix, where P is a positive integer. Now, if this P is the least positive integer such that A power P is equal to 0, then this P is called order of nilpotency. Let us see an example. In this example, we have a matrix A which is equal to 2 minus 1 4 minus 2. Now let us obtain A square. A square is equal to A into A. So let us multiply 2 minus 1 4 minus 2 with another A matrix which is 2 minus 1 4 minus 2. If we multiply these two matrices, as a result we get 0 0 0 0, which is a 0 matrix. So we can get that A square is equal to a 0 matrix, and this implies that A is a nilpotent matrix. Nilpotent matrix with nilpotency index 2. Involutory matrix. A square matrix A is called involutory matrix if it satisfies this equation. A square is equal to I, where I is multiplicative identity matrix. Let us see an example. In this example, we have a matrix A which is equal to 1 minus 1 0, 0 minus 1 0, 0 0 1. Now, if we obtain A square, which is equal to A into A, in that case, we can write 1 minus 1, 0, 0 minus 1, 0, 0, 0, 1. And again, we can write matrix A, which is 1 minus 1, 0, 0 minus 1, 0, 0, 0, 1. If we multiply these two matrices, as a result, we can get this matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, which is an identity matrix. So you can see that A square is equal to I. This implies that A is an involutory matrix. So let us start from the first one. Row operations or column operations in a matrix. In a matrix, we can perform three types of operations, which are called row operations or column operations. Let us see the first operation. Interchange of any two rows or columns in a matrix. So the first operation is that we can interchange any two rows or any two columns in a matrix. Rij denotes the interchanging of ith and jth row. So this is the notation. Let me write R12. So R12 mean interchanging of first and second row. The second operation is multiplication of a row or column with a non-zero number. The non-zero number may be a real number or a complex number. So in a matrix, we can multiply each element of one row with a non-zero number, or each element of one column with a non-zero number. The notation which is used for this operation is KRI. KRI denotes the multiplication of constant K with ith row of a matrix. Let me write 5 or 1, which means multiplication of 5 with each element of row 1. The third operation is addition of a scalar multiple of one row or column with another row or column, which means that we can multiply each element of one row with a non-zero constant, and then we can add that multiple to another row. The notation Ri plus Krj means the addition of k times of jth row with ith row. Let me write a simple form R1 plus 3 R2, which means multiplication of each element of R2 with 3 and adding that thing with R1. Leading entry or pivot. The first non-zero number or element in a row of a matrix is called a leading entry or pivot. Let us see some examples. So the first example, we have a matrix A, which is given by 2, 3, 7, 0, 4, 3, 0, 0, 3. Now we can see that the first non-zero number in row 1 is 2, and that 2 is called a leading entry. of row 1. In the second row, the first non-zero number is 4, and that 4 is called a leading entry or pivot. In the third row, the first non-zero element is 3, and 3 is called leading entry of row 3 of matrix A. Let us see another example. In this example B, let us write 0, 3, 4, 7, 0, 0, 1, 6, 0, 0, 1, 3. In this matrix, we can see that in row 1, the first non-zero entry is 3, and that is the leading entry. In the second row, the first non-zero entry is 1, and that is the leading entry. In the third row, the non-zero number, the first non-zero number is 1, and that is the pivot or leading entry. Echelon form of a matrix. We say that a matrix is in the echelon form if it satisfies 3 conditions. The first condition is the first non-zero element in each row must be 1. Number 2, the number of zeros to the right hand side of 1 increase row by row from up to down. And number 3, if there is a non-zero row, that must be at the bottom of the matrix. Let us see some example. So in this example, we take a matrix A in which we have 1, 3, 4, 0, 1, 7, 0, 0, 1. Now we can see that the first non-zero element in each row is 1. First condition is satisfied. Number of zeros to the left hand side of 1 increase row by row from up to down. In the first row to the left hand side of 1, there is no 0. In the second row to the left hand side of 1, there is 1 0. In the third row, at the left hand side of 1, there are 2 zeros. So number of zeros to the left hand side of 1 increase row by row from up to down. Let us see another example. In this example, we have a matrix B, and let us write its elements 0, 1, 4, 5, 6, 0, 0, 1, 3, 4, 0, 0, 0, 1, 7, 0, 0, 0, 0, 0. We can see that each first non-zero element is 1. In each row, the first non-zero element is 1. And number of zeros to the left hand side of 1 increase row by row. In the first row, we have 1 0. In the second row, we have 2 zeros. In the third row, we have 3 zeros. So number of zeros to the left hand side of 1 increase row by row from up to down. And there is only 1 0 row, and that row is in the bottom of matrix B. So matrix B is in echelon form. A reduced echelon form. We will say that a matrix is in the reduced echelon form if, in addition to these 3 properties of the echelon form, it satisfies the fourth property, which is the column in which 1 lies, all other entries of that column must be 0. Let us see example A. So in example A, I will write 1. So all other entries in the column in which 1 lies must be 0. Now in the second row there is 1. So all other entries of that column must be 1. In the third row there is 1. So all other entries in that column must be 1. So that's why A is now in the reduced echelon form. Or we can say that A is in the echelon form because the first non-zero entry in each row is 1. Number of zeros to the left hand side of 1 increase row by row from up to down. And the third one, the last one, is that the column in which 1 lies, all other elements of that column are zeros. So this is in the reduced echelon form. Let us see another example B. In this example, we have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Now you can see this matrix is in the echelon form, and in addition, the column in which 1 lies, all other entries of that column are zeros. So this is in the reduced echelon form. In some cases, we say that this is a row echelon form and row reduced echelon form. Row equivalent matrices. Two matrices are said to be row equivalent if one can be obtained from the other by finite number of row operations. If a matrix A is row equivalent to another matrix B, symbolically we shall write A is row equivalent to B, as you can see on the screen. Rank of a matrix. Let us see a simple definition. If we are given a matrix A, we should reduce that matrix to echelon form, and then we shall count the number of non-zero rows. So rank of A is equal to number of non-zero rows in the echelon form of a matrix. In this example, we should learn how to reduce a matrix to echelon form and to reduced echelon form, and how to obtain the rank of a matrix. So let us start the solution of part 1. So we can write that A is row equivalent to another matrix which is obtained by the row operation. The first thing which we need is that guy should be equal to 1. So we can divide row 1 by 6, or we can interchange row 1 and row 3. So by the operation R1, 3, which means interchanging row 1 and 3, we can get, let us write row 3 here. 1, 2, minus 5. And row 1 here, 6, 3, minus 4. And row 2 as it is, minus 4, 1, minus 6. The next thing we need that this minus 4 must be 0 and this 6 must be equal to 0. So we need another row operation to get that this 4 is equal to 0. We shall perform the row operation row 2 plus 4 R1. we can multiply row 1 with 4 and then we can add with row 2. So this will be 0. To make this 6 as 0, we can perform the operation row 3 minus 6 row 1. Multiplying row 1 with 6 and then subtracting from row 3. So let us perform this operation. 1, 2, minus 5. Now multiplying 4 with 1. So 4 minus 4 is 0. 4 2s are 8. 8 plus 1, 9. And now 4 5s are minus 20. So we get minus 26 here. Now let us multiply row 1 with 6 and then subtract it from row 3. So we get 0 here, minus 9 and plus 26. Now the next thing which we need is that this 9 must be equal to 1. So by the row operation, we can get just divide row 2 by 9 and we can get 1, 2 minus 5. Let us divide this row 2 by 9, 0. This is now 1 and this one is minus 26 by 9 and this row should be as it is, 0, minus 9, 26. The next thing is that we need that this minus 9 should be 0. So let us perform another operation and we can write the operation always on the right hand side. So R2 R3 plus 9 R2. Multiply row 2 with 9 and then add with row 3. So we will get 1, 2 minus 5, 0, 1 minus 26 by 9 and this is now 0 and you can see this is 0 and again you will see that this point is also 0. So this is an echelon form of matrix A. Now, in the second part, we have to obtain the reduced echelon form. So the column in which 1 lies, all other entries of that column must be 0. This 2 must be equal to 0. So we need another row operation. We can write the operation here on the right hand side that R1 minus 2 R2. Multiply row 2 with 2 and then subtract from row 1. So we can get 1, 0 here. If we multiply this with minus 26 into 2 divided by 9, we get 52 divided by 9, and if we simplify, we can get 7 by 9 here. And write this as it is, 0, 1 minus 26 by 9, and the remaining as it is 0, 0, 0. Now the third one is rank of matrix A. So rank of matrix A is equal to the number of non-zero rows when a matrix A is reduced to echelon form. So this one is the echelon form, and we can see that there are 2 non-zero rows. So rank of A is equal to 2. Inverse of a matrix. A square matrix B is said to be inverse of another square matrix A if AB is equal to BA is equal to identity matrix. Let us see an example. We have a matrix A, 1, 0, 3, 2, 4, 1, 1, 3, 0. Now we have another matrix B, minus 1, 3, minus 4. 1 over 3 minus 1, 5 by 3. 2 by 3 minus 1, 4 by 3. Now if we multiply A with B and simplify this, we will get 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is an identity matrix I3, 3 cross 3 matrix. In a similar procedure, if we obtain BA and simplify this, we will get 1, 0, 0, 0, 1, 0, 0, 0, 1, which is again I3. So we can see that AB is equal to BA is equal to identity matrix. This implies that B is an inverse matrix of A. In this example, we should learn how to obtain the inverse of matrix A by using the row operations. The procedure is that we should write matrix A on one side and the identity matrix on another side. Now we should reduce matrix A to the identity matrix. So for this purpose, we need that this 2 must be equal to 0 and this 1 must be equal to 0. So we perform the operation R2 minus 2R1 and R3 minus R1. And we get 1, 0, 3, 0, 4, minus 5, 0, 3, minus 3. Now we should perform the same operation on I. So we get 1, 0, 0, minus 2, 1, 0, minus 1, 0, 1. In the next step, we need that this 4 should be equal to 1. So we need another row operation. The row operation is by R2 minus R3. We get 1, 0, 3, 0, 1, minus 2, and 0, 3, minus 3. So we should perform the same operation on I. So we get 1, 0, 0, minus 1, 1, minus 1, minus 1, 0, 1. In the next step, we need that this 3 must be equal to 0. So we can write A here and identity matrix on this side. And now we can perform the row operation by R3 minus 3 R2. So we get 1, 0, 3, 0, 1, minus 2. And now this becomes 0, 0, and here we can get plus 3. And at the same time, we perform the operation and we get 1, 0, 0, minus 1, 1, minus 1, 2, minus 3, 4. Now, in the next step, we need that this 3 should be equal to 1. So let us divide row 3 by 3, and we can get by row 3 divided by 3. So we get 1, 0, 3, 0, 1, minus 2, 0, 0, 1. Now we have to perform the same operation on the other side. So we get 1, 0, 0, minus 1, 1, minus 1. And now let us divide this by 3. So we get 2 by 3 minus 3 by 3 is 1, 4 by 3. Now, in this step, we need that this minus 2 should be 0 and this 3 should be 0. So let us perform another operation. So by using R1 minus 3 R3 and R2 plus 2 R3, we get that this is 1, 0, 0, 0, 1, 0, 0, 0, 1. Now we should perform the same operation on this side. So we get minus 1, 3, minus 4, 1 by 3, minus 1, 5 by 3, 2 by 3, 1, 4 by 3. And now we can see that A has been reduced to an identity matrix. And at the same time, we get another matrix on the right hand side, and that matrix is A inverse. So A inverse is minus 1, 3, minus 4, 1 by 3, minus 1, 5 by 3, 2 by 3, 1, 4 by 3. So this is the required solution. That's all. In this video, we shall learn two methods, the Gauss elimination method and the Gauss-Jordan elimination method to solve system of linear equations. Representation of a system of linear equations in the form of matrices. If we are given a system of m linear equations in n variables, as we can see on the screen, then in the matrix notation, this system can be represented as AX is equal to B, where A is a matrix which can be obtained from the coefficients of these variables, and X is a matrix which contains all variables in this system, and B is a matrix which contains all constants on the right hand sides of these equations. Another important matrix is called the augmented matrix. AB, it contains all the coefficients of variables and constants on the right hand side of these equations. Let us see a simple example. Express the following system of two equations in two variables x and y in the matrix notations. 2x plus 3y is equal to 4, 5x plus 7y is equal to 6. In the matrix notations, this system can be represented as Ax is equal to B, where A is a matrix 2, 3, 5, and 7, which can be obtained from the coefficients of these variables. X is a matrix which contains the variables x and y in these equations. And B is a matrix which can contain the constants on the right hand side of these equations. Another matrix which is called the augmented matrix for these equations can be written as 2, 3, 5, 7, 4, 6. In the Gauss elimination method, we solve a system of linear equations by reducing the augmented matrix of that system to echelon form. And then by the backward substitution, we get the values of the variables in that system. Let us explain it by solving this example. In this example, we have two equations. In the first place, we have to obtain its augmented matrix as follows. AB is equal to 5, 4, 2, 2, 3, 4. Now, by the row operations, we have to reduce this augmented matrix to the echelon form. So we need that this 5 should be 1. We use the row operation, row 1 minus 2 are 1. Multiplying 2 with 2, we get 4. 5 minus 4 is 1. So we get 1 here. Similarly, we get minus 2 and minus 6. And this will be as it is 2, 3, 4. Now, by the row operation, we need that this 2 must be 0. So we use the row operation, R2 minus 2 R1. Let us write R1 as it is, 1 minus 2 minus 6. Now 2 ones are 2 and 2 minus 2 is 0. And then in a similar way we get 7 and here we get 16. Now we need that this 7 should be 1. So again we have to perform a row operation, R2 divided by 7. So we get 1 minus 2 minus 6. This is 0. 7 divided by 7 is 1. And this one is 16 by 7. Now by the backward substitution, we can see that this is the coefficient of x, this one is the coefficient of y. So we get that y is equal to 16 by 7. That this is equation 1. From the first row, we get this is the coefficient, 1 is the coefficient of x minus 2 is the coefficient of y. So we get x minus 2y is equal to minus 6. Let us say this is equation 2. Now we already have the value of y. So we need the value of x. So put equation 1 and 2, and after simplification we get that x is equal to minus 10 by 7. In this example, we have to solve a system of 3 equations with 3 variables x, y, and z. So let us write its augmented matrix. AB is equal to 1, 5, 2, 9, 1, 1, 7, 6, 0, minus 3, 4, minus 2. Now we have to reduce this augmented matrix to echelon form. So we need that this one should be 0. By the row operation, R2 minus R1, we have 1, 5, 2, 9. And now we get this is 0, minus 4, 5, minus 3. And the third row will be as it is 0, minus 3, 4, minus 2. Now we need that this minus 4 should be 1. So we perform the row operation. R2 minus R3. And we get 1, 5, 2, 9. Here we get 0. Here we get minus 1, plus 1, and this one is minus 1. And this is 0, minus 3, 4, minus 2. Now we have to multiply row 2 with minus 1. So we get 1, 5, 2, 9, and now this is 0, 1, minus 1, plus 1, and this is 0, minus 3, 4, minus 2. Now we need that this minus 3 should be 0. So we use the row operation. R3 plus 3 R2, and we have 1, 5, 2, 9, 0, 1, minus 1, 1. Now this is 0, this one becomes 0, and this one is now 1, this one is also 1. Now we have to use the backward substitution. So from the third row, we can see the coefficient of x is 0, the coefficient of y is 0, the coefficient of z is 1. So z is equal to 1. Let us say This is our equation number 1. From the second row, the coefficient of x is 0. The coefficient of y is 1. The coefficient of z is minus 1. And this is equal to 1. Let us say this is equation 2. From the first row, we have x plus 5y plus 2z is equal to 9. Let us say this is equation number 3. So now 2 implies just put the value of z in equation 2 and we get y minus 1 is equal to 1, which gives y is equal to 2. Now from the third equation, let us put the value of z and y in equation 3. We have x plus 5 2s are 10 plus 2 1s are 2 is equal to 9. So this is 12. 9 minus 12. We get minus 3. So x is equal to minus 3. To solve a system of linear equations by the Gauss-Jordan elimination method, the key point is that we should reduce the augmented matrix of that system to reduced echelon form. We explain the method by solving this example. Let us write the augmented matrix of this system. AB is equal to 1, 3, 2, 2, 2, 7, 7, minus 1, 2, 5, 2, 7. Now we have to reduce this augmented matrix to the reduced echelon form. So we need the row operations to make this 2 as 0 and this guy also as 0. By row 2 minus 2 or 1, we can make this 0. Let us write 1, 3, 2, 2. And now 2 2s are 2, 2 minus 2 is 0. And this one is 1, 3, minus 5. The next operation is R3 minus 2 or 1. So again we can get here 0, minus 1, minus 2, and 3. Now by the row operations, we need that this minus 1 should be 0 and this 3 should also be 0. So we perform the operation row 1 minus 3R2 and row 3 plus row 2, and we get 1, 0, minus 7, 17, 0, 3, sorry, this one is 1, let me write it again, this one is 1, 3, minus 5. And now 0, this becomes 0, 1, minus 2. Now the next thing which we need, this 3 should be 0 and this minus 7 should be 0. So we have to perform another row operation. or 1 plus 7 or 3. If we multiply 1 with 7 and then add it with this one, so we can get 0. And now R2 minus 3 R3. So we get 1, 0, this one becomes 0, and this one is 3. 0, this one is 1, it will become 0, and this one is now 1 because 2 2s are okay, 3 2s are 6, so minus 5 plus 6 is 1. And this one is 0, 0, 1, minus 2. And now let us use the equation. So we can see from the first row, the coefficient of x is 1, but the coefficient of y and the coefficient of z, they are 0. So we get x is equal to 3. From the second row, you can see the coefficient of x is 0. The coefficient of y is 1. The coefficient of z is 0. So we get y is equal to 1. From the third row, the coefficient of x and y, they are 0, and the coefficient of z is 1. So z is equal to minus 2. That's all. Dear students, a vector space is a particular type of a non-empty set. By a particular type of non-empty set, we mean that this is a set which satisfies 10 properties, which we will study in detail shortly. To prove the first 5 properties, we take all elements from inside V, and they are called internal properties. And to prove the last 5 properties, we take some elements from another set, which is called field, and they are called the external properties. In most cases, we consider that a field is a set of real numbers or complex numbers. The elements of a field are called scalars. We denote them by A, B, or C. The elements of a vector space V are called vectors. We denote them by U, W, and S. To show that a non-empty set V is a vector space, we shall verify 10 properties. The first property is the closure property under addition, which means that if we add any two elements of V, the resultant element must be inside V. The second property is the associative property, which means U plus into W plus S will be equal to U plus W plus S. The third property is that there must be an additive identity inside V, which means there will be an element inside V. When we add that element to any other element of V, we will get the same element. The fourth property says that there will be additive inverse of each element, which says that if there is an element U of V, then there must be an other element minus U inside V, such that if we add minus U with U, we shall get the additive identity. The fifth property is the commutative property, which says that u plus w must be equal to w plus u. Now, if a set satisfies the first four properties, that set is called a group. And now, if it satisfies the first five properties, then that set is called an abelian group. The sixth property is the closure property under scalar multiplication, which means that if we take an element from the field and any element from the vector space and we multiply them, the resultant element must be inside V. The seventh property is the associative property under scalar multiplication, which means that A into BU must be equal to AB into U. The eighth property is the identity, which says that inside V there will be a scalar identity or multiplicative identity, which means there will be a number such that when we multiply that number with any element of U of V, we will get the same element. The ninth property is the distributive property, in which we take two elements from V and one element from the field. So it says A into U plus W is equal to AU plus AW. The 10th one is also the distributive property, in which we take two elements from the field A plus B and one element from the vector space, and this is equal to AU plus BU. Now, if a set satisfies these 10 properties, we will say that set is a vector space. We can see that the first property and the sixth property are similar. The second property and the seventh property are similar. The third property and the eighth property are similar. In this example, we show that R square is a vector space. Hence, R square will satisfy all the 10 properties of a vector space. So the first property is, let us take two elements U, which is A1 comma B1, and W, which is A2 comma B2 from R square. Now if we add U with W, we will add first element with first and second with second, and we can see the resultant element is also an order pair. So this belongs to R square, and it shows that R square is closed under addition. Let us see the second property, which is associative property under addition. We take three elements U, W, and S. Let us put values. First add W and S, and then add U with this. Now arrange them in this way, and we can see that this is U plus W and this is S. So U plus W plus S is equal to U plus W plus S. So associative property under addition is satisfied. The third property is, inside V, we can see that A and B are real numbers. So A may be 0, B may be 0. So we can get 0 comma 0. So inside R square, there exists an additive identity. Let us prove the fourth property. If we take any element U, which is A1 comma B1 from R square, there exists minus U in that R square. When we add u with minus u, we get additive identity. So it says that additive inverse of each element exists. Now let us see the commutative property. We add u plus w and then arrange the elements. Then we write in this form, and now the first one is w, the second one is u. So the commutative property is satisfied. In property number 6, we take an element from the field, which is a set of real numbers, and one element from V. When we multiply these two elements, we again get an ordered pair, which shows that Ku belongs to R square and V is closed under scalar multiplication. In property number 6, we prove the associative property under scalar multiplication. So we take two elements A and B from field and one element U from the vector space. And we first multiply B with U and then we multiply A with this. Then we taking AB as common and we get that AB into U. So the associative property is satisfied under scalar multiplications. Now property number 8 is there exists a number 1. When we multiply this number, when any element of V with the vector space, we get the same element, so multiplicative identity exists. Property number 9 is associative property, in which we take two elements from the vector space and one from the field. First, we add these two elements, then we multiply A, then we arrange them in such a way that we get AU plus AW. So the distributive property is satisfied. In the 10th property, we take two elements from the field and one from the vector space. Then we multiply A plus B with U, and let us see what we can get. Multiplying A plus B with A1 as well as B1, and then we multiply A1 with each element and B1 with each element. And then we can arrange in this way. Taking A common from the first one and B from the second one, we get AU plus BU. So property number 10 is satisfied. Since all properties of the vector space are satisfied, we will say that R square is a vector space. In a similar way, we can prove that R, R cube, R4, and up to Rn are vector spaces. In example number 2, we are given a non-empty set V which contains all those polynomials whose degree is 3. Let us see whether this set V is a vector space or not. So if it is a vector space, it must satisfy all 10 properties of the vector space. We are checking the first property, which is the closure property under addition. Let us take two polynomial from V. We denote the first polynomial by P1 of x, which we write 2x cubed minus 3x square plus 4x plus 3. We can see this is a polynomial of degree 3, so it belongs to V. We are taking now another polynomial. Let us denote it by P2 of x. This is equal to minus 2x cubed plus 3x square plus 2x plus 5, and we can see this is a polynomial of degree 3, so it also belongs to the set V. Now let us add these two polynomials, P1 of x plus P2 of x. Adding these two polynomials, the first two terms will cancel. So we get 6x plus 8. And we can see this is a polynomial of degree 1. So it does not belongs to V. This implies that V is not closed under addition. So the first property is not satisfied. This implies V is not a vector space. In example number 3, W is a set which contains all those polynomials whose degree is less than or equal to 3. We need to prove that W is a vector space. Let us write it in a simple form. W may be written like this one. It contains a polynomial of 0 degree, a polynomial of degree 1, a polynomial of degree 2, a polynomial of degree 3, Cx plus D, where we can say that A, B, C, and D, these are real numbers. So A may be 0. In that case, it contains the additive identity. Now we can prove that this set satisfies all properties of the vector space. So that is a homework. You can try this question. In example number 4, we are given a non-empty set V which contains only those elements of our cube which satisfies this relation. And we need to prove that this set of vectors is a vector space. So the first property is the closure property under addition. Let us take two elements from this set. I will say U is equal to 1, 1, 1 is an element of V. Why this is an element of V? Because it satisfies this relation. Let us take left hand side of that relation. The left hand side is x minus 2y square plus z power 4. Now if I put x is equal to 1, y is equal to 1, and z is equal to 1, we get 0, which is a right hand side of that relation. So the element U belongs to the set V. Now we are taking another element, let us say W, from that set. So I will write 2, 3, 2. This element belongs to the set V. Why this belongs to the set V? Again, take left hand side of that relation. So this is x minus 2y square plus z power 4. And now substitute the values. So I will write x is equal to 2, y is 3. 3 3s are 9, 9 2s are 18 plus 2 power 4. 2 2s are 4, 4 2s are 8, 8 2s are is 16. So if I simplify this, we get 0, which is right hand side of that relation. So U and V are any two elements of the set V. We need to add these two elements, U plus W. So if we add, we will add first with first. This is 3, second with second, and third with third. And now let us see whether this element is an element of V or not. So again, I am taking the left hand side of that relation. The left hand side is x minus 2 y square plus z power 4. And now let us substitute the values. So we have 3 here, and if I put 4 here, so we get minus 32 here. Now if I substitute z is equal to 3, we get 81 here. If we simplify, we get 52. And this is not equal to 0. In other words, this is not equal to the right hand side. So this implies that u plus v does not belongs to v, which means that v is not closed under addition. And this implies that V is not a vector space. That's all. Dear students, a subspace is a subset of a vector space which is itself a vector space. In other words, if we know about a vector space and we find a subset of that vector space which satisfies all the 10 properties of a vector space, then that subset is called a subspace. As we can see that from the definition number 1, it is a long procedure to show that a subset of a vector space is a subspace. So that is why we will use definition number 2 to prove that a subset H of a vector space is a subspace. According to definition number 2, if a subset H of a vector space V satisfies 3 properties, then we will say that H is a subspace. The first property is the closure property under addition, which means that if we take any 2 elements U and W from H, and now if we add these 2 elements U plus W, and the resultant element is inside H, then we will say that H is closed under addition for all U comma W belongs to H. The second property is the closure property under scalar multiplication, which means that if we take any number from a field, we take the set of real numbers as our field, and any element from the subset H. Now if we multiply these 2 elements and the resultant element AU belongs to H, we will say that H is closed under scalar multiplication. Property number 3 is that the 0 vector of H and V will be same. In other words, we can say that the 0 vector of V is in H. Now if a subset H satisfies these 3 properties, we will say that that subset H is a subspace. In this example, we are given a subset H of R square which contains only those elements of R square whose first part is 0 and second part is any real number. Let us check whether H is a subspace or not. So we are going to prove the first property, which is called the closure property under addition. Let us take any two elements of H. I am taking U, which is equal to 0, comma B1, and now I am taking another one, which is 0, comma B2. These are two elements of H because they are an ordered pair and the first part is 0. Let us add these two elements, U plus W, then 0 plus 0 is 0, and B1 plus B2. We can see that the resultant element is an element of H because the first part is 0 and the second is any real number. So this implies that H is closed under addition. And now let us check the second property. In this property, we take some element from a field which is set of real numbers and some element U which is 0, comma B1 from H. Now let us multiply these two elements U and H. We have A into 0, comma B1. If we multiply, we get 0, comma A B1. We can see that this is also an element of H. So this implies that H is closed under scalar multiplication. Scalar multiplication. And now let us see the third property. In the third property, we can see that in H, we have elements, the first part is 0 and B is any real number. So if we take B as 0, then we can write that 0, comma 0 is an element of H, and this is the additive identity, which is also the additive identity of the vector space R square. So H and V have the same 0 vector. Since all properties are satisfied, this implies that H is a subspace of R square. Dear students, a linear transformation is a function which satisfies two properties. As we are working on vector spaces, so we will define that a function t from one vector space to another vector space is called a linear transformation if it satisfies two properties. The first property is that if we take any two elements from the domain V and then add these two elements, after that apply T on them, then T of U1 plus U2 will be equal to T of U1 plus T of U2. The second property is that if we take any element from our domain V and take some scalar, let us say it is some real number, then T of Cu will be equal to C T of u. Let us explain it by some examples. In this example, we are given a function t which is defined by this relation. So we can see that in the first place, we keep the first element of the domain as it is. And in the second place, we add the first and second element of the domain. This function can also be written as t of x, y, which is a matrix, is equal to x plus y. It is also a column vector. So now let us check the first property. So for the first property, we take any two elements, u1, which is equal to x1, y1, and we take another element u2, which is equal to x2, y2 from our square. Now let us add these two elements, u1 plus u2. So we get x1 plus x2, y1 plus y2. It is a simple addition of matrices. And now let us find transformation of u1 plus u2. So T of u1 plus u2 is equal to, according to the definition of T, we shall keep the first element as it is. And in the second place, we shall add the first component with the second component. So we get this thing. Let us say this is 1. Now we need to find T of u1. So T of u1 is x1, y1. So according to the definition, this can be written as x1 plus y1. And now let us find T of u2. So we have T of the value of u2 is x2, y2, which is equal to x2 plus y2. Now let us add T of u1 with T of u2. So we get, adding these two, we get x1 plus x2, and then we get x1 plus y1 plus x2 plus y2. So we can say that this is equation number 2. Now from 1 and 2, we can see that T of u1 plus u2 is equal to T of u1 plus T of u2. Hence, the first property is satisfied. Now to check the second property, we need any element from the domain and some constant. So then we shall verify this equation. Let us take some element u1, which is equal to x1, y1 from our square, and some constant c from R. Then multiply c with u1. So we have cx1, cy1. Now let us take T of cu1. So this can be written as T of cx1, cy1. Using the definition of transformation, we keep the first one as it is, cx1, and in the second place we add the first element with the second element. Let us say this is equation number 3. Let us find T of C into T of U1. This can be written as TC, T of U1. Now U1 is X1, Y1. Applying the definition of transformation, we have X1 and then we have X1 plus Y1. Let us multiply C. So we have CX1, CX1 plus CY1. And let us say this is 4. Now from 3 and 4, we can see from 3 and 4, we can see that T of C U1 is equal to C T of U1. So second property of the linear transformation is satisfied. So in a simple word, we can say T is a linear transformation. In this example, we are given a new relation. T is defined by this one. We can see that in the range, the first element is 0 and the second element is the square of the second element of the domain. To check that this is a linear transformation or not, it must satisfy both properties. Let us see the first property. So we take a real number C and any element U from the domain and then multiply C and U. So we get CX, CY. And let us find T of CU. This can be written as T of CX, CY. Now, according to the definition, we can write that the first element is 0 and we will square the second element. So we can write C square, Y square. Let us say this is 1. Now, we need to find Cn2 T of U. This can be written as C T of U is XY. So according to the definition, we can write 0 y square. And now let us multiply C with that one. So we have C T of U. This is equal to 0 C y square. Let us say this is 2. Now from 1 and 2, we can see that T of Cu is not equal to C T of U. So this implies that T is not a linear transformation. So if one or both properties are failed, then we will say that T is not a linear transformation. That's all. Linearly independent and linearly dependent vectors. Dear students, if we are given a set of vectors from a vector space, then these vectors will be linearly independent or linearly dependent. Now, to determine whether these vectors are linearly independent or dependent, we shall put this linear combination equal to a 0 vector. And from this we shall get a system of equations. We shall solve the system of equations to obtain the values of C1, C2 up to Cn. If we get that all the constants are 0, then we shall say that these vectors are linearly independent. And if we get that at least one constant C1 or C2 is non-zero, then we shall say that these vectors are linearly dependent. Let us explain it by some examples. In this example, we are given two vectors, v1 and v2. They belongs to R square. Let us determine whether they are linearly independent or dependent. So we shall put the linear combination C1 V1 plus C2 V2 equal to a zero vector. Let us put the values of V1, which is 1, 2, plus C2, putting the value of V2, we get 2, 3, which is equal to a zero vector 0, 0. Let us multiply C1, so we get C1, 2, C1, plus multiplying C2, we get 2, C2, 3, C2, and this is equal to 0, 0. From this we get a system of equation C1 plus 2, C2 equal to 0 and 2C1 plus 3C2 equal to 0. Let us solve this system of equation by the Gauss elimination method. So the augmented matrix is 1, 2, 0, 2, 3, 0. Now we need that this 2 must be 0. So let us subtract 2 or 1 from our 2. We get 1, 2, 0. Now this one is 0, this is minus 1, and this is 0. In the next step, we multiply row number 2 with minus 1. So we get 0, 1, 0. Now by backward substitution, we get C2 equal to 0. And then from the other equation, we get C1 plus 2, C2 equal to 0. But as C2 is 0, so we can write that C1 plus 2 into 0 is 0, which is equal to 0. From this we get C1 is equal to 0. So we can see that both constants C1 and C2 are zeros. So this implies the vectors V1 and V2 are linearly independent. In example number 2, we show that the given three vectors are linearly dependent. In a similar procedure, we shall put the linear combination C1V1 plus C2V2 plus C3V3 equal to a zero vector. Let us substitute the values of V1, V2 and V3. So we have 1, 2, then plus C2, here we have 1, minus 1, plus C3, Here we have 1, 3, which is equal to the 0 vector. From this we get C1 plus C2 plus C3, comma, 2C1 minus C2 plus 3C3 equal to 0, comma 0. From this we get a system of equations. C1, C2 plus C3 equal to 0 and 2C1 minus C2 plus 3C3 equal to 0. Let us write the augmented matrix. So we have 1, 1, 1, 0, then 2 minus 1, 3, 0. Now we need that this number should be 0. So let us apply the row operations. R2 minus 2 R1. So we have 1, 1, 1, 0. From here we get 0. Here we get minus 3. And here we get 1 and this one is 0. Now this minus 3 should be 1. So let us apply another row operation. We write 1, 1, 1, 0. And then we multiply row number 2 with minus 1 over 3. So we have 0, 1, minus 1 over 3 and 0. Now by backward substitution, we have C2 minus 1 over 3, C3 equal to 0. Let us say this is equation number 1. Then we have C1 plus C2 plus C3 equal to 0. This is equation number 2. Now from 1 we can obtain that C3 is equal to 3C2. So here we let C2 equal to some non-zero real number t. Then C3 becomes equal to 3t. Now using the value of C2 and C3 in 2, we get C1 plus C2 is t and C3 is 3t. This is equal to 0. From this we get C1 is equal to minus 4t. So we have C1, C2, C3, which is equal to the value of C1, that is minus 4t, the value of C2, that is t, the value of C3, that is 3t. Let us take t as common. So we have minus 4, 1, 3. So for any non-zero real number t, we have different solution of this system. So we can see that the values of C1 and C2 and C3 are non-zeros. So this implies that the one solution of this system is C1 is equal to minus 4, C2 is equal to 1, C3 is equal to 3. But this system has an infinite number of solutions. So this implies that the vectors v1, v2 and v3 are linearly dependent. That's all. Dear students, a spanning set is a set of all linear combinations of a subset of a vector space. Let us explain it by these figures. If we are given a vector space which we represent by this black circle, and there is a subset S of this vector space, we represent the subset S by the blue circle. For simplicity, let us assume that in S there are only two elements, V1 and V2. Then a spanning set S is another set which contains all the linear combinations of the elements of S. So we can see that the first linear combination FC2 is 0, we can take C1V1. If C1 is 0, we can take another linear combination C2V2. If both are non-zeros, we can write C1V1 plus C2V2. So this set which contains all the linear combinations of the elements of S, S is a subset of V, is called a spanning set. And we can see that C1 and C2, these are real numbers. So real numbers are infinite. So there will be infinite number of elements in the spanning set. Let us explain it mathematically. We say that V is a vector space and there are V1, V2, V3 and up to Vn. So there are total n elements in V. We take another subset S, which is this one containing only two elements, V1 and V2. These are the elements of V because S is a subset of V. Then another set S, which contains all those elements which are the linear combinations of the elements of V1 and V2. That set S is called a spanning set. In simple word, the spanning set is denoted by this symbol and it will contain elements C1V1 plus C2V2. But these are infinite number of elements because C1 and C2 are real numbers. We can put the value of C1 as 0, 1, 2, 3, 1 over 2, 1 over 3, minus 1, minus 2. Similarly, we can put the value of C2 equal to 0, 1, 2, 3, minus 1, minus 2, 1 over 2, minus 1 over 2. So there are infinite numbers of elements in the spanning set S. Basis for a vector space. We say that a subset S of a vector space V is called basis for V if it satisfies two properties. The first property is elements of S will be linearly independent. Let us see what we mean by linearly independent. Let S is a set of these elements V1, V2 up to Vn. If we put the linear combination of these elements equal to a zero vector and simplify this, and we get that all values of these constants are zeros. It means that this set is linearly independent. The second property is span of S will be equal to V, or we can say that S spans V. It means that if we take any element from the vector space, that can be written as a linear combination of the elements of S. Now let us explain it by an example. In this example, we have a set B in which there are two elements. We show that this set B is a basis for a vector space equal to R square. The elements of R square are order pairs. To show that B is a basis for R square, we shall satisfy two properties. The first one is the elements of B will be linearly independent. So let us represent the first element by V1, the second by V2, and now we put the linear combination of these elements equal to 0. Use the value of V1 and V2. In this equation, we get that thing. Now multiply C1 inside here and C2 inside here. We get this, and comparing, now add the first element with the first, second with the second. And then compare both sides. This will be equal to 0 and this thing will be equal to 0. So we get two equations. Now the task is to solve these two equations to get the value of C1 and C2. The first method is to add these two. C1 will cancel and we can get C2 equal to 0. Put C2 equal to 0 in any of these equations, we get C1 equal to 0. But we shall use the method of matrices because it will be useful for other questions. To learn that method, we shall express these two equations in the form of augmented matrix. The augmented matrix is the coefficients of these things 1, 2, 0. The coefficient of this equation -1, 4, 0. Now we shall reduce it to the echelon form. In echelon form, this element will be 0. So adding row number 1 with row number 2, we get this. Now this element must be 1. So divide row number 2 by 6. Now this is in the echelon form. By backward substitution, we can get 0 C1 plus 1 C2 equal to 0, which gives C2 equal to 0. From this equation, 1 C1 plus 2 C2 equal to 0, but C2 is 0, so this gives C1 equal to 0. As both these constants, C1 and C2 are zeros, so it means V1 and V2 are linearly independent. In other words, this set B is linearly independent and the first property is satisfied. Let us see the second property, in which we will show that S spans V. So we shall take any element from V. V is R square. So and any arbitrary element of R square is A comma B. Then we put that element equal to the linear combination of the elements of B. Now using the value of V, V1, V2, multiply C1 here, C2 in this one. Is a similar procedure. We can get C1 plus 2C2 equal to A minus C1 plus 4C2 equal to B. Now we shall solve this system of two equations to get the value of C1 and C2. If we get the value of C1 and C2 in terms of A and B, we can put the value of C1 and C2 here, and it means we can represent any element of R square as a linear combination of V1 and V2. So its augmented matrix is 1, 2, A. Then -1, 4, B. Reduce it to the echelon form. This will be 0. Add row number 1 with 2. We get this thing. This must be 1. So divide row number 2 by 6. And now we can see This is in the echelon form. By backward substitution, we get C2 is equal to B plus A by 6. From here, C1 plus 2C2 is equal to A. But use the value of C2 here and simplify it. So we can get C1 is equal to 2A minus B divided by 3. Put these two values in equation number 1 and we get this equation. And you can see that AB is an arbitrary element of our square. So we can represent any element of our square as a linear combination of these two elements of B. Hence, span of B is equal to V, or we can say that B spans V. Second property is satisfied. As both properties are satisfied, we say B is a basis of our square. Now let us check that any element of our square can be represented as a linear combination of these two elements. So take any element from our square, just like I'm taking 1, 0. This is a member of our square. Students can take 2, 3, 4, 7, 10, 100, or 1000, 10,000. So if you take any element, put the value of A and B in this equation on both sides and simplify this, we will get this thing. Now take the right hand side, multiply this inside here, this one here, then add the corresponding element, and after simplification we get the left hand side. So if students, in this video we shall define and explain the method to find the eigenvalues and eigenvectors for a square matrix. We shall solve two examples. In example number 1, we shall take a matrix of order 2 cross 2, and in example 2, we shall take a matrix of order 3 cross 3 to find the eigenvalues and eigenvectors. Let us see the definition of eigenvalues and eigenvectors. We say that a real or complex number lambda is called an eigenvalue of a square matrix A if there exists a column vector X such that this equation is satisfied. Here I is the identity matrix and the order of A and I must be same. X gives us the eigenvector and it is a column vector, a matrix with only one column. Let us explain it a little more. If in a given question we are given a square matrix A of order 2 cross 2, then we shall take I of the same order. And in this case, the column vector X must be given by x1, x2, which is a matrix with only one column but with two rows. And now if A is a given matrix of order 3 cross 3, then I must be of the same order. And in this case, the matrix X must be equal to x1, x2, x3, which is a matrix with only one column but of 3 rows. To find the eigenvalues, we must solve this equation, which is determinant of A minus lambda I equal to 0. This equation is called the characteristic equation. When we solve this equation, we can get the values of lambda, such as lambda is equal to a comma b and so on, and these are called the eigenvalues. For each value of lambda, we can find at least one eigenvector. To find an eigenvector for a given value of lambda, we must solve this equation to find the values of x. For example, if lambda is equal to a, we shall put the value of lambda, and then we have to simplify and solve this equation and find the values of x1, x2 and so on, and that will be our corresponding eigenvector. In example number 1, we shall learn how to find the eigenvalues and eigenvectors of a square matrix A. Let us start the solution. The first thing which we need is A minus lambda I. Let us put values. So we have 2, 2, 5, minus 1. Minus lambda, and the value of the identity matrix is 1 0 0 1. If we simplify this, we have a minus lambda I is equal to 2 minus lambda 2 5 minus 1 minus lambda. Let us say this is our equation number 1. Now, to find the eigenvalues, we must solve the equation determinant of A minus lambda I is equal to 0. Let us put values. So we have 2 minus lambda 2, 5 minus 1 minus lambda equal to 0. To solve this determinant, we must multiply 2 minus lambda with minus 1 minus lambda, and then minus 5 into 2. So let us simplify this. We have lambda square minus lambda minus 12 is equal to 0. And now let us factorize this. So we have lambda square minus 4 lambda plus 3 lambda minus 12 is equal to 0. If we further simplify this, we have lambda plus 3 into lambda minus 4 is equal to 0. And from this we have two values. Lambda is equal to minus 3 and the other value is lambda is equal to 4. And these two are the eigenvalues of the square matrix A. For each value of lambda, we can find at least one eigenvector. So let us take lambda is equal to minus 3. To find an eigenvector, we must solve the equation A minus lambda I into x is equal to 0. Let us put values in this equation. So from 1 we have 2 minus lambda 2, 5 minus 1 minus lambda into x1, x2, which is the value of x, and this is equal to 0. Now we can see that lambda is equal to minus 3. So if we put lambda is equal to minus 3, we have 5, 2, 5, 2 into x1, x2 equal to 0. Let us multiply these two matrices. So we have 5x1 plus 5, sorry, plus 2x2. And from the second row, we have 5x1 plus 2x2 is equal to 0. From this, we can get two equations. 5x1 plus 2x2 is equal to 0. The other equation is also same, which is 5x1 plus 2x2 is equal to 0. From any one of the above equation, we get the value that x2 is equal to minus 5 by 2 x1. And now we suppose that the value of x1 is equal to t. So therefore we get that the value of x2 is equal to minus 5 by 2t. Now putting these values in x, we have x is equal to x1, x2. So if I put the value of x1, which is t, then the value of x2 is 5 by 2 t. Now taking t as common, but to remove the fraction, let us take 2t as common. So we have 1 minus, sorry, this one is 2 minus 5. So this is the required eigenvector corresponding to the eigenvalue minus 3. But we can see that t here is any scalar. So any scalar multiple of this vector is an eigenvector of the given matrix A. So I can say that when lambda is equal to minus 3, we have an eigenvector 2 minus 5. This is only one eigenvector, but multiplying this vector with any scalar, you can get infinite number of eigenvectors for lambda is equal to minus 3. To find the eigenvectors for the other value of lambda, which is equal to 4, we will do the same procedure. So let us solve the equation a minus lambda I into x is equal to 0. And now let us put values in this equation. So we have 2 minus lambda, 2, 5 minus 1 minus lambda into the value of x, x1, x2 is equal to 0. And now let us put the value of lambda, which is 4. If we put the value of lambda, we have minus 2, 2, 5 minus 5 into x1, x2, which is equal to 0. Let us multiply these two equations. So we have minus 2x1 plus 2x2. Then 5x1 minus 5x2 is equal to 0. Now we have two equations. Minus 2x1 plus 2x2 is equal to 0. Let us say this is equation 2. And the other one is 5x1 minus 5x2, which is equal to 0. Let us solve equation number 2. So from equation number 2, we have x2 is equal to x1. If we solve equation 3, we can get the same value, x2 is equal to x1. So now let us suppose, let the value of x1 is equal to some scalar, let us say s. Then the value of x2 is the same scalar, s3. So we have the eigenvectors s, s. Let us take s as common. So we have 1, 1. So corresponding to lambda is equal to 4, we have an eigenvector 1, 1. But let us repeat once again that s is a scalar number. Let us say is a real number. So any scalar multiple of this is also an eigenvector. So there are infinite number of eigenvectors associated to the value lambda is equal to 4. In example number 2, we shall find the eigenvalues and eigenvectors for a 3 cross 3 matrix. The method is same. So let us find A minus lambda I, which is equal to 3 minus lambda minus 1, 2. 3 minus 1 minus lambda 6 minus 2, 2 minus 2 minus lambda, and let us say this is our equation number 1. To find the eigenvalues, we shall solve the equation determinant of A minus lambda I is equal to 0. Let us put values from 1. So we have 3 minus lambda minus 1, 2. 3 minus 1 minus lambda 6 minus 2, 2 minus 2 minus lambda, determinant is equal to 0. And now let us expand this determinant. So if we expand, we can get 3 minus lambda into 2 plus lambda plus 2 lambda plus lambda square minus 12. And now minus, but the sign of 1 is minus, so minus into minus plus 1 into minus 6 minus 3 lambda plus 12. And the next term is plus 2 into 6 minus 2 minus 2 lambda is equal to 0. Now, if we further simplify this, we get lambda cube minus 12 lambda plus 16 equal to 0. And now let us find the roots of this equation. So by guessing, one root must be in the divisor of 16. So we can see that if I put lambda is equal to 2, this equation is satisfied. So lambda is equal to 2 is one root of this equation. And now to find the other roots, we can divide the given equation by lambda minus 2, or we can use the synthetic division. So let us use the synthetic division. I am writing the coefficients. The coefficient of lambda cube is 1. The coefficient of lambda square is 0, minus 12, and then we have 16. And now let us use the synthetic division. I will write the root here. Now 1 into 2 is 2. I get 2 here. 2 2s are 4. I get minus 8 here. Minus 8 into 2 is minus 16. So we can see the remainder is 0. So I get lambda square plus 2 lambda minus 8 equal to 0. And now let us factorize this. So I have lambda square plus 4 lambda minus 2 lambda minus 8 equal to 0. And if we further simplify this, we can get lambda plus 4 into lambda minus 2 is equal to 0. So we have two more roots. Lambda is equal to minus 4 and lambda is equal to 2. So all the eigen values of this matrix are minus 4, 2 and 2. So we have three eigenvalues for the given matrix. 2 is repeated and minus 4 is a distinct real root. Now let us find eigenvalues corresponding to the eigenvalue lambda is equal to minus 4. So we must solve the equation a minus lambda I into x is equal to 0. Let us put value of a minus lambda I from 1. So from 1 we have 3 minus lambda minus 1, 2. 3 minus 1 minus lambda 6 minus 2, 2 minus 2 minus lambda. And the value of x, let us say it is x, y, z, which is equal to 0. Now if we put the value of lambda which is equal to minus 4, we have from here 7 minus 1, 2, 3, 3, 6, minus 2, minus 2, and minus 2 plus 4 is 2 into x, y, z equal to 0. Let us multiply these two matrices and we have three equations. 7x minus y plus 2z equal to 0. 3x plus 3y plus 6z equal to 0. Minus 2x plus 2y plus 2z equal to 0. So now we have three equations. Here we use the method of cross multiplication, which is also called the Cramer rule. So we can use any two of these equations. This is equation number 2, this one is 3, and this one is 4. So I will solve 2 and 3, but you can take any two equations. So according to that method, we write x equal to minus y equal to z. Now x is divided by the determinant. So we will ignore the x variable. So we can write the coefficient of y and z. This is minus 1, 3, 2, 6. Now in case of y, let us ignore y. So we can write 7, 3, and 2, 6. And now in case of z, we shall ignore the variable z. So we can write 7, 3 minus 1, 3. And now we put this thing equal to t. So let us simplify this. From here we can get x divided by, it is just a determinant. You can just simplify the determinant and you can get minus 12 here, which is equal to minus y divided by, we can get 36 here, which is equal to z, and divided by, we can get 24 equal to t. Now from here we can write x over minus 12 is equal to t, and this gives x is equal to minus 12t. From the other one we get minus y over 36 is equal to t. This will give us y is equal to minus 36t. From the third one we get z divided by 24 is equal to t, which gives z is equal to 24t. Hence we have the eigen vector x is equal to x, y, z. Let us put the values. So we can write minus 12t minus 36t, 24t. And let us take minus 12t as common. So we have 1, 3, minus 2. So this is the required eigenvector. So I can write here that with respect to lambda is equal to minus 4, we have the eigenvector 1, 3, minus 2. Any scalar multiple of this vector is an eigenvector corresponding to lambda is equal to minus 4. So there are infinite eigenvectors. To find eigenvectors when lambda is equal to 2, just remember that 2 is a repeated eigenvalue. 2 occurs 2 times. So we will proceed as usual. We must solve the equation a minus lambda I into x is equal to 0. And now let us put value of a minus lambda I and x. So from 1 we can write that the value of a minus lambda I is 3 minus lambda minus 1, 2. 3 minus 1 minus lambda 6. The third row is minus 2, 2 minus 2 minus lambda. And now let us multiply this matrix with x, which is x, y, and z. And this is equal to 0. The value of lambda is 2. Let us put the value of lambda. If I put lambda is equal to 2, we get 1 minus 1, 2. 3 minus 3, 6. Minus 2, 2 minus 4 multiplied with x, y, and z, which is equal to 0. Now let us multiply these two matrices. So I get x minus y plus 2z is equal to 0. Then I get 3x minus 3y plus 6z is equal to 0. And now from the final row I get 2x plus 2y minus 4z is equal to 0. So the next task is to solve this system of equation. So I would like to suggest all the students, when you have repeated eigenvalues, you should use the row operation, which is called the Gauss elimination method or the Gauss-Jordan elimination method. So first of all, we need the augmented matrix for this system. So the augmented matrix is the augmented matrix is 1 minus 1 2, which is equal to 0. Then 3 minus 3 6, which is equal to 0. Minus 2 2 minus 4, which is equal to 0. So I will draw a line here. Now the task is to reduce this matrix to the echelon or reduced echelon form. So we need that this number must be 0 and this number must be 0. So we need a row operation. Let us apply the row operation. So the first row operation, which I would like to make 3 as 0, is R2 minus 3R1. And to make minus 2 as 0, we need the operation R3 plus 2 R1. So let us write row number 1 as it is. 1 minus 1, 2, and this number is 0. And now if I apply operation, I get 0, 0, 0. Similarly, from the second operation, I get 0, 0. And these numbers are as it is. So now from here, I can write from the first row, x minus y plus 2z is equal to 0, which can be further simplified as x is equal to y minus 2z. Now we put, let y is equal to t and z is equal to k. So x is equal to t minus 2k. Hence, the eigenvector x is equal to x, y, and z becomes, let us put values of x, which is t minus 2k. The value of y is t, the value of z is k. And now let us simplify it a little more. So I can write t 0 plus I can write minus 2k 0 k. Let us take t as common. So I can write x is equal to, let us take t as common from the first one. So I have 1, 1, 0. And let us take, now let us take k as common from the second matrix. So what we get? We get minus 2, 0, 1. So we have two eigenvectors associated to lambda is equal to 2. And let us write this. Hence we can say that when lambda is equal to 2, we have two eigenvectors. 1, 1, 0. The other vector is minus 2, 0, 1. Again, I will repeat that 1, 1, 0 or minus 2, 0, 1. We can say this is one eigenvector, but any scalar multiple of this vector is another eigenvector associated to lambda is equal to 2. So there are infinite number of eigenvectors. That's all. Mathematics. In this video, we shall present an introduction to ordinary differential equations. These are the topics which we shall study in this lecture. Let us start from the first one. Let us see the definition of a differential equation. We say that an equation containing the derivatives of dependent variable with respect to one or more than one independent variable is called a differential equation. There are two types of differential equations: ordinary differential equations and partial differential equations. We say that an equation involving the ordinary derivatives of a dependent variable with respect to a single independent variable is called an ordinary differential equation. And an equation containing the partial derivatives of a dependent variable with respect to more than one independent variable is called a partial differential equation. Let us see some examples. In the first example, we have dy by dx plus y equal to 0. This is an ordinary differential equation because it involves the ordinary derivatives of a dependent variable y with respect to an independent variable x. Let us see another equation: dy over dx plus y cos x is equal to sin x. And we can see this equation involves the ordinary derivatives of a dependent variable y with respect to an independent variable x. So this is an ordinary differential equation. Let us see another example. In this example, we have del u over del x is equal to del v over del y. This differential equation involves partial derivatives of dependent variable u and v with respect to independent variable x and y. So this is partial differential equation. Let us see another example: del square u over del x square plus del square v over del y square is equal to 0. We can see this equation involves partial derivatives of u with respect to x and v with respect to y, and this is second order differential equation. So this is a partial differential equation. Order of a differential equation. The order of the highest derivative occurs in the equation is called order of a differential equation. Degree of a differential equation. The greatest power of the highest order derivative occurs in the equation is called degree of a differential equation. Let us see some examples. Now, in this first example, we can see that the highest order derivative is d square y over dx square. So its order is 2. Order of this differential equation is 2. And the power of the highest order derivative that appears in the equation is called its degree. So we can see the power of the highest order derivative is 3. So degree of this differential equation is 3. Now look at example number 2. In this example, the highest order derivative is 2. So we can say order of this differential equation is 2. And power of the highest order derivative in this equation is 1. So its degree is 1. Now look at example number 3. Before to find order and degree of this differential equation, we have to finish this fraction. Let us square both sides. So after squaring both sides, we get 1 plus dy over dx whole square whole power 3 is equal to d cube y over dx cube whole square. Now we can find degree and order of this differential equation. So order of this differential equation is the highest order derivative. So the highest, this is first order derivative and this is third order derivative. So the highest order of the derivative in this equation is 3. So order of this differential equation is 3. Now degree of this differential equation. So the power of the highest order derivative. So the highest order derivative is d cube y over dx cube and its power is 2. So degree of this differential equation is 2. Linear ordinary differential equation. Let us start from the definition. We say that an ordinary differential equation g of x comma y dy by dx up to nth derivative of y with respect to x equal to 0 is a linear ordinary differential equation. If the function g is linear in x, y, dy by dx up to dny over dx power n. A general linear ordinary differential equation is an equation of the form 1, which is a n of x, nth derivative of y, plus a n minus 1 of x, n minus 1th derivative of y, plus up to a naught of xy minus f of x equal to 0. Now, if the function f of x is 0, then it is known as a homogeneous ODE. And if the function f of x is not equal to 0, then it is called a non-homogeneous ordinary differential equation. Let us see some example. dy over dx plus y is equal to x. This is a linear ordinary differential equation. Here f of x is x. Now the coefficient of dy over dx, it may be a function of x or some constant, let us say 2. Then again this is a linear ordinary differential equation. Let us write another definition. X d square y over dx square plus dy over dx plus 3y is equal to e power x. This is an ordinary differential equation which is linear because the coefficients of all d square y over dx square, dy over dx, similarly y, they are function of x. And f of x in this case is e power x. Now if e power x is 0, this is homogeneous. But now it is a non-homogeneous ODE because we have a function e power x. Similarly, from equation 1, if I write d2 dy over dx plus y equal to 0, now this one is homogeneous, but the star that one is a non-homogeneous because f of x is x in star. Now let us write another equation, dy over dx plus sine x y is equal to cos x. This is a non-homogeneous ODE because f of x in this case is cos x. To classify the linear and non-linear ordinary differential equations, let us see the key points. We will say that an ordinary differential equation is linear if it satisfies three conditions. Number one, the dependent variable y and its derivatives are all of degree 1. Number two, there will be no product of y and or any of its derivatives. Number three, there will be no transcendental function of y and or its derivatives. By transcendental functions, we mean trigonometric functions like sine y, cos y, tangent y, exponential function, e power y, 2 power y, logarithmic function, ln y, and so on. If any one or more than one of these conditions are not satisfied, then the ODE is called a nonlinear ODE. Let us see some examples. In the first example, we have dy over dx plus y square is equal to 2. This is a non-linear ODE because of y square, because the degree of y is 2. Let us see another example. 2 dy by dx plus sine y is equal to e power x. This is a non-linear ODE because of sine y, which is a transcendental function. Number 3, y dy by dx plus y is equal to e power x. This is a non-linear ODE because of the product y and dy over dx. What is solution of an ordinary differential equation? Let us see the definition. A relation between the dependent and independent variables is called a solution if it satisfies the following two conditions. Number one, it does not contain derivatives. Number two, this relation and the derivatives obtained from it satisfy the given ordinary differential equation. Let us explain it by an example. In this example, we have an ordinary differential equation d square y over dx square plus y is equal to 0. Its solution is y is equal to a sine x plus b cos x. Let us say this is 2. If we say that 2 is a solution of ODE 1, it must satisfy the above definition. We can see this is a relation between y and x, and it is free from derivatives. There is no derivative. So condition 1 is satisfied. To show that condition 2 is true, let us differentiate 2 with respect to x. We have dy over dx is equal to A, cos x minus B sin x. Let us differentiate it once again. D square y over dx square is equal to minus A sin x minus B cos x. Let us take minus as common. We have A sin x plus B cos x. Now from 2 we can see that A sin x plus B cos x is equal to y. So therefore we can get d square y over dx square is equal to minus y from 2. Now if we simplify this, we have d square y over dx square plus y is equal to 0. And hence we can see that the relation 2 and the derivatives obtained from it satisfy the given ordinary differential equation. Hence 2 is a solution of ODE1. Later on, we shall learn how to obtain a solution of ordinary differential equation. Initial and boundary conditions. In this course, later on, we shall study different methods to solve ordinary differential equations. We will see that we use integration techniques to solve ODEs, and hence integration constants appear in many places. Due to integration constants, solutions to ordinary differential equations are usually not unique. To get the value of integration constant, we use two types of conditions with ODEs, and they are called initial conditions and boundary conditions. Let us start from the first one. Initial conditions. If the conditions with ordinary differential equations are given at only one value of the independent variable, then those conditions are called initial conditions. We usually write it as y of x naught is equal to y naught. So there is only one value x naught of the independent variable. Let us explain it by some example. In example number 1, we have a problem. Solve the ordinary differential equation dy by dx is equal to 2x such that y of 1 is equal to 4. In this problem, we have a condition. The condition is given at only one value x naught is equal to 1 of the independent variable. So this condition is an initial condition. Let us see another example. In this example, we have a problem. Solve d square y over dx square plus y is equal to 0. Subject to the conditions y of pi by 4 is equal to under root 2 and y dash of pi by 4 is equal to 1 over under root 2. Now we can see that there is only one value of the independent variable. X naught is equal to pi by 4. So these conditions are called initial conditions. Now let us explain what are boundary value conditions. If the conditions with ordinary differential equation are given a two or more than two independent variables, then those conditions are called boundary conditions. We usually write y of x naught is equal to y naught and y of x1 is equal to y1. So we will see that there will be two or more than two values of the independent variable. Let us explain it by some examples. In this example, we have a problem. Solve the ordinary differential equation d square y over dx square plus y is equal to 0 with the given conditions y of 0 is equal to 1 and y of pi by 2 is equal to 2. Now we can see that there are two values of the independent variable. In this case, x naught is equal to 0 and x1 is equal to pi by 2. So this is a boundary value problem and the conditions are boundary conditions. Let us see another example. In this example, we have solve d square y over dx square plus y is equal to 0. Subject to the initial condition or boundary condition, which we will see that which type of conditions are given, y of 0 is equal to 1 and y of pi is equal to 5. Now we can understand that whether they are initial condition or boundary condition, because here the value of x naught is 0 and the value of x1 is pi. So conditions are given at two values of the independent variable. So these are boundary conditions. We shall learn different methods for solutions to some particular type of ordinary differential equations of the first order and first degree, which you can see on the screen. In this video, we shall study the first one. Separable equations. These are the simplest type of equations. Let us see the definition. We say that a differential equation of the form dy over dx is equal to f of x into h of y is called a separable equation or an equation with separable variables. Or this can be defined as an equation whose all functions of x can be transferred towards dx and all functions of y towards dy is called a separable equation. Equation 1 can also be written as dy into 1 over h of y is equal to f of x into dx. And now just integrating both sides, we can get the solution. Let us see an example of the separable equations. We have 1 plus x dy plus y dx is equal to 0. This is a separable equation because we can separate the coefficients. This can be written as 1 over y dy plus 1 over 1 plus x dx is equal to 0. And now just integrating each term, we can get the solution. Let us solve some separable equations. Question number 1. Solve dy by dx is equal to x over y square. To solve this problem, we shall separate the variables. From equation number 1, we have dy is equal to x by y square dx. This implies y square dy is equal to x dx. Now, integrating both sides, we have integration of y square with respect to y and integration of x with respect to x, which gives y cube divided by 3 is equal to x square divided by 2 plus constant of integration c1. Note one thing, that we shall add constant of integration only at one side of the equation. Because if I add c2 on the left hand side and c1 on the right hand side of equation, then again c1 minus c2 is equal to some constant. So better to use only one constant. Now after simplification, we have 2y cube is equal to 3x square plus 6c1. This implies that 2y cube is equal to 3x square plus c, where c is equal to 6c1, and that is the required solution for the given problem. Question number 2. Solve 2x cos y dx minus x square plus 1 sin y dy equal to 0. To solve this problem, the first task is to separate the variable. So we can see there is cos y with dx. We shall divide each term by cos y and will bring it towards dy. Similarly, we can see with the dy, there is x square plus 1. So dividing each term with x square plus 1, we can bring x square plus 1 towards dx. So let us solve equation number 1, which gives 2x divided by x square plus 1 dx minus sin y divided by cos y dy. And now we can integrate each term. So we have integration of 2x divided by x square plus 1 dx. Plus, we write plus in integration of minus sin y divided by cos y dy is equal to 0. Now, after integrating this, we have ln of x square plus 1 plus ln of cos y is equal to ln of c. Here, ln c is a constant of integration. So if all terms are in the log form, we can replace c by ln c. And the formula for integration which we use here is, if there is a function f in the denominator and it has its derivative in the numerator, then integration of this is ln f plus c. Now, after simplification, we have, using the rule of log, we have x square plus 1 into cos y is equal to ln c. We know that log m plus log n is equal to log m into log n. So now cancelling ln from both sides, we have x square plus 1 into cos y is equal to c. And this is the required solution of the given problem. Question number 3. Solve the initial value problem 1 plus 2 y square dy is equal to y cos x dx with the given initial conditions y of 0 is equal to 1. Let us say this is equation number 1 and this one is equation number 2. The first task is to separate variables from 1. So let us simplify equation number 1. We can write 1 plus 2 y square whole divided by y. Dividing both sides by y into dy is equal to cos x dx. After simplification, we get 1 over y plus 2y into dy is equal to cos x dx. Now let us integrate both sides. So we have 1 over y dy plus 2 integration of y dy is equal to cos x dx. Now integration of 1 over y is ln y plus 2 integration of y is y square divided by 2 is equal to integration of cos x. We know that differentiation of sine is cos, so integration of cos is sine. This is sine x plus constant of integration. Now 2 can be cancelled with 2. From here we can get ln y plus y square is equal to sine x plus c. Now we can use the initial conditions. From 2 we have y of 0 is equal to 1, which means at x is equal to 0, the value of y is 1. So putting these values in equation number 3, we have ln 1 plus 1 square is equal to sine 0 plus c. Now ln 1 is 0 plus 1 sine 0 is 0 plus c. From here we can get that c is equal to 1. So using this value of c in 3, therefore 3 becomes ln y plus y square is equal to sine x plus 1, and that is the required solution for the given problem. That's all. Mathematics. In this video, we shall learn about the homogeneous equations. We shall define the homogeneous functions, homogeneous ordinary differential equations, and the method of solutions for ordinary differential equations which are homogeneous. At the end, we shall solve two problems to explain the method. Homogeneous equations. Let us start from the definition of homogeneous functions. A function f of x comma y is called homogeneous of degree n if f of tx comma ty is equal to t power n f of x comma y. Let us explain it by some examples. Example number 1. We have a function f of x comma y is equal to x square plus y square. To show that this function is homogeneous, we shall replace x by tx and y by ty. So equation 1 becomes f of tx comma ty is equal to tx whole square plus ty whole square. If we simplify this, we get t square x square plus t square y square. Now taking t square is common, we have x square plus y square, and we can see from equation number 1 that this is t square f of x comma y. So f of tx comma ty is equal to t square f of x comma y. This implies that f of x comma y is a homogeneous function of degree 2. Let us see another example. In this example, we have a function f of x comma y is equal to x y square plus x square y. Let us, this is equation number 2. To show that 2 is homogeneous, we shall replace x by tx and y by ty. Then 2 becomes f of tx comma ty is equal to tx into ty whole square plus tx square into ty. Now if we simplify this, we get t cube xy square plus t cube x square y. If we take t power cube as a common, we have x y square plus x square y. And now we can see from 2 that this is equal to t cube f of x comma y. So we have f of t x comma ty is equal to t cube f of x comma y. So this implies that 2 is homogeneous of degree 3. Definition of first order homogeneous ordinary differential equations. A first order ordinary differential equation of the form dy by dx is equal to f of x comma y is said to be homogeneous if the function f of x comma y is homogeneous function of any degree. Let us see another definition. If one is written as m of x comma y into dx plus n of x comma y into dy is equal to 0, then it is called homogeneous. If the coefficient of dx, which is m of x comma y, and the coefficient of dy, which is n of x comma y, are homogeneous of the same degree. Let us explain it by some examples. Example 1. We have a differential equation dy by dx. This is equal to xy plus y square. To show that equation 3 is homogeneous, we must show that the function on the right hand side, this one, is homogeneous. So here f of x comma y is equal to xy plus y square. And if I replace x by tx and y by ty and simplify this, we can get that this is equal to t square f of x comma y, which implies that the function f of x comma y is homogeneous of degree 2. Therefore, we can say that 3 is homogeneous of degree 2. Let us see another example for definition number 2. We have a differential equation x cube plus xy square into dx plus x square y plus y cube into dy is equal to 0. To show that this equation is homogeneous, we shall apply the second definition. So here m of x comma y is equal to x cube plus xy square, and n of x comma y is equal to x square y plus y cube. Now we have to show that m is homogeneous. So m of xt comma yt. If we simplify this, we can get t cube m of x comma y. So m is homogeneous of degree 3. Similarly, from n, just replace x by tx and y by ty and simplify this. We can get that this is t cube n of x comma y. So we can see that n is homogeneous of degree 3. Now m and n both are homogeneous of the same degree. Therefore, we can say that equation number 4 is homogeneous of degree 3. Method of solution for homogeneous ordinary differential equations. To solve a homogeneous ODE, we shall follow these steps. In the first step, we shall put y is equal to Vx. And now if we differentiate both sides with respect to x, we have dy by dx is equal to V plus x dv over dx. Now just replacing y by dv over dx and dy by dx by v plus x dv over dx. After this substitution, we shall simplify the given equation. And as a result of simplification, we must get a separable equation. So just separate the variables. And after that, if we integrate both sides of the separable equation, we will get the solution. Let us explain this method by solving some problems. Question number 1. Solve the ordinary differential equation number 1. So we can see that this is a homogeneous ordinary differential equation. Or if we replace x by tx, y by ty, we will see that this is a homogeneous equation of order 3. So to solve equation 1, we shall put y is equal to Vx. And from here, we can obtain the value of dy by dx, which is equal to V plus x dv divided by dx. Therefore, equation 1 implies that V plus x dv by dx is equal to x cube plus Vx whole cube divided by x square Vx plus x Vx whole square. Now, if we simplify this, we get x cube into 1 plus V cube divided by x cube into V plus V square. Now x cube will cancel with x cube. So we have V plus x dv divided by dx is equal to. This can be written as 1 plus V into 1 minus V plus V square. This is formula for a cube plus b cube and divided by V into 1 plus V. Now this 1 plus V will cancel with the other 1 plus V. So we have 1 minus V plus V square divided by V. And now if we simplify this, we get x dv by dx. Just transfer V to other side of the equation. We have 1 minus V plus V square divided by V minus V. Now if we take the LCM, we will get 1 minus V plus V square minus V square and divided by V. So this V square will cancel with this one and we have 1 minus V divided by V. And now we can see that this is a separable equation in x and V. So now just separate the variables. So if I separate the variable, I will have V divided by 1 minus v dv is equal to 1 over x dx. Now divide v by 1 minus v. So after division, we can get that this is minus 1 plus 1 over 1 minus v into dv is equal to 1 over x dx. And now let us integrate both sides. So integrating this side, we have minus 1 dv, and plus we have integration of 1 over 1 minus v dv, which is equal to integration of 1 over x dx. Integration of minus 1 with respect to v is minus v. And now differentiation of 1 minus v is minus 1. So if we multiply with minus here and here, we will get that this is minus log of 1 minus v. And this is equal to ln x plus constant of integration, which we take ln c. Now if we further simplify these two terms by using the rules of logarithm, we have this is ln cx. And now from here we get that this is minus v minus ln of 1 minus v and minus ln cx is equal to 0. Taking minus as common, we have, and replace v by y by x, because we know from here that y is equal to vx, so we can take the value of v from here. We get this is y by x plus log of 1 minus y by x and plus log of cx is equal to 0. Again, we use the logarithmic rule on this one. So we have y by x plus log of cx into taking LCM of 1 minus y by x, simplifying this one, we have x and here we have x minus y is equal to 0. This x will cancel with this one. So we have ln c into x minus y plus y by x is equal to 0. And that is the required solution. Solve the initial value problem number 1 with the given initial conditions y of 1 is equal to 1. To solve this problem, let us write equation number 1 in the form of dy by dx, which is equal to x plus y divided by x. Let us say this is equation number 3. And we can see that it is a homogeneous ordinary differential equation. To solve this homogeneous differential equation, we should put y is equal to vx. And from here, we can obtain the value of dy by dx, which is equal to v plus x dv divided by dx. Therefore, equation 3 implies that v plus x dv divided by dx, this is equal to x. Let us replace y by vx divided by x, taking x as common, and after simplification we can get that this is 1 plus v. And now if we transfer v to other side, we have x dv divided by dx. And now we have 1 plus v minus v, which is equal to 1. And this is now a separable equation. To separate the variable, we can have that this is dx dv is equal to dx. And if we further simplify this, we have dv is equal to 1 over x dx. Now let us integrate both sides. So if we integrate, we have dv is equal to integration of 1 over x dx. By integrating these terms, we have v is equal to log x plus c. And now let us re-put the value of v from equation number 4. In equation number 4, we have v is equal to y by x. So we have y by x is equal to ln x plus c. And that is the required solution, but we have to use the initial condition. Therefore, from 2 we have the initial condition y of 1 is equal to 1, which means that at x is equal to 1, the value of y is 1. So putting these values in equation number 5, we have y is 1 and x is 1. 1 by 1 is equal to log of 1 plus c. Log of 1 is 0. So this implies 1 is equal to 0 plus c, which gives us c is equal to 1. Therefore, putting c is equal to 1 in equation number 5, we have y by x is equal to ln x plus 1. And if I multiply x on both sides, it will give us y is equal to x ln x plus x. And that is the required solution. That's all. Let us learn the type of ordinary differential equations which are not homogeneous, but they can be reduced to homogeneous form. Equations reducible to homogeneous form. There are some particular type of ordinary differential equations which are not homogeneous, but they can be reduced to the homogeneous form. These equations have the form of equation 1. By equation 1, we mean in this equation, there is a constant C1 in the numerator and C2 in the denominator. If we don't have these two constants, the remaining is a homogeneous ordinary differential equation. Now, if we see an equation of this type, that equation can be reduced to the homogeneous form. In this lecture, we shall learn the method for solutions of such type of equations. Let us see some examples of these type of equations. In example number 1, we have a differential equation. dy by dx is equal to 2x plus 3y plus 4 divided by 4x plus 9y minus 1. This equation is not homogeneous, but it is of the form 1, so we can reduce this equation to the homogeneous form. By of the form 1, we mean there is a constant plus 4 like plus C1 and a constant minus 1 like C2. So if we don't have these two constants, the remaining is homogeneous. So this equation is of the form 1. And now let us see another example of such type of equations. Example number 2. In this example, we have a differential equation dy by dx is equal to 7x plus 11y plus 12 divided by 3x plus 4y plus 1. This equation is not homogeneous, but it can be reduced to homogeneous form because it is of the form 1. By of the form 1 we mean there is plus 12 in the numerator and plus 1 in the denominator. If we don't have these two constants, the remaining is homogeneous. So it is of the form 1 and it can be reduced to the homogeneous form. Let us see another example. In example number 3, we have a differential equation dy by dx, which is equal to 11x plus 13y plus 15 divided by 4x plus 7y plus 6. Now this equation is not homogeneous, but it is of the form 1, so we can reduce this equation to the homogeneous form. Method of solutions. To solve such type of equations, we have two cases. Case number 1, if a1 divided by a2 is equal to b1 divided by b2, then we have to put a1x plus b1y is equal to z. And as a result, we shall get a separable equation. Case number 2, if a1 divided by a2 is not equal to b1 divided by b2, then we have to put small x is equal to capital X plus h and small y is equal to capital Y plus k. After these substitutions in 1, we shall get a1x plus b1y plus a1h plus b1k plus c1 divided by a2x plus b2y plus a2h plus b2k plus c2. Then we will put a1h plus b1k plus c1 equal to 0 and a2h plus b2k plus c2 equal to 0 to obtain the value of h and k. And as a result, we will get a homogeneous equation. So for case 1, we have to remember this substitution, and for case number 2, we have to remember these substitutions. Let us solve some questions to explain the method. We can see that equation number 2 is of the form of equation number 1. So 2 is reducible to homogeneous form. Now here a1 is equal to 3 and a2 is equal to 3. So 3 by 3 is equal to 1. Similarly, we can see that b1 is equal to -4 and b2 is equal to -4, which is equal to 1. So we can see that a1 over a2 is equal to b1 over b2. So we can use case number 1 to solve equation number 2. Let us put 3x minus 4y is equal to z. Now we need the value of dy by dx. So let us simplify this equation. So if we simplify this, we can get that this is y is equal to 3 by 4x minus 1 over 4z. Differentiating both sides with respect to x, we have dy by dx is equal to 3 by 4 minus 1 over 4 dz divided by dx. Therefore, equation number 2 becomes, after putting these values, we have 3 by 4 minus 1 by 4 dz over dx is equal to z minus 2 divided by z minus 3. Now let us simplify this equation. 1 over 4 dz divided by dx, which is equal to z minus 2 divided by z minus 3 minus 3 by 4. Now if we take the LCM and simplify this equation, we get z plus 1 divided by 4 into z minus 3. Cancelling 4 from both sides, we have minus dz divided by dx is equal to z plus 1 divided by z minus 3. And now it is a separable equation. So let us separate the variable. So if we separate the variable, we have z minus 3 divided by z plus 1 into dz is equal to minus dx. Now we can integrate both sides, but from the left hand side we can see, we can write this z plus 1 minus 4 divided by z plus 1 dz, which is equal to minus dx. From here we can get 1 minus 4 divided by z plus 1 into dz is equal to minus dx. Now integrating both sides, we have integration of 1 dz minus 4, integration of 1 over z plus 1 dz is equal to minus integration of dx. From this we can get z minus 4 ln of z plus 1, which is equal to minus x plus c1. Now we can re-put the value of z. So z is equal to 3x minus 4y. If we re-put this value, we have 3x minus 4y minus 4 ln of 3x minus 4y plus 1 is equal to, now we can bring minus x to this side, so we have plus x is equal to c1. Now if we further simplify this equation, we have 3x plus x, this is 4x. So we have 4x minus 4y minus 4 ln of 3x minus 4y plus 1 is equal to c1. Dividing each term by 4, we have x minus y minus ln of 3x minus 4y plus 1 is equal to c. where C is equal to C1 by 4. And this is the required solution of the given problem. Question number 2. Solve the ordinary differential equation number 1. We can see that this is an equation reducible to homogeneous form. To solve this differential equation, here a1 divided by a2 is equal to 1 divided by minus 1, which is equal to minus 1. And b1 divided by b2 is equal to 1 divided by 1, which is 1. So we can see that a1 divided by a2 is not equal to b1 divided by b2. So we can use case number 2 here. Now put small x is equal to capital X plus h and small y is equal to capital Y plus k. And from here we can get dx is equal to d capital X and d small y is equal to d capital Y. So equation 1 becomes dy over dx is equal to x plus h plus y plus k minus 1 divided by minus x minus h plus y plus k minus 3. And now we simplify this to get dy over dx is equal to x plus y plus h plus k minus 1 divided by minus x plus y minus h plus k minus 3. Let us say this is equation number 3. Now put h plus k minus 1 is equal to 0 and minus h plus k minus 3 is equal to 0. This is equation 4 and let us say this is equation number 5. Now adding equation 4 and 5, we have 2k minus 4 is equal to 0, which gives k is equal to 2. Now putting k is equal to 2 in equation number 4, we have h plus 2 minus 1 is equal to 0, which gives h is equal to minus 1. Therefore, equation 3 becomes dy over dx is equal to x plus y divided by minus x plus y, which is a homogeneous ordinary differential equation. It is homogeneous ordinary differential equation. And now to solve this homogeneous differential equation, we put y is equal to vx. And from here we get that dy over dx is equal to v plus x dv divided by dx. So putting these values in equation number 6, we get. So let us solve the remaining question. Here I have to just separate the screen for simplicity. And now we get from equation number 6 that v plus x dv divided by dx is equal to x plus vx divided by minus x plus vx. Taking x as common and then simplifying, we have 1 plus v divided by minus 1 plus v. Now taking v from the left hand side to right hand side, we have x dv divided by dx is equal to 1 plus v divided by minus 1 plus v minus v. Let us take its LCM. So its LCM is minus 1 plus v. We have 1 plus v and minus, this is plus v and minus v square. So if we further simplify this, we have 1 plus 2v minus v square divided by v minus 1. Now from here we get dv over dx is equal to, let us take minus as common. We have v square minus 2v minus 1 divided by v minus 1. And now it is variable separable. So it is separable equation, just separating the variables. From here we get that v minus 1 divided by v square minus 2v minus 1 is equal to minus 1 over x dx. And here we have dv. Now just integrating both sides. So if we integrate v minus 1 divided by v square minus 2v minus 1 dv, which is equal to minus integration of 1 over x dx. Now differentiation of this denominator is 2v minus 2. So multiplying and dividing by 1 over 2. And now we have 1 over 2 ln of v square minus 2v minus 1 is equal to minus ln x plus ln of c1. And now let us multiply each side with 2. We have ln of v square minus 2v minus 1 is equal to minus 2 ln x plus 2 ln c1. And now we can take this 2 in the power, which is rule of law. So we have, this implies ln of v square minus 2v minus 1, and now this becomes plus ln x square. This is equal to ln c, taking c equal to c1 square. And now again by using the rule of logarithm, we have log x square into v square minus 2v minus 1 is equal to ln c. Let us cancel ln from both sides. So now we have to separate the screen once again. Let us see what will happen in the next step. Here we have to re-put the value of v now. So we know that y is equal to vx. So v is equal to y by x. So putting this value, we have x square into y square divided by x square minus 2y divided by x minus 1 is equal to c. Multiplying this x square, so we have y square minus 2xy minus x square is equal to c. Now again, re-putting the value of capital Y and the value of capital X. So we know that capital X is equal to X minus H. And we know that H is, let us see the value of it, which is minus 1. So this is X plus 1. Similarly, capital Y, this is equal to small y minus k. And we know that the value of k is 2. So we have y minus 2. Let us put these values in equation number star. So star becomes, we have y minus 2 whole square minus 2 into x plus 1 into y minus 2 and minus x plus 1 whole square is equal to c. And now if we simplify this equation, we get y square minus x square minus 2xy minus 6y plus 2 x plus 3 is equal to c. And this is the required solution of the given problem. That's all. In the previous part of this lecture, we have studied that an equation of the form 1 can be reduced to the homogeneous form. We studied two cases. Now let us solve this example. Here, the first thing which we need is the value of a1 over a2. Now, a1 is 1, a2 is also 1. So, a1 over a2 is 1. And now we need the value of b1 over b2. So, b1 over b2 is 1 over minus 1, which is equal to minus 1. So, we can see that a1 over a2 is not equal to b1 over b2. So we shall use case number 2 here. According to case number 2, we need to substitute small x equal to capital X plus h, and small y is equal to capital Y plus k. Here h and k, they are constants. From here we get dx is equal to d of capital X. And from this one we get d small y is equal to d of capital Y. Now by division, from here we get the value of dy over dx, which is equal to d of capital Y over d of capital X. Plugging these values into, we obtain d capital Y over d capital X is equal to, let us use the value of small x, which is capital X plus h, plus the value of small y, which is y plus k minus 1, whole divided by x plus h minus y plus k plus 1. If we simplify, we get x plus y plus h plus k minus 1 divided by x plus, sorry, this one is minus, this is minus y plus h minus k plus 1. Let us say this is equation number 3. Now we need to put h plus k minus 1 equal to 0, and let us say this is equation number A, and h minus k plus 1 equal to 0, let us say this is equation number B. Now we need to solve A and B to obtain the value of h and k. So let us add these two equations. K will cancel with k, minus 1 will plus 1, and we get 2h is equal to 0, and from here we get h is equal to 0. The next thing, let us put h is equal to 0 in A. So from A we can get the value of k. So k is equal to 1. Now if we use h is equal to 0 and k is equal to 1 in equation number 3, we get dy over dx is equal to x plus y divided by x minus y. And we can see that it is a homogeneous ODE. So let us solve this homogeneous ODE. We put y is equal to vx, and from here we get the value of dy over dx, which is equal to v plus x dv divided by dx. So let us say this is equation number 4. 4 becomes v plus x dv by dx is equal to x plus vx divided by x minus vx. If we further simplify this, we get v plus x dv by dx is equal to, taking x as common, we have 1 plus v, and taking x common from this one, we get 1 minus v. Now x will cancel with x, and let us take v to right hand side. So we have dx over dv divided by dx is equal to 1 plus v divided by 1 minus v minus v. Now we take the LCM. So if we take the LCM is 1 minus v. We have 1 plus v minus v plus v square. Minus v and plus v, they will cancel. So we get x dv over dx. This is equal to 1 plus v square. So let us write it as v square plus 1 divided by 1 minus v. And now we can see that this is a variable separable equation. So let us separate the variable. We have 1 minus v divided by v square plus 1 dv, which is equal to 1 over x dx. And now let us integrate both sides, but from the left hand side we can get 1 over v square plus 1 minus v over v square plus 1. And now we write dv is equal to 1 over x dx. Let us integrate both sides. So we get 1 over v square plus 1 dv minus v over v square plus 1 dv is equal to 1 over x dx. Now from the first term we can see this is integration of tangent inverse v, And from the second term, we divide and multiply it with 2. So we have minus log of v square plus 1, but here we have 1 over 2, is equal to log x plus c. And that is the solution, but we need to reput the value of v now. So reput v is equal to y by x. We obtain tangent inverse of y by x minus 1 over 2 natural log of y square divided by x square plus 1 is equal to natural log of x plus c. Now the given question was in small x and y, but here we have capital X and capital Y. So let us reput the value of capital X. The value of capital X is small x minus h, but h is 0. So we can write x minus 0. So capital X is equal to x. And capital Y is equal to small y minus k. Now let us put the value of k, which is 1. Using these values, we obtain tangent inverse of y minus 1 divided by x minus 1 over 2 natural log of the value of y is y minus 1 whole square divided by the value of x, which is small x, so x square plus 1. This is equal to natural log of the value of capital X is again small x plus c, and that is the required solution. That's all.
Exact differential equations. Let us start from the definition. We say that a differential equation of the form 1 is exact if left hand side of this equation is a total differential of some function. Note that we denote the coefficient of dx by m and the coefficient of dy by n. Let us explain it by some examples. Example number 1. X dy plus y dx is equal to 0. Is it an exact differential equation or not? So we can see that this equation, or the left hand side of this equation, can be written as d of xy is equal to 0. Because if we use the product rule and evaluate this, again we get the left hand side of the given equation. So we can see that the left hand side of this equation is a total differential of the function xy. So this implies that equation 2 is exact. Let us see another example. 2xy dx plus x square dy is equal to 0. Is it an exact differential equation or not? So from here we can write that this is d of x square y is equal to 0. Because again, if I evaluate this by the product rule, I can get the left hand side of equation 3. So we can see that the left hand side of equation 3 is a total differential of x square into y. And this implies that 3 is exact. Criteria for exact differential equation. We say that a differential equation of the form m dx plus n dy is equal to 0 is exact if and only if my is equal to nx, or we can write by my we mean partial differentiation of m with respect to y, and nx mean partial differentiation of n with respect to x. So if we are given a differential equation of this form, we shall partially differentiate m with respect to y and n with respect to x. If these two are equal, we will say that the given equation is an exact differential equation. Let us explain it by some example. Example number 1, in which we have x dy plus y dx is equal to 0. Here the coefficient of dx is m, which is y, and the coefficient of dy, which is n, and here it is x. So let us differentiate m with respect to y, we get 1, and to differentiate n with respect to x, we get 1. So we can see that my is equal to nx, which is equal to 1, and this implies that this equation number 2 is exact differential equation. So throughout this course, we shall use criteria for exact differential equation to determine whether the given differential equation is exact or not. Method of solutions for exact differential equations. If we are given an ordinary differential equation of the form 1, and we prove that it is exact, it means that if we prove that my is equal to nx, then equation 1 can be solved as follows. We shall integrate m with respect to x, but keeping y as constant. Plus we shall integrate only those terms of n which are free from x with respect to dy is equal to c. C is a general constant. Let us explain this method by solving some problems. Question number 1. Solve the ordinary differential equation number 3. So here m is the coefficient of dx, which is 3x square y plus 2. And n is a coefficient of dy, which is x cubed plus y. Let us partially differentiate m with respect to y. So we have 3x squared. And now let us partially differentiate n with respect to x. So we have 3x squared. Now from here we can see that my is equal to nx, which means that the ordinary differential equation number 3 is exact. Now to solve this differential equation, we shall use the procedure given by 2. According to this integral, we can write m is 3x square y plus 2 into dx. But I will write here that y is constant in this integral. Plus, we shall integrate only those terms of n which are free from x. So there is only one term which has no x, and that is y. So I will integrate y with respect to y equal to c. And if I integrate the first term by keeping y as constant, I get 3x cubed divided by 3y plus 2x plus y squared divided by 2 is equal to c. And now if I simplify this, I will get that this is x cubed y plus 2x plus y squared divided by 2 is equal to c, and that is the required solution for this problem. Question number 2. Determine whether the differential equation number 1 is exact or not. If it is exact, solve it. To show that the given equation is exact, here m is the coefficient of dx, which is equal to y cos x plus 2x e power y, and n is equal to sine x plus x square e power y minus 1. Now we have to partially differentiate m with respect to y, which gives cos x plus 2x e power y. And now we have to differentiate n with respect to x. We get cos x plus 2x e power y, and we can see that my is equal to nx. This implies that equation number 1 is exact. Now, to solve this equation number 1, we know the procedure that we shall integrate m with respect to x, keeping y as constant, plus we shall integrate those terms of n which are free from x with respect to y equal to constant. So according to this procedure, let us integrate m, which is cos x plus 2x, it's y cos x plus 2 x e power y into dx, and we shall write y constant, plus let us write those terms of n which are free from x. So there is only one term, which is minus 1, into dy is equal to c. And now let us solve this equation. So y is constant, differentiation of sine is cos, so integration of cos is sine, plus e power y is constant, so we have to write 2x squared divided by 2 e power y, and this is minus y is equal to c. If we further simplify this, we get y sin x plus x square e power y minus y is equal to c, and that is the required solution. Question number 3. Solve the differential equation number 1 with the given initial condition number 2. To solve this differential equation, here m is equal to 2x y minus 3 and n is equal to x square plus 4y. Now let us partially differentiate m with respect to y. We have 2x, and if we partially differentiate n with respect to x, we get 2x. So we can see that my is equal to nx. This implies that equation 1 is exact. Now to solve equation number 1, we use the procedure that integration of m with respect to x, keeping y is constant, plus integration of those terms of n which are free from x, which has no x, dx dy is equal to c. From here we get integration, and the value of m is 2xy minus 3 into dx, keeping y is constant, plus those terms of n which are free from x. So we can see there is only one term of n which is free from x, and that is 4y into dy is equal to c. Now to evaluate this integral, we have 2x square divided by 2y minus 3x plus 4y square divided by 2 is equal to c. If we further simplify this, we get x square y minus 3x plus 2 y square is equal to c. In the next step, we need the value of this general constant c. So we have to use the initial conditions. From 2, we have the initial conditions y of 1 is equal to 2, which means that at x is equal to 1, the value of y is 2. Therefore, putting x is equal to 1 and y is equal to 2 in equation number 3, we have, so x is 1, y is 2, we will get 2 here. Now here x is 1, so we get minus 3 plus 2, and y is 2, 2 2s are 4. So we have 4 here is equal to c, which if we simplify, we get that c is equal to 7. Therefore, equation number 3 becomes, 3 becomes x square y minus 3x plus 2y square, and the value of c is 7. And that is the required solution. That's all.
Assalamu alaikum. Integrating factors. There are differential equations which are not exact, but when we multiply them with some particular type of functions, they become exact. Those functions are called integrating factors. Let us explain it by starting from the previous lecture. If we are given a differential equation of the form m dx plus n dy is equal to 0, and if we partially differentiate m with respect to y and n with respect to x, and they are equal, then we know that equation 1 is called an exact ordinary differential equation. And in that case, the solution of equation 1 can be obtained by integrating m dx, keeping y is constant, plus integration of only those terms of n which are free from x dy is equal to c. Now look at once again. If I have a differential equation m dx plus n dy, the coefficient of dx is called m, and the coefficient of dy is called n. Let us change it by m cap, and I say this is n cap. So the coefficient of dx is called m. In this case, m is equal to m cap and n is equal to n cap. Now if I differentiate m partially with respect to y and n partially with respect to x, and they are not equal, we will say that equation 3 is not exact. Now if we multiply equation 3 with some particular function, let us say f, then I get f m cap dx plus f n cap dy is equal to 0. In this case, m is the coefficient of dx and n is the coefficient of dy. And if I find now that m dy is equal to n dx, in that case we say that 4 is exact ordinary differential equation, and the function f is called an integrating factor. So the main purpose of integrating factor is that it converts a non-exact differential equation into an exact differential equation. In this lecture, we shall study 4 cases or 4 rules to find f. To find integrating factor, let us study rule number 1. Rule number 1 is if my minus nx divided by n is equal to p of x. P of x means it is a function of x only. P is a function of only x. There will be no y. In that case, integrating factor for this differential equation is given by f is equal to e integration of p of x dx. So this is integrating factor for this differential equation. Rule number 2. Rule number 2 is if nx minus my divided by m is equal to q of y. Q of y means it is a function of only y. Q is a function of only y. There will be no x. In that case, integrating factor for this differential equation is given by f is equal to e power integration of q of y dy. That will be the required integrating factor for that differential equation. Question number 1. Solve the differential equation number 1. Here the coefficient of dx is m, which is equal to x square plus x minus y, and the coefficient of dy is n, so n is equal to x. Let us differentiate m with respect to y, we get minus 1, and let us differentiate n with respect to x, we get 1. So we can see that my is not equal to nx, and this implies that 1 is not exact. So we need an integrating factor to convert this differential equation into an exact differential equation. Let us use rule number 1. Rule number 1 is my minus nx divided by n must be equal to a function of x only. So let us put values. My is minus 1 and nx is 1 divided by n, which is x. So this is equal to minus 2 divided by x, and we can see that this is a function of x only. So integrating factor for this problem is f is equal to e power p of x dx. Let us put values. We get e power integration of minus 2 divided by x dx. If we take minus 2 as common outside from integration, we get e power integration of 1 over x is ln x, and here we have minus 2. So this can be written as e power ln x power minus 2. So ln will cancel with e. So integrating factor f is equal to x power minus 2, which can be written as 1 over x square. That is the required integrating factor for equation number 1. Now multiply equation 1 with integrating factor, which is 1 over x square. We get that multiplying x square with 1 over x, we get 1 plus 1 over x and minus y divided by x square into dx plus 1 over x dy is equal to 0. Now equation number 2 will be automatically an exact differential equation. Let us confirm this. Here the coefficient of dx is 1 plus 1 over x minus y divided by x square. So if I differentiate m partially with respect to y, I get minus 1 over x square. And the coefficient of dy is called n, which is 1 over x. So if I partially differentiate n with respect to x, I get minus 1 over x square. And here we can see that my is equal to nx, which implies that equation 2 is an exact ordinary differential equation. So now we can use the formula integration of m dx keeping y is constant plus integration of only those terms of n which are free from x into dy is equal to c. Let us put values in this formula. We get the value of m here is 1 plus 1 over x minus y divided by x square dx. Here y will be considered as a constant, and plus those terms of n which are free from x. So we can see there is no term of n which is free from x. So that term, this is 0, equal to c. Now let us integrate this with respect to x. So we have x plus ln x minus, now y will be considered as a constant. So if I integrate 1 over x square, I will get y over x is equal to c. And that is the required solution for this problem. Question 2. Solve the ordinary differential equation number 1. Here again the coefficient of dx is called m, which is equal to xy square plus y, and the coefficient of dy is called n, which is equal to minus x. Let us differentiate m partially with respect to y. We get 2xy plus 1, and let us differentiate n with respect to x. We get minus 1. Now let us use rule number 2. Rule number 2 is nx minus my divided by m must be equal to a function of only y. So let us put values. We get 2, okay, minus 1 minus 2xy minus 1 divided by m. So m is x y square plus y. Let us simplify this. By simplification here we get minus 2xy minus 2 and divided by x y square plus y. Let us take minus 2 as common. So we have x y minus plus 1 divided by, taking y as common, we have xy plus 1. Now xy plus 1 will cancel, and this is equal to minus 2 divided by y, which is a function of only y. So integrating factor for this problem is f is equal to e power integration of q of y dy, which is equal to e power integration of minus 2 divided by y dy. Taking minus 2 as common and integrating 1 over y, we get e power minus 2 ln y, which can be written as e power ln y power minus 2. Ln will cancel with e, so we get integrating factor which is equal to 1 over y square. That is the integrating factor for problem number 1. Let us multiply 1 with this integrating factor, so it will become an exact differential equation. So we have x plus 1 over y dx minus x divided by y square dy is equal to 0. Now 2 will be automatically an exact differential equation. Let us check that. Here m is the coefficient of dx, which is equal to x plus 1 over y. So if I differentiate m with respect to y partially, I get minus 1 over y square. And here the coefficient of dy is n, which is equal to minus x divided by y square. Let us partially differentiate n with respect to x. We get minus 1 over y square. So we can see that my is equal to nx. And this implies that equation 2 is exact. So now we can use the formula integration of m dx keeping y is constant plus integration of only those terms of n with no x dy is equal to c. Let us put values. So the value of m is x plus 1 over y dx, keeping y is constant, plus those terms of n which are free from x. There is no term of n which is free from x. So this is 0, is equal to c. Let us integrate the first term with respect to x. We have x square divided by 2 plus integration of second term is x divided by y is equal to c. And that is the required solution for this problem. Rule number 3. If the differential equation m dx plus n dy is equal to 0, is homogeneous, and if I multiply m with x plus n with y, and this is not equal to 0, then integrating factor for this problem is given by f is equal to 1 over xm plus yn. That will be the required integrating factor for this problem. To solve question number 3, we can see that equation number 1 is homogeneous because the power of variables in each term is same. So here the coefficient of dx is m, which is equal to x square y minus 2xy square, and the coefficient of dy, that is n, which is equal to minus x cube plus 3x square y. Now let us partially differentiate m with respect to y. We have x square minus 4xy. And now let us partially differentiate n with respect to x. We have minus 3x square plus 6xy. And we can see that my is not equal to nx which implies that equation 1 is not exact. Now let us multiply m with x plus n with y and simplify this. So if I multiply m with x, I get x cube y minus 2x square y square. If I multiply n with y, I get minus x cube y plus 3x square y square. Now these two terms will be cancelled and we get that this is equal to x square y square, which is not equal to 0. So we can see that equation number 1 is homogeneous and xm plus yn is not equal to 0. That is why we can use rule number 3. According to this rule, integrating factor for this problem is given by f is equal to 1 over xm plus yn. Let us put values. We have f is equal to 1 over x square y square, and that is the required integrating factor for this problem. Now let us multiply equation 1 with integrating factor, which is x square y square. This implies that we can get 1 over y minus 2 over x into dx minus x over y square minus 3 over y dy is equal to 0. Now this equation number 2 will be automatically an exact differential equation, but let us confirm this. So again here m is the coefficient of dx, which is 1 over y minus 2 over x, and n is the coefficient of dy, which is minus x over y square plus 3 over y. Let us differentiate m partially with respect to y. We get minus 1 over y square. And now to differentiate n partially with respect to x, we get minus 1 over y square. From these two results, we can see that my is equal to nx. So it confirms that 2 is exact. Now we can use the formula for the solution of this differential equation, that integration of m with respect to x keeping y as constant plus integration of those terms of n which are free from x, dy is equal to c. Let us put values. The value of m, that is 1 over y minus 2 over x dx, keeping y as constant, plus let us put those terms of n which are free from x. So we can see there is only one term with no x. So we can write 3 by y, dy is equal to c. Now if we further simplify this, we get that integration of 1 over y, but 1 over y will be considered as a constant. So we have x over y here. Now integration of 2 over x, taking minus 2 as common, integration of 1 over x is ln x, plus taking 3 as common, and integration of 1 over y with respect to y is ln y is equal to c. And that is the required solution for this problem. Let us study the last rule. If m dx plus n dy is equal to 0 is of the form y f of xy dx plus x g of xy dy is equal to 0, and xm minus y n is not equal to 0. Then integrating factor for this problem is given by f is equal to xm minus yn. That will be the required integrating factor for this problem. To solve question number 4, it is easy to confirm that my is not equal to nx, which means that equation number 1 is not exact. Now we can see that equation number 1 is of the form y f of xy into dx plus x g of xy into dy is equal to 0. So we have to find xm minus yn. Let us multiply m with x and n with y. We get x square y square plus 2x cube y cube minus x square y square plus x cube y cube. If we simplify this, we get 3x cube y cube, and we can see that this is not equal to 0. So equation 1 is of the form 2, and xm minus yn is not equal to 0. Therefore, integrating factor for this problem is f is equal to 1 over xm minus yn, which is equal to 1 over 3x cube y cube. Let us multiply equation 1 with integrating factor. So if I multiply 1 with integrating factor, which is 1 over 3x cube y cube, this implies that we can get 1 over x square y plus 2 over x dx plus 1 over xy square minus 1 over y dy is equal to 0. And now you can easily confirm that the coefficient of dx, which is m, if you differentiate m with respect to y and n with respect to x, n is the coefficient of dy, they must be equal. So we can say that equation number 3 is exact. So we can use the method integrating m with respect to x, keeping y as constant plus integrating those terms of n which are free from x into dy is equal to c. Let us put values in this formula. So we get the value of m here is 1 over x square y plus 2 over x into dx plus, let us find those terms of n which are free from x. So there is only one term which is minus 1 over y dy is equal to c. Now let us integrate this. In the first integral, y will be considered as a constant. So we have, taking 1 over y as common from here, if I take 1 over y as common, so I have x power minus 2. So we have x power minus 2 plus 1 divided by minus 2 plus 1. So we have minus 1 over xy from the first term. Let me write this term once again. There is some confusion. Okay, so let me write that term once again. From the first I have minus 1 over xy. In the second term, taking 2 as common, and integration of 1 over x is ln x. So I can write 2 ln x. Here taking minus as common, and integration of 1 over y with respect to y is ln y is equal to c. And that is the required solution for this problem. That's all. Linear equations. Let us start from the definition. We say that an equation of the form dy by dx plus p of x y is equal to q of x is called linear equation in y. This is linear equation in y. Now here the coefficient of y, which is p of x, and on the right hand side we can see there is another function q of x. So by p of x we mean that there will be a function of x only, and similarly q of x is also a function of x only. Now if we have an equation of this form, then that equation is called a linear equation. Let us see some examples. In the first example, I write an equation dy by dx plus xy is equal to x square. This is an equation of the form 1, and this is called linear. Here p of x is x and q of x is x square. Let me write another example. Dy over dx plus e power x y is equal to sine x. This is an equation of the form 1, and this is called a linear equation. Here p of x is the coefficient of y, which is e power x, and q of x is sine x. Now if we are given an equation of the form 1 which is called linear, how we can solve that equation, how to obtain the solution? Let us see the method of solution. So if we are given an equation of the form 1, you should always remember that integrating factor for that equation must be given by this thing, f is equal to e power p of x dx. P of x, you can see it is the coefficient of y. So the coefficient of y is p of x, and we can obtain integrating factor from here, that f is equal to e power integration of p of x dx. After obtaining the integrating factor, we should multiply equation 1 with that integrating factor. So if I multiply 1 with integrating factor, what I get? Let me multiply that. F into dy by dx plus p of x y and is equal to f q of x. Now remember that in each question, when you simplify the left hand side, it will always be equal to d by dx of two things: integrating factor into the dependent variable, which is y. So if you again differentiate f into y, you will get the above terms. So this is equal to f q of x. Now from here you can see that we can write d of f into y is equal to f q of x dx. Just integrate both sides and you can see from the left hand side, integration will cancel with derivatives and we will get fy is equal to integration of f into q of x dx, and after simplification you will get the solution. Now let us solve a question to see that how we can find the solutions of linear ODEs. So let us write question number 1 here. Question number 1. Question number 1 is solve the ordinary differential equation x minus 1 whole cube dy by dx plus 4 into x minus y whole square y is equal to x plus 1. In the first case, you can see that in the linear differential equation in the standard form, the coefficient of dy over dx is 1. So let us divide each term by x minus 1 whole cube. And we will get that this is equal to dy by dx plus, here I get 4 over x minus 1 y, and here I get x plus 1 divided by x minus 1 whole cube. And now you can see that equation 2 is of the form dy by dx plus p of x y is equal to q of x. So the coefficient of y is p of x. So here p of x is 4 over x minus y. And now I can obtain integrating factor, as we have studied that integrating factor for such type of equation will be f is equal to e power integration of p of x dx. Let us put value of p of x. So if I put value, the value is 4 over x minus 1. I am taking 4 outside of integration. So this is 1 over x minus 1 dx. Let us integrate this. We get e power 4, and this is now ln of x minus 1. If I further simplify this, I will get e power ln of x minus 1 power 4. We use the rule of logarithm. And this is equal to, let us cancel ln with e. So we get x minus 1 whole power 4. In other words, I will say that integrating factor for this equation is x minus 1 whole power 4. Now, in the next step, we have to multiply given equation number 2 with integrating factor. So now I will multiply the given equation with integrating factor. So 2 into integrating factor, which is x minus 1 whole power 4. This implies that. So if I multiply 4 with that, I get x minus 1 whole power 4 into, I get dy by dx plus 4 over x minus 1 into y is equal to, here I will get x plus 1 into x minus 1, because x minus 1 whole power cube will simplify with x minus 1 whole power 4. Okay. Now, as I told you that in each question, the left hand side will always be equal to d by dx of two things, the product of two things. What is the first thing? The first thing is integrating factor. Integrating factor is x minus 1 whole power 4. And the dependent variable, which is y. In each question, you will get that thing. Now, if you differentiate the left hand side, this one, then this is first function, that one is second function. So if you apply the product rule, you will automatically get the above left hand side. And this is now equal to x square minus 1 by using formula a plus b into a minus b. Let us simplify this. We can get d of x minus 1 whole power 4 into y is equal to x square minus 1 dx. Just integrate both sides. So if I integrate both sides, d and integration will cancel from the left hand side, and I get x minus 1 whole power 4 into y is equal to, and now let us integrate the right hand side. So I get x cube divided by 3 minus x plus c, and that is the required solution for this problem. Now let us solve another problem, but before to solve the problem, let me explain one thing more. I will write the definition once again. I say an equation of the form dx over dy plus p of y, x is equal to q of y, is called linear equation in x. The first was linear equation in y, but here you can see the dependent variable is x. So I said this is linear equation in x. Sometime you can find a question in which the dependent variable will be x. So you can see in that case the coefficient of x is p of y. Integrating factor must be equal to f is equal to e power p of y dy, and the remaining procedure is same. So let us solve a question to understand this definition. Question number 2. Solve the ordinary differential equation x plus 2y cube into dy by dx is equal to y. Now, to find the linear form, let us divide both sides by the coefficient of dy by dx. So I will get dy over dx is equal to y over x plus 2y cube. Now you can see it is not possible to obtain an equation which is linear in y from here. So what I do? Let me write the next step. I take the inverse of the left hand side and right hand side. So I write dx over dy. Similarly, from the right hand side I can obtain x plus 2y cube divided by y. If I divide each term by y now, I will get 1 over yx plus 2y square. So if I write it in more simple form, I can write dx over dy minus 1 over y into x is equal to 2y square. And now you can see that this is an equation of the form star. It is linear in x now, you can see it. So what will be integrating factor? F is equal to integration of coefficient of x, which is minus y. Let us take minus as common. So I take 1 over y dy. Let us simplify this. We get minus ln y. If I further simplify, I get ln y power minus 1. From this I can get 1 over y. So integrating factor for this equation is this one, 1 over y. F is equal to 1 over y. So as f is equal to 1 over y, I will multiply. Let me say this is equation number 3. So I will multiply 3 with integrating factor, which is 1 over y, and this implies that 1 over y into d by dy of x minus 1 over y x is equal to, here I will get 2y. And as I told you that in each question, the left hand side must be equal to d by dy. Now this is differentiation with respect to y. So must be equal to d by dy, the product of two things. The first thing is integrating factor, which you obtain. The second thing is the dependent variable. Now, if you apply the product rule and find d over dy of 1 over y into x, you will obtain the above thing. So it is obvious, you can try this. And this is now equal to 2y. So let us simplify this thing. I get d of x over y is equal to 2y dy. Now if I integrate both sides, what we get? D and integration will cancel. Here I will get x over y is equal to, let us take 2 as common. So here I will get y square divided by 2 plus c. 2 will cancel with 2. So what I get now? I get x over y is equal to y square plus c. And that is
the required solution for this problem. Let us start from the definition. We say that an equation of the form dy over dx plus p of x y is equal to q of x into y power n is called a Bernoulli equation. Note that if we don't have this term, which is y power n, then the remaining is just a linear equation, and we can solve this by using the method of the previous lecture, by using integrating factor. But here we have y power n with q of x. So now if n is not 0 or n is not equal to 1, then this is a non-linear ordinary differential equation. Let us see some examples of the Bernoulli equation. The first example is dy by dx plus x square y is equal to x power 5 y power 3. So due to y cube, this is a Bernoulli ordinary differential equation. If we don't have y cube, the remaining is just a linear equation. So let us see another example. Dy by dx plus ln x y is equal to e power x y power 5. Now this is a Bernoulli ordinary differential equation because of this term, which is y power 5. If we don't have y5, then we can see the remaining is a linear ordinary differential equation. Now if we are given a Bernoulli ordinary differential equation, then how we can solve it? So let us see the method of solution. But first of all, note that this equation number 1 is a standard Bernoulli ordinary differential equation. By standard Bernoulli equation, we mean the coefficient of dy by dx is 1. So if we are given a standard Bernoulli equation, or if we reduce it to the standard form, then how to solve them? Let us see the method. The first step is that we shall divide equation 1 with y power n, so that there will be only a function of x on the right hand side of equation 1. So let us say 1 divided by y power n implies that divide each term by y power n. We have y power minus n dy by dx plus p of x y power 1 minus n is equal to q of x. And now we can see that in equation 2, on the right hand side there is a function of x only. Now what we have to do in the next step? In the next step, in each question, we will put the coefficient of p of x equal to some other variable. So let us put y power 1 minus n equal to z and differentiate both sides with respect to x. So we have 1 minus n y power minus n dy by dx is equal to dz over dx. And if I simplify it a little more, I can get y power minus n dy by dx is equal to 1 over 1 minus n dz over dx. So let us put this value in equation number 2, and also we have to put this value in equation number 2. So I will say equation 2 implies that. So we have 1 over 1 minus n dz over dx plus p of x. And we can see y power 1 minus n is equal to z. So replace it by z is equal to q of x. Let us multiply each side with 1 minus n to obtain a standard form of the linear equation. So we have dz over dx plus 1 minus n p of x z is equal to 1 minus n q of x. And now we can see that this is a standard linear differential equation in z, so we can use the method of integrating factor and obtain its solution just like in the previous lecture. To explain the method, let us solve question number 1. We can see that in this question, the given equation number 1 is a Bernoulli ordinary differential equation. Here, p of x is equal to 1 and q of x is equal to x. So the first step is to divide each side of equation 1 by y power 3. So dividing each side by y cube, equation 1 implies that y power minus 3 dy by dx plus y power minus 2 is equal to x, and now this is equation number 2. In the next step, we have to put y power minus 2 equal to some other variable. So we put y power minus 2 is equal to z, and differentiating both sides, we get minus 2 y power minus 3 dy by dx is equal to dz by dx, which can be written as y power minus 3 dy by dx is equal to minus 1 over 2 dz over dx. So putting these values in equation number 2, we have. So 2 implies that minus 1 over 2 dz over dx plus y square is equal to z. So putting z here is equal to x. If we further simplify this by multiplying each side with minus 2, we have dz over dx minus 2z is equal to minus 2x. And now we can see that this is a linear ordinary differential equation in z. So let us find its integrating factor f, which is equal to integration of minus 2 dx. Here p of x is minus 2. So from here we can get that this is e power minus 2x. So multiplying equation 3 with integrating factor, which is e power minus 2x, we have e power minus 2x into dz over dx minus 2z is equal to minus 2x e power minus 2x. And now we know that left hand side will always be equal to d by dx of integrating factor into the dependent variable, which is equal to minus 2x e power minus 2x. In the next step, we have to integrate both sides. So if we integrate both sides, we have e power minus 2x into z is equal to minus 2, and here now we use integration by parts. So we have first function integration of the second function minus integration differentiation of the first function integration of the second function. And if we further simplify this, we have minus 2 will cancel with minus 2. So we have x e power minus 2x. And here minus 2 will cancel with minus 2. So we have minus integration of e power minus 2x dx. Let us further simplify this. We have x e power minus 2x, and integration of e power minus 2x is e power minus 2x divided by minus 2 plus c. And now we can write that this is x e power minus 2x plus 1 over 2 e power minus 2x plus c. Let us further simplify this. So if we further simplify this, we have divide each term by e power minus 2x. So we have z dividing each term by e power minus 2x. We have z is equal to x plus 1 over 2 plus c e power 2x. And now at the end, report the value of z, which is y power minus 2. So we have y power minus 2 is equal to x plus 1 over 2 plus c e power 2x. And if we further simplify this, I can write y power minus 2 is 1 over y square is equal to x plus 1 over 2 plus c e power 2x, and that is the required solution of the given problem. Let us explain another method for the solution of Bernoulli ordinary differential equations. If we are given a standard Bernoulli ordinary differential equation of the form dy by dx plus p of x into y is equal to q of x y power n. In the first step, we have to find its integrating factor. Let us denote integrating factor by f. It is a function of x, so you can also write it as f of x. In some books you can see I or I of x. So integrating factor f must be equal to e power integration of 1 minus n p of x dx. That will be the required integrating factor for each question. Once we obtain the integrating factor, then the solution will be y power 1 minus n. is equal to 1 over integrating factor, which we have already obtained, into integration of 1 minus n q of x into integrating factor dx plus constant of integration. So that is the main formula to obtain the solution for Bernoulli ordinary differential equation. Let us solve question number 1 again by using this method. In question number 1, we have a Bernoulli differential equation dy by dx plus y is equal to x y cube. Now comparing this equation number 2 with equation number 1, we can see that here p of x is equal to 1 and q of x is equal to x. So in the first step, we need integrating factor, which is f is equal to e power integration of 1 minus n. But here we can see that n is 3. So 1 minus 3 into p of x. P of x is 1 dx. So if I simplify, I will get e power minus 2x. Now, in the second step, we have to use formula given as star and get the solution. So from star, we can see we have y power 1 minus n. N is 3 is equal to 1 over integrating factor, which is e power minus 2x into integration of 1 minus n. N is 3 into q of x. Q of x is x into integrating factor, which is e power minus 2x dx plus constant of integration. And now let us simplify this. From the left hand side, we get y power minus 2, which is equal to 1 over e power minus 2x into integration of 1 minus 3. This is minus 2. Let us write minus 2 outside of the integration. And we can see this is first function and this is second function. So we can use integration by parts here. So I will write x e power minus 2x dx plus c. And now let us use integration by parts to obtain the solution. So this is 1 over e power minus 2x into minus 2 into first function integration of the second, e power minus 2x divided by minus 2 minus integration differentiation of the first integration of the second into dx plus constant of integration. Now from here we can further simplify this by multiplying minus 2 inside the brackets. We have 1 over e power minus 2x into minus 2 will cancel with minus 2. So we will get x e power minus 2x. Now minus 2 will cancel again with minus 2. So we get minus integration of e power minus 2x dx plus c. Let us further simplify this. So we have 1 over e power minus 2x into x e power minus 2x minus e power minus 2x divided by minus 2 plus c. If we further simplify this, I can write y power minus 2 as 1 over y square. And this is equal to 1 over e power minus 2x into x e power minus 2x minus minus is plus. So this is 1 over 2 e power minus 2x plus c. And now let us multiply 1 over e power minus 2x with each term. So we get 1 over y square, which is equal to x plus 1 over 2 plus c divided by e power minus 2x. So I can write c into e power 2x. And that is the required solution for the given problem. And we can see that the solution obtained by this method as well as from the previous method is same. So we have the same solution by using any method. That's all. To solve question 2, we can see that equation 1 is a Bernoulli ordinary differential equation with the initial conditions y of 1 is equal to 2. Here P of x is equal to 3 by x and Q of x is equal to x square. N is equal to 2. So let us use method 2 to find its solution. So according to method 2, we need integrating factor f, which is equal to e power integration of 1 minus n p of x dx. So let us put values. We have e power integration of 1 minus n, which is 2, p of x, which is 3 by x into dx. If we simplify it a little more, we have e power minus 3 integration of 1 over x dx. So integration of 1 over x is ln x. F is equal to e power minus 3 ln x, which can be written as e power ln x power minus 3. Ln will cancel with e. So we have x power minus 3. And now let us write the solution. So the solution is y power 1 minus n is equal to 1 over integrating factor into integration of 1 minus n q of x into f of x, which is integrating factor, dx plus c. Let us put values in this formula. We have 1 over x power minus 3 into integration of 1 minus n, which is 2, q of x. Q of x is x square. F is x power minus 3 into dx plus c. And now let us simplify this. So from the left hand side, we can see here we have y power 1 minus 2. So we have y power minus 1, which is equal to x cube into 1 minus 2 is minus 1. So I write minus here. Integration of here x power minus 3 and x power 2. We have x power minus 1, so I can write this 1 over x dx plus c. And if we further simplify this, we have x cube into minus ln x plus c. Let us say, let me write y power minus 1 is 1 over y. So I will write 1 over y is equal to x cube into minus ln x plus C. Let us say this is equation number 2, and now we have to use the initial conditions y of 1 is equal to 2 to find the value of C. Y of 1 equal to 2 mean at x is equal to 1, the value of y is 2. So putting y is equal to 2, we have 1 over 2 is equal to, putting x is equal to 1 into minus ln 1 is 0 plus C. So from here we get that C is equal to 1 over 2. Therefore equation 2 becomes 1 over y is equal to x cube into, let me write 1 over 2 minus ln x, and that is the required solution. Sometime we can just take reciprocal of both sides and write it as y is equal to 1 over x cube into 1 over 2 minus ln x, and that is the required solution of the given problem. That's all. Now it's the homework to solve question number 2 by using method number 1. So use method number 1 to find the solution of question number 2. If we are given a Bernoulli ordinary differential equation of the form 1, then we should remember 2 steps to find its solution. In step 1, we should use formula A to find its integrating factor. And in step 2, we should use formula B to find its solution. Now let us use this procedure to solve an example. Solve dy by dx plus x over 1 minus x square y is equal to x y power 1 over 2. So here we can see, comparing equation 2 with equation 1, p of x is equal to x divided by 1 minus x square, and q of x is equal to x, and n is equal to 1 over 2. So now let us use step number 1 to find its integrating factor. F is equal to e power integration of 1 minus n is 1 over 2, p of x, which is x divided by 1 minus x square dx. Let us simplify this. So we can write e power 1 minus 1 over 2 is 1 over 2. We can write it here. And now we can write x over 1 minus x square dx. Let us recall a rule from a calculus, that if we are given a function f in the denominator and it has its derivative in the numerator, then its integration is equal to ln f plus c. Using this rule, we can see the differentiation of 1 minus x square is minus 2x. So let us multiply and divide by minus 2. So we can obtain that this is equal to e power minus 1 over 4 ln of 1 minus x square. Now by the rules of logarithm, we know that it can be written f is equal to e power ln of 1 minus x square whole power minus 1 over 4. Ln will cancel with ln, and this will give us that f is equal to 1 minus x square whole power minus 1 over 4, and that is the required integrating factor. Now let us use step 2, formula number B, to find its solution. Formula B is
y power 1 minus n, n is 1 over 2. This is equal to 1 over f. F is 1 minus x square whole power minus 1 over 4 into integration of 1 minus n, n is 1 over 2, q of x, q of x is x, and to f, f is 1 minus x square whole power minus 1 over 4 dx plus c. Now let us recall another rule from the calculus. If we are given a function and it has some power n and its derivative f dash is multiplied with that, then its integration is f power n plus 1 divided by n plus 1 plus c. So using this rule, we can find that this is equal to 1 minus x square whole power 1 over 4 into, now we can write that 1 minus 1 over 2 is 1 over 2, and now integration of, let me write this 1 minus x square whole power minus 1 over 4 into x dx plus c. Now differentiation of 1 minus x square is minus 2x. So I should again multiply and divide with minus 2. So we can get that this is 1 minus x square whole power 1 over 4 into 1 over 4 minus 1 over 4, and using that formula we can get 1 minus x square whole power minus 1 over 4 plus 1 divided by minus 1 over 4 plus 1 plus c. Let us simplify this. So after simplification we can see that we can get that this is equal to minus 1 over 4 into 1 minus x square power 3 by 4 divided by 3 by 4 plus c. We can multiply it a little more. Y power 1 minus 1 over 2 is y power 1 over 2, and from here we get just multiplying, but you can just leave it like this one, 1 minus x square whole power 1 over 4, and from here we can get minus 1 over 3, 1 minus x square whole power 3 by 4 plus c. And that is the required solution for the given problem. That's all. In this lecture, we shall study the Riccati ordinary differential equation. Let us revise that a standard linear ordinary differential equation is an equation of this form: dy by dx plus p of x into y equal to q of x. P of x and q of x, they are functions of only x. And let us see what is a Bernoulli ordinary differential equation. It is an equation of this form, and we can see in the linear ODE, we just multiply y power n with q of x, and it becomes a Bernoulli equation. And now let us see what we mean by the Riccati ordinary differential equation. Now we can see with q of x, there is y square. Y square is fixed, 2 is fixed, n is equal to 2, plus r of x. Here again, p, q, and r, they are functions of only x. Generally, we say that the Riccati equation is an equation of the form this one, which is dy by dx is equal to p of xy plus q of x y square
plus r of x. Again, I will repeat p, q, and r. They are functions of only x. Let us see some particular examples of the Riccati equation. Example number 1, dy over dx is equal to x into y plus x cube y square plus x power 4. If we compare this with the general Riccati equation, p of x is x, q of x is x cube, r of x is x4. We can see p, q, and r, they are functions of only x. So this is a Riccati ordinary differential equation. Let us see example number 2. Here p of x is e power x, q of x is x, r of x is sine x, and again we can see p, q, and r. They are functions of only x. So this is a Riccati ordinary differential equation. Now, if we are given a Riccati ordinary differential equation, then how we can solve that equation? So let us see the method of solution. Step number 1, for a Riccati ordinary differential equation, one particular solution, let us say y1, must be given in the question, or it must be known. If it is not given, by guessing we shall find one particular solution. So let us say y1 is given. Then we can go to step number 2. In step number 2, we shall substitute y is equal to v plus y1 in the given question. And we shall simplify the given question. So it will automatically be reduced to the Bernoulli ordinary differential equation. And then we know how to solve a Bernoulli ordinary differential equation. Let us solve example number 1. We are given a particular solution, y1 is equal to 1 over x. So we shall substitute a general solution. Y is equal to v plus y1, but y1 is given, so we can write y is equal to v plus 1 over x. Let us say this is equation number 2. Now from this we need the value of dy by dx. So let us differentiate both sides. We have dy by dx is equal to v dash minus 1 over x square. So substituting these values in 1, we obtain. So 1 becomes v dash minus 1 over x square. This is equal to minus 1 over x, and y is equal to v plus 1 over x plus y square. So y is v plus 1 over x whole square minus 1 over x square. And we can see minus 1 over x square will cancel with minus 1 over x square. So we have v dash is equal to minus 1 over x v minus 1 over x square plus v square plus 1 over x square plus 2 v into 1 over x. And now we can see minus 1 over x square and plus 1 over x square, they will cancel. And from the remaining, now let us simplify this. So we have v dash is equal to, this is v and this one is also v. So let us simplify these two. From these two we can get 1 over x into v plus v square. And now we can see that this is a Bernoulli ordinary differential equation in V, let us write it in a proper way. dV over dx minus 1 over x V is equal to V square. So we can see that this is the Bernoulli equation. Now to solve the Bernoulli equation, we divide each side by V square. So from this we can obtain V power minus 2 dV by dx minus 1 over x V power minus 1 is equal to 1. And now we can plugging in V power minus 1 is equal to z. And if we differentiate this, we can obtain minus V power minus 2 dV over dx is equal to dz over dx. From this we can get V power minus 2 dV over dx is equal to minus dz over dx. Let us substitute these values in equation number 3. So 3 becomes minus dz over dx minus 1 over x into z is equal to 1. Let us multiply both sides with minus 1. So we have dz over dx plus 1 over x z is equal to minus 1. And we can see that it is a linear ODE, linear ordinary differential equation. So to solve a linear ordinary differential equation, we find its integrating factor, which is equal to e power integration of p of x dx. And p of x here is 1 over x. So we have e power ln x. And if we further simplify this, ln will cancel with e. So f is equal to x. So now we can multiply equation number 4 with integrating factor, which is x, and we have x into dz over dx plus 1 over x z is equal to minus x. So we know that left hand side must be equal to d by dx of the integrating factor into the dependent variable. So now let us integrate both sides. So if we integrate both sides, we have d of x into z is equal to minus x dx. So if we integrate both sides, we have xz is equal to minus x square by 2 plus, let us say, c dash. Multiplying both sides with, dividing both sides with x, we have z is equal to minus x over 2 plus c dash over x. Let us take the LCM. The LCM is 2x. So here we have minus x square, and here we have plus 2c dash. Now let us re-put the value of z. So z was equal to v power minus 1. So re-put the value of z. So we have v power minus 1 is equal to 2c dash plus minus, sorry, this is minus x square divided by 2x. Let us take reciprocal of both sides. So this will become v, and this will become 2x divided by 2c dash. Let us denote this by c, minus x square. We denote 2c dash by c. And now finally you can see that we have the value of v. So let us put this value in 2. So 2 implies 2 is y is equal to v. V is 2x divided by c minus x square plus 1 over x, and that is the required solution. Let us solve example number 2. We proceed as usual by substituting the general solution y is equal to v plus y1. But y1 is given, so we can write v plus the value of y1, which is x square. Let us say this is equation number 2. From this we obtain the value of y dash by differentiating both sides. So this is equal to v dash plus 2x. Using these values in the given question number 2, we have v dash plus 2x plus 1 over x, the value of y, which is v plus x square, minus 1 over x cube into the value of y, which is v plus x square whole square, and this is equal to 2x. 2x will cancel with 2x, and let us further simplify this. So we have v dash plus 1 over x v plus x minus 1 over x cube v square plus x4 plus 2x square v equal to 0. And if we further simplify this, we have v dash plus 1 over x v plus x minus 1 over x cube v square minus x minus 2 over x v equal to 0. And we can see minus x and plus x, they will cancel. Now 1 over x and minus 2 over xv. Let us simplify these two terms. So we have v dash, from them we can obtain minus 1 over xv and minus 1 over x cube v square equal to 0. Let us write it in a proper way. So we have v dash minus 1 over xv is equal to 1 over x cube v square, and we can see that this is Bernoulli ordinary differential equation. So to solve a Bernoulli ordinary differential equation, we divide both sides by v square. So we have v power minus 2 into v dash. So let us write v dash as dv over dx minus 1 over x, and this will become v power minus 1 is equal to 1 over x cube. Now let us put v power minus 1 is equal to z. And from this, if we differentiate, we get minus v power minus 2 dv over dx is equal to dz over dx. And from this, we can obtain v power minus 2 dv over dx. This is equal to minus dz over dx. So the above equation, let us say this is 3. This becomes minus dz over dx minus 1 over x z
is equal to 1 over x cube. Let us multiply both sides with minus 1. So we have dz over dx plus 1 over xz is equal to minus 1 over x cube. And we can see that it is a linear ordinary differential equation. To solve a linear ordinary differential equation, we find integrating factor, which is equal to e power p of x dx. But p of x here is 1 over x. So from this we can get e power ln x, which can give us x. Ln will cancel with e. So now let us multiply equation 4 with integrating factor, which is x. So this becomes x into the given question, which is dz over dx plus 1 over x z is equal to minus 1 over x square. And now we know that the left hand side must be equal to d by dx of the integrating factor into the dependent variable. In the next step, let us integrate both sides. D of x into z is equal to x power minus 2. We can write this x power minus 2 into dx, and let us integrate it. So we have xz is equal to minus x power minus 2 plus 1 divided by minus 2 plus 1 plus c. So from this we can get z is equal to 1 over x square plus c over x. Let us take the LCM. The LCM is x square. So we have 1 plus cx. Now let us reput the value of z. So z is equal to v power minus 1. So v power minus 1 is 1 over v. So we have 1 over v is equal to 1 plus cx divided by x square. And from this we can get the value of v, which is equal to x square divided by 1 plus cx. Let us put this value of v in equation number 2, which is the general solution. So we have y is equal to v. V is x square divided by 1 plus cx and plus x square. And that is the required general solution of the given question. That's all. In this lecture, we shall study linear higher order ordinary differential equations. Let us see an example of the first order ODE, which we have studied in the previous classes, which is an equation of the form dy by dx plus 3y is equal to e power x. We can see that the highest order derivative in this equation is 1. That is why this is called first order ordinary differential equation. Now let us see another example. 2d square y over dx square plus 4 dy over d plus 7y is equal to e power x. The highest order derivative in this equation is 2. So this is called second order ordinary differential equation. And now let us see another example. 4 d cube y over dx cube plus 7 d square y over dx square plus 2 dy over dx x plus 3y is equal to sine x. Now we can see that the highest order derivative in this equation is 3. So this is called third order ordinary differential equation. So an equation whose order is greater than or equal to 2 is called higher order ordinary differential equation. So in this lecture, we shall study higher order ODEs. Generally, a higher order ordinary differential equation of order n is represented by equation 1. Here the coefficients an minus 1 up to a1 comma a naught, these are constants, or they may be function of x. The function on the right hand side, which is g of x, it may be 0 or function of only x. Now equation 1 can also be written in the form of this one. Just taking y as a common, we get that equation. And now if we represent d by dx is by d square over d x square by d square and up to dn over dx n by dn, then the above equation can be written as a star. So star is just another form of equation 1, which is nth order ordinary differential equation, and that is a linear equation. Now if that function g of x is 0, then that is called homogeneous. And if g of x is not equal to 0, then that equation is called a non-homogeneous. It means that g of x must be equal to some function like e power x, sine x, x square, x, etc. The solution of a higher order ordinary differential equation of the form star contains two parts. One part is called complementary function. We denote this by yc. And the other part is called particular integral. We denote this by yp. Now once we get yc and yp, then the total solution is given by y is equal to yc plus yp. Now how we can obtain yc and yp? So yc can be obtained from the homogeneous part of equation star. So the homogeneous part of that equation is given by a. So once we get a, then its auxiliary equation or characteristic equation is an equation of the form this one, which is a n d power n plus a n minus 1 d power n minus 1 plus up to a 1 d plus a not equal to 0. Once we get that auxiliary equation, then we will factorize this to find the roots d. Obtaining the roots of d, we can get yc, which we will study shortly. Now, to obtain the particular integral yp, we get the non-homogeneous part of star. From here, we get the value of y. In other words, we keep y on the left-hand side and transfer all other parts to other side of the equation. And we get yp is equal to g of x over f of d. And then we will study different cases to obtain yp. To find the solution of homogeneous higher order ordinary differential equation of the form A, the first step is to find its auxiliary equation of the form B. and then just factorize this to find its roots. So there will be three types of roots. That is why we shall discuss three different cases to find its solution. Case 1 is if the roots are real and distinct. Let us say we have two different roots. The roots are d is equal to a1 comma a2. Then the solution yc of equation A is given by yc is equal to c1 e power a1x plus c2 e power a2x. Now, if we have three different roots, a1, a2, and a3, in that case, the solution yc will be equal to c1 e power a1x plus c2 e power a2x plus c3 e power a3x. And similarly, if we have four roots or five different roots, we will generalize this formula. Now let us see an example to explain case number 1. Solve an ordinary differential equation d square minus 5d plus 6 whole into y equal to 0. This is second order ordinary differential equation, and it is homogeneous because f of x is 0. So the first step is to obtain its auxiliary or characteristic equation, which is d square minus 5d plus 6 equal to 0. Now we have to factorize this equation. So its factorization is d square minus 3d minus 2d plus 6 equal to 0. Taking common, we have d minus 3. From here, we take 2 as common, and we get d minus 3 equal to 0, which implies that d minus 2 into d minus 3 is equal to 0. So from here we get a root d is equal to 2, and from the second one we have a root d is equal to 3. So we actually have two different roots. D is equal to 2 comma 3. So according to case 1, the solution of this equation is given by yc is equal to c1 e power 2x plus c2 e power 3x. Case 2 is if we have real and repeated roots. Let us say we have two roots, d is equal to a1, and again we have the same root a1. They are equal. In that case, the solution yc will be equal to c1 plus c2x e power a1x. And now if we have three equal roots, a1, a1, and again a1, in that case the solution yc will be equal to c1 plus c2x plus c3x squared into e power a1x, and so on. Now let us see an example to explain case number 2. We have an ordinary differential equation d square minus 6d plus 9 whole into y is equal to 0. Solve this ordinary differential equation. The first step is to find its auxiliary equation. Its auxiliary equation is d square minus 6d plus 9 is equal to 0. Let us factorize this. So if we factorize this, we have d square minus 3d minus 3d plus 9 is equal to 0. And from this we have d into d minus 3. Taking minus 3 as common, we have d minus 3 is equal to 0. And we get d minus 3 into d minus 3 is equal to 0. So we have two roots, d is equal to 3, and from the other we also have d is equal to 3. So these are two roots, d is equal to 3 comma 3. That is why the complementary function yc is equal to c1 plus c2x into e power 3x. The last case, case 3, is if the roots are complex numbers. Let us say we have d is equal to a plus minus b iota. In that case, the complementary function yc is equal to e power ax. A is the real part of that complex number into c1 cos bx plus c2 sin bx. B is the imaginary part of that complex number. Let us see an example. In this example, we have a differential equation d square plus 4 into y is equal to 0. Its auxiliary equation is d square plus 4 is equal to 0. If we factorize this, we get d is equal to plus minus 2 iota, plus minus 2 iota, which can be written as 0 plus minus 2 iota. So in this case, a is 0 and b is 2. Therefore, its solution is yc is equal to e power 0x into c1 cos 2x plus c2 sin 2x, which can be written as yc is equal to c1 cos 2x plus c2 sin 2x. In this example, we solve a fourth order homogeneous ordinary differential equation 1. Equation 1 can also be written in the form of d power 4 plus 4d square plus 4 whole into y is equal to 0. Its auxiliary equation is d power 4 plus 4d square plus 4 is equal to 0. Now let us factorize this. So from here we can write that this is equal to d square plus 4 whole square is equal to 0, which can be further simplified is d square plus 4 into d square plus 4 is equal to 0. From here we get the roots that d is equal to plus minus 2 iota. And from the other one we can also get d is equal to plus minus 2 iota. So we have complex roots. The complex roots are 0 plus minus 2 iota, and we have again 0 plus minus 2 iota. So these are complex roots and they are repeated. In other words, they are equal. So we use the conditions, the cases that the solution for this equation is given by yc is equal to e power ax, but a is 0. So we will write 0x into, as they are repeated, we will write c1 plus c2x into cos bx. B is 2 here. So we get 2x plus C3 plus C4x into sine 2x. And that is the required solution, but we can write it as e power 0x is 1. So this can be written as C1 plus C2 x and whole into cos 2x plus C3 plus C4x sine 2x. And that is the required solution for this problem. In this example, we solve the third order ordinary differential equation star, which can be written as d cube plus 3d square plus d minus 5 whole into y is equal to 0. Let's take its auxiliary equation, which is given by d cube plus 3 d square plus d minus 5 equal to 0. And now let us factorize this auxiliary equation. So one root of this equation must be in the divisor of 5. So 1 is divisible by plus minus 1 and plus minus 5. Let us try d is equal to 1. If I put 1 here and also here, I get 1 plus 3 plus 1 minus 5. And we can see that this is 0. So d is equal to 1 is one root of this equation. And now let us use the synthetic division. According to that division, we have to write the coefficient of that equation 1, 3, 1 minus 5. And the root d is equal to 1 should be written here. Now we bring this one as it is. 1 into 1 is 1, we get 4. 4 into 1 is 4, we get 5 by adding 4 and 1. 5 into 1 we get 5. So the last remainder must be equal to 0. So now we can write that the given auxiliary equation d cube plus 3d square plus d minus 5 is equal to d minus 1, which is the first root, and the other equation should be obtained from these numbers. So 1d square plus 4d plus 5. Now to factorize this equation, we know that from the first we have d is equal to 1, and from the next we have d square plus 4d plus 5 equal to 0.
Here we can use the quadratic formula. So if we use the quadratic formula, we get that d is equal to -2 plus minus iota. So all roots are d is equal to 1, which is a real root and distinct, different from other, and we have 2 plus minus iota. So we can find the solution that yc is equal to c1 e power 1x, which is obtained from the real root, plus the remaining is a complex. So here a is 2 and b is 1. So we can write e power 2x into c1 cos 1x plus c2 sin 1x, and that is the required solution for this problem. Let us solve the last example. Equation A can also be written in the form of dq minus 3d plus 2 whole into y equal to 0. The first step is to find its auxiliary equation. Its auxiliary equation is d cube minus 3d plus 2 equal to 0. And now we have to factorize this. So one root of this equation must be in the divisor of 2. So 2 is divisible by plus 1 and minus 1, also by plus 2 and minus 2. Let us try the first one, d is equal to 1. If I put d is equal to 1 in this equation, I get 1 minus 3 plus 2, and this is 0. So d is equal to 1 satisfies this equation, hence this is the first root. Now we use the synthetic division. According to the synthetic division, we have to write the first root here, and now the coefficient of that equation here. The coefficient of d cube is 1. There is no d square, so the coefficient of d square is 0. The coefficient of d is minus 3 and then 2. This 1 will come as it is. Now multiplying 1 with 1, adding 1 with 0. 1 with 1 is again 1. So minus 3 plus 1 is minus 2. Minus 2 into 1 is minus 2. And here we get the remainder as 0. So the given auxiliary equation, d cube minus 3d plus 2 can be written as d minus 1, which is the first root, and the remaining equation can be obtained from these numbers. There will be the coefficient, so 1d square plus d minus 2. And now we have to further factorize this quadratic equation. So if we factorize this equation, we can get d minus 1 into d square plus d minus 2 is equal to 0. From the first we have d is equal to 1, and from the next one we have, if we factorize, we can obtain d minus 1 into d plus 2 equal to 0. And we get two roots from here, d is equal to 1 and d is equal to minus 2. Now we can see that there are three roots, 1, again 1, and minus 2. The first two roots are real, but they are equal. So we can write the complementary function, or its solution is c1 plus c2x e power 1x plus. Now we can see that the third root is real and distinct. So its solution is c3 e power minus 2x, and that is the required solution for this problem. That's all. Let us revise that if we are given a non-homogeneous higher order ordinary differential equation of the form 1, then its general solution y is equal to yc plus yp. Yc is the complementary function, and in the previous lecture we have studied 3 different cases to find the value of yc. Yp is called the particular integral, and its value depends on the value of g of x. It means that for different values of g of x, we have different values of yp. So in this lecture, we shall study different cases to find the value of yp with the method of undetermined coefficients. Let us start from case number 1. If g of x is equal to e power ax, a is any real number, we shall put yp is equal to a e power ax in the given question. And then we shall simplify to obtain the value of a. Once we get the value of a, we shall put the value of a here, and that will be our required solution. If g of x is equal to b e power x, b is any real number. Again, we shall use the same substitution. Yp will be equal to a e power ax. Let us see an example. If g of x is equal to e power 3x, then put yp is equal to a e power 3x. If g of x is equal to 2 e power 3x, use the same substitution. If g of x is equal to 3 e power 3x, 4 e power 3x, 5 e power 3x, in all cases we shall put yp is equal to a e power 3x. Now this note is important. If there is a common term in yc and this yp, then yp should be multiplied with x. In that case, we shall put yp is equal to ax e power x. And if there is again a common term ax e power ax in yc, we shall put yp is equal to ax square e power x, and so on. Let us solve question number 1. Equation 2 can also be written as d square plus 3d plus 2 into y is equal to 24 e power 2x. Now, the first thing is to obtain the value of yc, for which we need the auxiliary equation. So the auxiliary equation is d square plus 3d plus 2 equal to 0. And now if we factorize this, we get d plus 1 into d plus 2 is equal to 0. So we have two distinct roots. D is equal to minus 1 and d is equal to minus 2. So the complementary function yc is c1 e power minus x plus c2 e power minus 2x. Now the next task is to find yp. Now yp, according to case number 1, is equal to a e power 2x. Let us say this is equation number 3. Now we shall substitute the value of y in equation number 2, but from here we obtain the value of y dash, which is equal to 2a e power 2x, and the value of
y double dash, which is equal to 4a e power 2x. So substitution of these values in equation number 2 implies that y double dash is 4a e power 2x plus 3 y dash is 2a e power 2x, and plus 2, the value of y is a e power 2x, which is equal to 24 e power 2x. If we simplify this, we get 4, 3 2s are 6. So this is 10, 10 plus 2 is 12. So we get 12a e power 2x is equal to 24 e power 2x. Let us compare the coefficient of e power 2x on both sides. So by comparing the coefficients, we have 12a is equal to 24. From here we get that a is equal to 2. So we will put a is equal to 2 in equation number 3. So therefore 3 becomes yp is equal to 2 e power 2x. So the general solution of this question is y, which is equal to yc plus yp. Putting values, we have y is equal to yc, which is c1 e power minus x plus c2 e power minus 2x plus yp. The value of yp is 2 e power 2x, and that is the required solution for this problem. Now look at one thing. In the value of yp and in yc, there is no common term. You can see yp is e power 2x. There is no e power 2x in yc. So that is why we don't multiply this with x. Case number 2. If g of x is equal to b sine x or g of x is equal to b cos ax. A and b are any real numbers, they may be equal to 1. In both of these cases, we shall put yp is equal to a cos ax plus b sine ax. For example, if g of x is equal to sine 4x, or 2 sine 4x, or 3 sine 4x, and so on, or g of x is equal to cos 4x, or 2 cos 4x, and so on, we shall put yp is equal to a cos 4x plus b sine 4x. Here I will revise that if there is a common term in yp and yc, we shall multiply yp with x. And if again we can see a common term, we shall multiply with another x, and so on, so that there will be no common term in yp and yc, and then we shall continue our solution. Question 2. To solve equation 1, the first task is to find yc, which is equal to c1 e power minus x plus c2 e power minus 2x. We have obtained this value in question number 1. And according to case number 2, yp is equal to a cos x plus b sin x. And from here, we can get the value of y dash, which is equal to minus a
sin x plus b cos x, and the value of y double dash, which is equal to minus a cos x minus b sin x. And now let us put these values in equation number 1. So we have the value of y double dash, which is minus a cos x minus b sin x, plus 3, the value of y dash, which is minus a sin x plus b cos x, plus 2, the value of y, which is a cos x plus b sin x, and this is equal to 20 sin x. Simplifying this equation, we get a plus 3b cos x plus minus 3a plus b sin x is equal to 20 sin x. Comparing the coefficient of cos x and sin x on both sides, we have a plus 3b is equal to 0 and minus 3a plus b is equal to 20. Now solving these two equations, we get the value of b, which is equal to 2, and the value of a, which is equal to minus 6. Putting these values in equation 2, we get the particular solution, which is equal to minus 6 cos x plus 2 sin x. And now the general solution, y is equal to yc plus yp. Putting values, we have c1 e power minus x plus c2 e power minus 2x minus 6 cos x plus 2 sin x, and that is the required solution of this problem.
Case 3 is for different types of polynomial. If g of x is equal to c, which is a general constant, we shall put yp is equal to a. Let us see this example. If g of x is equal to 1, we will put yp is equal to a. If g of x is 1 over 2, 1 over 3, we shall put yp is equal to a. If g of x is equal to 2 or 3 or 4 and so on, any real number, we shall put yp is equal to a. If g of x is first degree polynomial, it means if g of x is equal to ax or ax plus b, we shall put yp is equal to ax plus capital B. Let us see this example. If g of x is equal to just x, put yp is equal to ax plus b. If g of x is equal to 2x or 3x or 4x plus 2 and so on, just put yp is equal to ax plus b. Second degree polynomial. If g of x is equal to ax square plus bx plus c, or g of x is equal to ax square, we shall put yp is equal to ax square plus bx plus c. Let us see an example. If g of x is equal to x square, use this substitution. If g of x is equal to 3x square,
or 4x square plus 2x plus 3, use yp is equal to ax square plus bx plus c, and so on. And so on mean if g of x is third degree polynomial, it means if g of x is equal to ax cube, we shall just generalize this thing and we will write yp is equal to ax cube plus bx square plus cx plus d, and so on.
Question number 3. To solve equation 1 as usual, we need yc. Yc, the complementary function, is equal to c1 e power minus x plus c2 e power minus 2x, which we know from question number 1. And now we can see that 4x is first degree polynomial. So according to case number 3, yp is equal to ax plus b. Let us say this is equation number 2. From here we get y dash, which is equal to a, and y double dash, which is equal to 0. Putting these values in equation number 1, we get 0 plus 3a plus 2ax plus b is equal to 4x. From here, we can get 3a plus 2b plus 2ax is equal to 4x. Now, comparing the coefficient on both sides. On the left hand side, the constant term is 3a plus 2b. And on the right hand side, we have 0. On the left hand side, the coefficient of x is 2a. And on the right hand side, the coefficient of x is 4. Let us say this is equation number 3 and this one is 4. Now, from 4, we can get the value of a, which is equal to 2. And from 3, we can put a is equal to 2. So we have 6 plus 2b is equal to 0, which gives b is equal to minus 3. Putting these two values in equation number 2, we get the required particular integral, which is equal to 2a minus 3. And now the general solution is y, which is equal to yc plus yp. Putting values, we have y is equal to c1 e power minus x plus c2 e power minus 2x plus 2a minus 3, and that is the required solution for this problem.
Case number 4. If we have the product of polynomial and exponential function, let us see if g of x is equal to first order polynomial into e power alpha x. Alpha is some constant. We shall put yp is equal to ax plus b e power alpha x. So let us see this example. If g of x is equal to x e power 3x, we shall put yp is equal to ax plus b into e power 3x. Or if we have 4x e power 3x or x plus 2 e power 3x, we shall use the same substitution. If g of x is equal to second order polynomial n to e power alpha x,
we shall put yp is equal to a x square plus bx plus c e power alpha x. Let us see this example. If g of x is equal to x square e power 5x, or 3x square e power 5x, or 2x square plus 3x plus 1 e power 5x, we shall put yp is equal to ax square plus bx plus c into e power 5x. So we can see that in all these cases, we are using the case of polynomial. So if there is a third order polynomial, we shall put yp is equal to ax cube plus bx square plus cx plus d into e power alpha x, and so on. Question number 4. To solve equation 1, the first task as usual is to find the complementary function yc, which is equal to c1 e power minus x plus c2 e power minus 2x. Now to find yp, we use case number 4 because the right hand side is a product of first order polynomial and exponential function. Therefore yp is equal to ax plus b into e power 2x. Let us say this is equation number 2. From here we can obtain y dash, which can be obtained by using the product rule. So we get 2ax plus b into e power 2x plus a e power 2x. Differentiating again, we get y double dash, which is equal to 4 into ax plus b into e power 2x plus 2a e power 2x plus 2a e power 2x. And now substituting all these values in equation number 1, we have 4 into ax plus b e power 2x plus 4a e power 2x plus 3 into y dash. Y dash is 2 into ax plus b into e power 2x plus a e power 2x plus 2y, which is ax plus b into e power 2x, and this is equal to 36x e power 2x. Let us simplify this equation. So simplification will give us 12 ax e power 2x plus 7a plus 9b into e power 2x is equal to 36x e power 2x. Comparing the coefficient of x e power 2x and e power 2x, we have
On the left hand side, the coefficient of x e power 2x is 12a. And on the right hand side, the coefficient of x e power 2x is 36. If we simplify this, we get a is equal to 3. Now, comparing the coefficient of e power 2x, on the left hand side, we have 7a plus 9b. On the right hand side, we have 0. Putting a is equal to 3 here, we get 7 into 3 plus 9b equal to 0. This implies that 9b is equal to minus 21. And this gives us that b is equal to 20 minus 21 divided by 9. And we can write 3 3s are 9, 7 3s are 21. And now we have b is equal to minus 7 divided by 3. Therefore, yp becomes, putting values in equation 2, we have a, where a is 3, so we can write 3x plus b. b is minus 7 by 3 into e power 2x. Now the general solution is y is equal to yc plus yp. Putting values, we have y is equal to c1 e power minus x plus c2 e power minus 2x plus 3x minus 7 by 3 into e power 2x, and that is the required solution. Case number 5. If g of x is equal to sine bx e power x or cos bx e power x. In other words, if g of x is the product of sine and exponential function or cos and exponential function, then we shall put yp is equal to e power ax into a cos bx plus b sine bx. And now let us use this case to solve a problem y double dash plus 3y dash plus 2y is equal to 20 e power x into cos x. Let us say this is equation number 1. The complementary function yc is given by yc is equal to c1 e power minus x plus c2 e power minus 2x. And according to case number 5, yp is equal to e power x into a cos x plus b sine x. Let us say this is equation number 2. Yp can also be written as a e power x cos x plus b e power x sine x. And let us differentiate this y dash. We apply the product rule on the first term as well as the product rule on the second term. And after simplification, we get a
plus b into e power x cos x plus minus a plus b e power x sin x. Let us differentiate this once again and obtain y double dash, which is equal to, again we can use the product rule on the first term as well as the product rule on the second term. And after simplification, we get 2b e power x cos x plus minus 2a e power x sin x. Now putting these values in equation 1, we get 2b e power x cos x minus 2a e power x sin x plus 3 y dash. Y dash is a plus b into e power x cos x plus minus a plus b e power x sin x plus 2y, and y is a e power x cos x plus b e power x sin x, which is equal to 20 e power x cos x. Now let us simplify this equation. So after simplification, we get 5a plus 5b into e power x cos x plus minus 5a plus 5b e power x sin x, which is equal to 20 e power x cos x. And now let us compare the coefficient. We have 5a plus 5b, which is equal to 20. This is equation number 3. And the coefficient of e power x sin x on the left hand side is minus 5a plus 5b, and on the right hand side it is 0. Now let us solve these two equations. So if I solve these two equations, I get 10b is equal to 20, and from here we get that b is equal to 2. Putting b is equal to 2 in 4, we have a is equal to 2. So using the value of a and b in equation number 2, we get the value of yp, which is equal to e power x 2 cos x plus 2 sin x. And now the general solution, let us obtain the general solution, which is y is equal to yc plus yp. And this can be written as y is equal to c1 e power minus x plus c2 e power minus 2x plus e power x into 2 cos x plus 2 sin x. And that is the required solution of the given problem. Case number 6. If we have the product of a polynomial with sine function or with cos function, then how to find yp for that problem?
let us see some particular cases. If g of x is equal to x sine bx or x cos bx, we shall put yp is equal to ax plus b cos bx plus cx plus d sine bx. By x here we mean if we have any first degree polynomial, x may be 2x, 3x or 2x plus 1. For any first degree polynomial multiplied with sine bx or with cos bx, we shall use this substitution. Now let us see if g of x is the product of a second degree polynomial, x square sine bx or x square cos bx. Then we shall put yp is equal to a1 x square plus b1 x plus c1 cos bx plus a2 x square plus b2 x plus c2 sin bx. By x square we mean any quadratic equation, any polynomial, just like we can use ax square plus bx plus c. Still we shall use the same substitution and so on. Question number 6. To solve this problem, let us find its auxiliary equation, which is d square minus 1 equal to 0. And if we factorize this, we have two roots, plus 1 and minus 1. So yc for this equation is given by c1 e power x plus c2 e power minus x. Now let us find yp by using case number 6. So according to that case, we have ax plus b cos x plus cx plus d sin x. Let us say this is our equation number 2. Now let us differentiate this. So y dash p is given by minus a x sin x plus c x cos x plus a plus d cos x plus minus b plus c into sin x. And now let us find y double dash from this one. So differentiating once again, and if we simplify, we get minus a x cos x minus c x sin x plus minus 2a minus d into sin x plus minus b plus 2c into cos x. And now let us put all these values in equation number 1. So equation number 1 becomes, we put all values, we have minus a x cos x minus c x sin x plus minus 2a plus d into sin x plus minus b plus 2c into cos x minus y. Let us put the value of y. So y is ax plus b into cos x plus cx plus d into sine x, and this is equal to 2x cos x. If we simplify this equation, we have minus 2a x cos x minus 2c x sine x plus minus 2b plus 2c cos x plus minus 2a minus 2d into sine x, and this is equal to 2x cos x. Now comparing the coefficient, we have, first we compare the coefficient of x cos x on both sides. So we have minus 2a is equal to 2, and from this we get the value of a, which is equal to minus 1. Now we compare the coefficient of x sine x on both sides, and we have minus 2c is equal to 0. This will give us c is equal to 0. And now we compare the coefficient of cos x on both sides. So we have minus 2b plus 2c is equal to 0. But c is 0, therefore we get b is equal to 0. And now we compare the coefficient of sine x on both sides. So we get minus 2a minus 2d is equal to 0. And if we put the value of a, this give us d is equal to 1. So using all these values in 2, we get the particular solution as follows. 2 implies that yp is equal to, the value of a is minus 1, so minus x, b is 0, plus 0 into cos x, plus c is 0, d is 1 into sine x. So we get minus x cos x plus sine x. And now the general solution, y is equal to yc plus yp. Putting values, we have y is equal to c1 e power x plus c2 e power minus x cos x plus sine x. And that is the required solution for this problem. The last case, case number 7. If we have the product of exponential function, polynomial, and sine or cos, then how to solve that problem? Let us see it. If g of x is equal to e power x into x sine bx or e power x into x cos bx, we will put yp is equal to e power x into ax plus b cos bx plus cx plus d sine bx. Here by x we mean any first degree polynomial. So it may be 2x, 3x, 4x, or x plus 1, x plus 2. So if it is any first degree polynomial, we shall use that substitution. And now if g of x is equal to e power ax into x square sine bx or e power ax x square cos bx, in that case we shall put yp is equal to e power x into a1x square plus b1x plus c1 cos bx plus a2x square plus b2x plus c2 sine bx, and so on. By x square we mean second degree polynomial. It may be any quadratic equation. So we shall use that substitution. Let us see an important note. In all cases which we have studied, if we find yc and then we use the substitution of yp, and if we see that there is a common term in yc and yp, we shall multiply yp with x. And if we again see the common term, then multiply with another x. And if we again see a common term, then multiply with another x, so that there will be no common term in yp and yc. Let us explain it by some examples. To explain this note, let us solve question number 7. To solve equation 1, the first task is to find yc, for which we need its auxiliary equation. So its auxiliary equation is d square minus 6d plus 5 equal to 0. And now let us factorize this. So if we factorize, we have d minus 1 into d minus 5 equal to 0. And from here we get two roots. D is equal to 1 and d is equal to 5. So yc is equal to c1 e power x plus c2 e power 5x. And now let us find yp. So the typical yp according to case number 1 for this problem is a e power x. But we can see that a e power x is common with c1 e power x. Just locate the function of x here. We have e power x in yp and we also have e power x in yc. So these are two common terms. So multiply yp with x, which will give us ax e power x. So now this one is our required yp, but the above yp is not correct. So now differentiate this. Y dash p is equal to a x e power x plus a e power x. Let us differentiate it once again. We have ax e power x plus a e power x and plus a e power x. Let us put these values in equation number 1. So we have y double dash, the value of y double dash is a x e power x plus 2a e power x minus 6, the value of y dash, which is equal to a x e power x plus a e power x plus 5 y. The value of y is ax e power x, and this is equal to 8 e power x. And now let us simplify this equation. So if we simplify this equation, we have, from here we have 6ax e power x. This is ax plus e power x and this is 5. So these terms will cancel. So what we have 2a e power x and minus 6a e power x, which is equal to 8 e power x. From here we can get minus 4a e power x is equal to 8 e power x. Now let us compare the coefficient on both sides. On the left hand side, the coefficient of e power x is minus 4a. On the right hand side, the coefficient of e power x is 8. So from here we get that a is equal to minus 2. So putting this value in 2, we get the particular solution. So the particular solution for this problem is yp, which is equal to minus 2x e power x. That is the required particular solution. And now the general solution y is equal to yc plus yp. Putting values, we have yc is c1 e power x plus c2 e power 5x, and yp is minus 2x e power x. That is the required solution for this problem. Now let us explain this notes a little more. In this example, or in this question, we saw that yc was c1 e power x plus c2 e power 5x. That is why the typical yp is equal to a power, yp is equal to a e power x is not a correct yp because these terms are common. So yp was equal to ax e power x. That is the correct yp for this problem. Now here I have to explain a little more. If we have some question in which yc is c1 e power x plus c2 e power 5x plus c3x e power x, then just like in this typical situation, yp will be equal to a e power x. But as this term is common with this one, so we must multiply this with x and we get yp is equal to ax e power x. But again, we can see that this term is now common with this one. So what we have to do? We have to multiply again with x. So we get yp is equal to ax square e power x. So now this yp is wrong, this yp is wrong for the above question. The correct yp is this one, and so on. That's all. I hope this lecture will be helpful. In this lecture, we shall study the method of variation of parameters. Let us explain this method to solve a standard second order ordinary differential equation of the form 1. By standard second order ODE, we mean that the coefficient of d square y over dx square must be equal to 1. To solve a second order ODE of the form 1, we must remember these 3 steps. Step number 1 is we will find CF, the complementary function. That is, yc will be equal to c1 y1 plus c2 y2. After obtaining the value of yc, in step 2, we will assume that its particular integral, pi, is given by yp is equal to u1 y1 plus u2 y2. Now the values of y1 and y2, we have already obtained these two values in step number 1. But now we only need the values of u1 and u2. So to obtain the values of u1 and u2, we must go to step number 3. In step number 3, we should remember these two equations. Equation A is u1 dash y1 plus u2 dash y2 is equal to 0. Equation B is u1 dash y1 dash plus u2 dash y2 dash is equal to g of x. G of x is a function of x which is given on the right hand side of equation 1. Now just putting values in these two equations, we have to solve these two equations for u1 dash and u2 dash. Once we get the value of u1 dash, integrating both sides, we can obtain the value of u1. And when we get the value of u2 dash, integrating both sides, we can get the value of u2. So from these two equations, we can obtain the value of u1 and u2. Once we get these two values, we will put them in equation number 2, and that will be the required particular integral. And at the end, the general solution as usual will be equal to yc plus yp. So putting values in this equation, we get the solution.
Question number 1. In the previous lecture, we have used the method of UC to solve equation 1. And now let us solve equation 1 by using the method of variation of parameters. So the first step is to find the complementary function. Let us write its auxiliary equation, which is given by this thing. And now let us factorize this. So we get d plus 1 into d plus 2 is equal to 0. And here now we get two roots. D is equal to minus 1 and minus 2, from which we can write yc, which is given by c1 e power minus x plus c2 e power minus 2x. And now we have to write yp, but note that here y1 is e power minus x and y2 is e power minus 2x. So let us write yp. Yp is equal to u1 y1 plus u2 y2. If we put values in this equation, we have yp is equal to u1 e power minus x plus u2 e power minus 2x. Let us say this is equation number 2. And now to find the values of u1 and u2, we will solve two equations. u1 dash y1 plus u2 dash y2 is equal to 0. And u1 dash y1 dash plus u2 dash y2 dash is equal to g of x. Let us say this is equation A and this one is equation B. So let us put values in equation number A. So I will say that A implies that u1 dash e power minus x plus u2 dash e power minus 2x is equal to 0. This is equation number 3. And from B, we can get u1 dash y1 dash. Differentiation of e power minus x is e power minus x into minus 1. And minus u2 dash e power minus 2x into 2 is equal to g of x. So g of x is the function on the right hand side of the given equation, which is 4x. This is equation number 4. Now we have to solve 3 and 4 to obtain the values of u1 and u2. So let us add 3 with 4. So we can see the first terms will cancel and we can get minus u2 dash e power minus 2x is equal to 4x. And if we simplify this, we get u2 dash is equal to 4x e power 2x, and minus will come here. Now from here we can get u2 dash mean d by dx of u2, which is equal to minus 4x e power 2x. And from here we can get du2 is equal to minus 4x e power 2x dx. Let us integrate both sides. So we can get from here that u2 is equal to minus 4, and now we shall use integration by parts. So first function integration of the second function, minus integration differentiation of the first, integration of the second. And let us simplify it a little more. So we have u2 is equal to minus 2x e power 2x. Minus minus is plus, so plus 2, and integration of e power 2x is again e power 2x divided by 2. So from here we get that this is equal to u2 is equal to minus 2x e power 2x plus e power 2x. This is the required y2. And now we have to find y1. So to find y1, let us multiply equation 3 with 2 and then add it with 4. So this will give us 2u1 dash e power minus x plus 2u2 dash e power minus 2x is equal to 0. And here we write minus u1 dash e power minus x minus 2u2 dash e power minus 2x is equal to 4x. From here we can see that these two terms will cancel. So we have u1 dash e power minus x is equal to 4x. From this we can get that du1 is equal to 4x e power x. So let us into dx. Let us integrate both sides. Again we use integration by parts. So we have u1 is equal to 4. Now first function integration of the second minus integration differentiation of the first, which is 1, integration of the second, and from this we can get 4x e power x minus 4 e power x, which is the required value of y1 u1. So we can write it here. This is u1. And now we need to put these values in equation 2. So let us put these values. We say that 2 implies. Now 2 becomes yp is equal to u1 we can see this is 4x e power x minus 4 e power x, into e power minus x. And now let us write plus u2. What is u2? We can see from here that the value of u2 is minus 2x e power 2x plus e power 2x into y2 and the value of y2 is e power minus 2x. So now just simplify this. If we simplify, we get yp is equal to 2x minus 3. And if you compare this with the previous lecture, so you can see in the previous video that yp is same, 2x minus 3. So now the general solution as usual is equal to yc plus yp. Let us put values in this equation. Yc is c1 e power minus x plus c2 e power minus 2x plus yp, which is equal to 2x minus 3. That is the required solution. Let us solve question number 2. Its auxiliary equation is d square plus 1 is equal to 0. If we factorize this, we get d is equal to plus minus iota, which can be written as 0 plus minus iota. So the roots are complex number and we can obtain yc, which is equal to e power 0x into c1 cos x plus c2 sin x. And we know that e power 0x is 1. So we have c1 cos x plus c2 sin x. And now here we know that y1 is cos x and y2 is sin x. So this one is y1 and this one is y2. Let us obtain yp, which is equal to u1 y1 plus u2 y2. Let us put the values of y1 and y2. So we have u1 cos x plus u2 sin x. Let us say this is equation number 1. Now to find the values of u1 and u2, we have to solve two equations. u1 dash y1 plus u2 dash y2 is equal to 0. Putting values, we get u1 dash y1, which is cos x, plus u2 dash y2, which is sin x, equal to 0. Let us say this is equation number 2. And we have to solve another equation, which is u1 dash y1 dash plus u2 dash y2 dash is equal to g of x. And this implies that u1 dash y1 dash is minus sin x. Let us put minus here. Plus u2 dash, differentiation of sin is cos x, is equal to g of x. G of x is the function which is on the right hand side of the given equation, cotangent x. Let us say this is equation number 3. Now to find the value of u1 dash and u2 dash from 2 and 3, let us multiply equation 2 with sine and then add it with equation 3 after multiplying 3 with cos x. We get u1 dash sin x cos x plus u2 dash sine x square is equal to 0. Now let us multiply 3 with cos. We have minus u1 dash sine x cos x plus u2 dash cos square x is equal to cos x into cotangent x into cotangent x. Now if we add these two equations, we get these two terms will cancel, and from here we get u2 dash into sine square x plus cos square x is equal to cos x into cotangent. Cotangent is equal to cos x divided by sine x. Now we know that sine square plus cos square is equal to 1. So from this we get u2 dash. So I will write du2 over dx is equal to cos square x divided by sine x. And now from here I can write du2, which is equal to cos square can be written as 1 minus sine square x divided by sine x into dx. Integrating both sides, we get u2, which is equal to integration of 1 over sine is cosecant x and minus sine x into dx. If we integrate this, integration of cosecant is log of cosecant x minus cotangent x, and integration of sine. So integration of sine is minus cos, so we have plus cos x. That is the required value of u2. And now to get the value of u1, we multiply equation 2 with cos x and subtracting equation 3 after multiplying this with sine x. This implies that u1 dash cos square x plus u2 dash sine x cos x is equal to 0. And now from equation 3 we can obtain minus u1 dash sine square x plus u2 dash sine x cos x is equal to, now we multiply with sine, so this is sine x into cotangent x. And now if I subtract this, it will change these signs. So we can see these two terms will cancel and we have u1 dash into cos square x plus sine square x is equal to minus sine x into cos x over sine x. Sine will cancel with sine. So cos square plus sine square is 1. From here we get u1 dash is equal to minus cos x. And now let us integrate both sides. So we have integration of u1. Okay, let me write this like this one. du1 is equal to minus cos x dx. And now let us integrate these equations. So we get from here we get u1, and now differentiation of sine is cos, so integration of cos is sine x. So u1 is equal to sine x. Now we have the value of u1 and u2. So let us put these values in 1 to obtain the required particular integral. Yp is equal to u1. u1 is minus sine x into cos x plus u2. u2 is log of cosecant x minus cotangent x plus cos x into sin x. Now if we simplify this, we can see this term is, if I multiply here, so this term will cancel with this one. So what I get? I get yp is equal to sine x into log of cosecant x minus cotangent x, and that is the required particular integral for this problem. And now we know that the general solution is given by y, which is equal to yc plus yp. Just put values in this equation. We have c1 cos x plus c2 sin x and plus yp, which is sin x into log of cosecant x minus cotangent x. That is the required solution for this problem. Question number 3. Let us write step number 1. So step number 1 is to write the complementary function yc, which is equal to c1 e power minus x plus c2 e power minus 2x. We have obtained this in question number 1. So here y1 is e power minus x and y2 is e power minus 2x. And now let us write step number 2, in which we need yp, which is equal to u1 y1 plus u2 y2. Let us put values of u1 y1 and y2. So yp will be equal to u1 e power minus x plus u2 e power minus 2x. Let us say this is equation number 1. In step 3, we solve two equations, u1 dash y1 plus u2 dash y2 is equal to 0, and u1 dash y1 dash plus u2 dash y2 dash is equal to g of x. Now let us put values in A. So if we put values in A, we get u1 dash e power minus x plus u2 dash e power minus 2x is equal to 0. And now let us put values in B. So we have minus u1 dash e power minus x minus 2 u2 dash e power minus 2x is equal to g of x. G of x is the function which is on the right hand side of the given question. So this is e power x. Let us say this is equation number 3. Now the task is to solve 2 and 3 and find the values of u1 dash and u2 dash, and from that we can obtain u1 and u2. So let us solve 2 and 3. Adding 2 with 3, we can see the first terms will cancel and we can get minus u2 dash e power minus 2x is equal to e power x. And if we simplify this, we get u2 dash can be written as d over dx of u2, which is equal to minus e power x divided by e power minus 2x. And this can be written as minus e power 3x. And now let us further simplify this. We can write du2, which is equal to minus e power 3x dx. Let us integrate both sides of this equation. So from here we can get u2, which is equal to minus e power 3x divided by 3. And that is the required value of u2. Now to find the value of u1, let us multiply equation 2 with 2 and then add this with equation 3. So we have 2 u1 dash e power minus x plus 2 u2 dash e power minus 2x is equal to 0. And from equation 3 we can write minus u1 dash e power minus x minus 2 u2 dash e power minus 2x is equal to e power x. And now if we add these equations, we can see the last two terms will cancel and we can obtain u1 dash e power minus x is equal to e power x. From here we can get u1 dash is equal to e power 2x, and if we integrate this we get u1 is equal to e power 2x divided by 2, and that is the required u1. Now let us put values of u1 and u2 in equation number 1 to find the value of particular integral. So yp is equal to u1. u1 is e power 2x divided by 2 into e power minus x. Now let us put the value of u2. u2 is minus e power 3x divided by 3 into e power minus 2x. Let us simplify this. So we have e power x divided by 2 minus e power x divided by 3. And if we further simplify this, we get yp is equal to e power x divided by 6. And that is the required particular integral. Now to find the general solution, we know that the general solution y is equal to yc plus yp. And now let us put values. So if we put values, we have the value of yc is c1 e power minus x plus c2 e power minus 2x plus e power x divided by 6, and that is the required solution of the given problem. Question number 4. Now this equation can also be written as d square plus 4 into y is equal to 8 secant 2x. Step 1 is to find its complementary function. So for this we need its auxiliary equation, which is d square plus 4 equal to 0. And if we factorize this, we get plus minus 2 iota, which can be written as 0 plus minus 2 iota. So the complementary function yc is equal to e power 0x into c1 cos 2x plus C2 sin 2x. And from here we can get C1 cos 2x plus C2 sin 2x, as e power 0x is 1. Now step number 2 is to write its yp, which is equal to u1 y1 plus u2 y2. And now we know that y1 is cos 2x. So just write its value plus u2 y2. y2 is sin 2x. Let us say this is our equation number 1. Step number 3 is to solve two equations. u1 dash y1 plus u2 dash y2 is equal to 0. And u1 dash y1 dash plus u2 dash y2 dash is equal to g of x. Let us put values in a. So we have u1 dash cos 2x plus u2 dash sin 2x is equal to 0. Let us say this is equation number 2. Now let us put values in b. So we have u1 dash, differentiation of cos 2x is minus sin 2x into 2. Let us write it here. Plus differentiation of sin 2x is cos 2x into 2. Let us write it here, equal to g of x, and g of x is the function on the right hand side of the given question. So this is 8 secant 2x. Let us say this is equation number 3. Now the task is to solve 2 and 3 and get the value of u1 dash and u2 dash, from which we can easily obtain the value of u1 and u2. So let us multiply equation number 2 with sin 2x into 2 and add it with equation number 3. This implies that we have 2 u1 dash sin 2x into cos 2x plus 2 u2 dash sin square 2x is equal to 0. And now let us multiply 3 with, we multiply 3 with cos 2x. So we have minus 2 u1 dash sin 2x into cos 2x plus 2 u2 dash, and this one is now cos square 2x is equal to 8, because 1 secant 2x is cos 2x, and if we multiply it we get 8. Okay, now we can see these two terms will cancel, and from here we get 4 u2 dash, and let me write this here. I can get cos square 2x plus sin square 2x, which is equal to 8. Now we know that cos square 2x plus sin square 2x, this is equal to 1. So what we get? From here we get 4 u2 dash. I can write u2 dash as du2 over dx, which is equal to 8. And now from this we can get that du2 is equal to 2 dx. And if we integrate both sides, we can get u2 which is equal to 2x. That is the required value of u2. Now to find the value of u1, let us solve 2 and 3 again. So now we multiply 2, look at here, we multiply 2 with cos 2x, with 2 into cos 2x, minus we multiply 3 with sine 2x, and this implies that. Let us do that. So we get u1 dash multiplying with cos 2 cos, we get cos square 2x, and plus let us write 2 u2 dash, and now you can see this one is sine, so it will become sine 2x into cos 2x. I will write sine 2x into cos 2x is equal to 0. And now look at equation number 3. If we multiply with sine 2x, we get minus 2 u1 dash sine square 2x. And the next term is plus 2 u2 dash sine 2x into cos 2x is equal to. Now this is 8 into secant 2x. Let us multiply this with sine 2x. So I write here sine 2x. And now let us subtract these things. So this will become plus, this one minus, this one minus. We can see these will cancel. So what we get from here? We get 4 u1 dash. And now we get cos square of 2x plus sine square of 2x, which is equal to minus 8 sine of 2x. Secant can be written as cos of 2x, 1 over cos. And now from here we can get that cos square plus sine square is 1. So what we have? We have u1 dash which is equal to minus 2. 4 2s are 8, so this become minus 2. And now what I get? I get sine 2x divided by cos 2x. Let us integrate both sides. So I get u1 which is equal to differentiation of cos 2x is minus sine 2x. So this will become log of cos 2x. Now we have the values of sine as well as cos. So putting values in 1, we get the required particular integral yp, which is equal to u1. u1 is ln cos 2x into cos 2x plus u2. u2 is 2x into sine 2x. That is the required particular integral for this problem. And now to find the general solution, we know that y is equal to yc plus yp. Let us put values. We have y is equal to c1 cos of 2x plus c2 sine of 2x plus yp. So yp is cos of 2x into log of 2x, log of cos 2x, log of cos 2x plus 2x sine of 2x, and that is the required solution for this problem. That's all.
the Cauchy-Euler equations. They are also called the Cauchy-Euler equation or Euler equations. Let us see the definition. We say that an equation of the form 1 is called the Cauchy-Euler equation. Here the coefficients an minus 1 up to a1 comma a naught are real numbers. And we can see that in each term, the order of derivative and power of the variable is same. That is why these type of equations are also called equidimensional equations. Let us see some examples. In example 1, this is first order Cauchy-Euler equation, and we can see in the first term order of derivative is 1, so power of x is also 1. Look at the second equation. This is second order Cauchy-Euler equation. And here the order of derivative in the first term is 2, so power of variable is also 2. In the second term, order of derivative is 1, so power of x is also 1. Similarly, in the third example, which is third order Cauchy-Euler equation, the order of derivative in the first term is 3, so power of variable which is multiplied with this is also 3. In the second term, order of derivative is 2, so power of variable is also 2. In the third term, order of derivative is 1, so the power of variable is also 1. So these type of equations are called the Cauchy-Euler equations. Method of solution. Let us remember some notations. We shall denote d by dx by capital D, d square by dx square by capital D square, and so on. D by dt is denoted by delta, and we denote d square over dt square by delta square, and so on. If we are given a Cauchy-Euler equation, the first step is that put x is equal to e power t. And from here, we can easily obtain that t is equal to log of x. Now, put xd is equal to delta. X square d square equal to delta into delta minus 1. X cube d cube equal to delta into delta minus 1 into delta minus 2, and so on. If we remember all these notations, we can easily transform the Cauchy-Euler equation to an ordinary differential equation with constant coefficients. And then we can easily solve that equation by using the methods of the previous lectures. Let us prove result number 2, 3, 4, and so on. From equation number star, by differentiating both sides with respect to x, we have dt over dx is equal to 1 over x. And now let us use the chain rule to get the value of dy by dx, which is equal to dy over dt into dt by dx. But we have already obtained the value of dt over dx. So we can write that this is dy over dt into 1 over x. So we have a result dy over dx is equal to 1 over x into dy over dt. Let us say this is result number A. Now from A we can obtain, multiplying both sides with x, that x dy over dx is equal to dy over dt.
Let us use the above notations. So we have x capital dy is equal to delta y. And from this we can easily obtain that xd is equal to delta. And that is the proof of result number 2. Now let us prove result number 3. Again, from equation A, differentiating both sides with respect to x, we have d square y over dx square, which is equal to d over dx of 1 over x into dy by dt. Let us apply the product rule. We write first function differentiation of the second function plus second function differentiation of the first function, which we can further simplify that d square y over dx square is equal to, we can write 1 over x, just replace d by dt and d by dx of y. So we write differentiation of 1 over x is minus 1 over x square dy over dt. And now from equation number A, we have the value of dy by dx. Let us put the value of that term. We have 1 over x into d by dt of 1 over x into dy over dt minus 1 over x square dy over dt. Now from here we can see that d square y over dx square is equal to 1 over x square into d square y over dt square minus 1 over x square dy over dt. Let us multiply x square on both sides. So we have x square d square over dx square of y is equal to d square y over dt square minus dy over dt. And now let us use our notations. So we have x square d square y is equal to delta square y minus delta y. And from this we can see that x square d square is equal to delta into delta minus 1. And that is the required result number 3. Similarly, we can prove result number 4 and so on. To solve question number 1, we can see that the order of derivative and power of the variable x in each term is same. So this is the Cauchy-Euler ordinary differential equation. This equation can also be written as x square d square minus 4xd plus 6 whole into y is equal to 24x power 5. Now let us put x is equal to e power t and xd is equal to delta. X square d square is equal to delta into delta minus 1. So we can obtain delta into delta minus 1 minus 4 delta plus 6. whole into y is equal to 24, and x power 5 can be written as e power 5t. Let us simplify this. So if we simplify, we get delta square minus delta minus 4 delta plus 6 whole into y is equal to 24 e power 5t. If we further simplify this, we can obtain delta square minus 5 delta plus 6 whole into y is equal to 24 e power 5t. Let us say this is our equation number A. And we can see this is an ordinary differential equation with constant coefficients. So we can use the method of UC to obtain YC and YP. To obtain YC, its auxiliary equation is given by this thing. And now let us factorize this. So we have delta square minus 3 delta minus 2 delta plus 6 is equal to 0. Taking delta as common, we have taking minus 2 common from here, and we can get this result. From here we can get delta minus 2 into delta minus 3 is equal to 0. So we have two roots. Delta is equal to 2 and 3. These are two different real roots, so the complementary function yc is equal to c1 e power 2t plus c2 e power 3t. And now let us use the UC method to obtain yp. So yp for this function is a e power 5t. Let us say this is our equation number B. Now let us differentiate this. So we have delta yp, which is equal to 5a e power 5t. And now let us differentiate it again. So we have delta square y, which is equal to 25a e power 5t. Now putting these values in equation A, we can obtain that the value of delta square, that is 25a e power 5t. Now minus 5, the value of delta y, so that is 5a e power 5t plus 6, the value of y, which is a e power 5t, and this is equal to 24 e power 5t. Let us simplify this. 5 5s are 25, so these two terms will cancel. So we have 6a e power 5t is equal to 24 e power 5t. Now let us compare the coefficient of e power 5t on both sides. So we have 6a is equal to 24, and from here we get a is equal to 4. Therefore, from B we can get the particular integral yp is equal to 4 e power 5t. And now the general solution, y is equal to yc plus yp. So let us put values. So we have y is equal to, the value of yc is c1 e power 2t plus c2 e power 3t. The value of yp is 4 e power 5t. Finally, let us replace the value of e power t, which is equal to x. So we have y is equal to c1
e power 2t is now equal to x square plus c2. E power 3t is equal to x cube plus 4. E power 5t is equal to x power 5. And that is the required solution of this problem. Question number 2. As we can see that the order of derivative and power of the variable are same in each term. Like in this term, order of derivative is 1, power of variable is 1. So this is the Cauchy-Euler ordinary differential equation. This equation can also be written in the form x square d square minus 2xd plus 2 whole into y is equal to log x. Now to solve this equation, we will put x is equal to e power t, and from here we can get that log x is equal to t. Similarly, we can put xd equal to delta, and x square d square is equal to delta into delta minus 1. And this equation will become delta into delta minus 1 minus 2 delta plus 2 whole into y is equal to log x is equal to t now. Let us simplify this. We get delta square minus delta minus 2 delta plus 2 whole into y is equal to t. And now if we further simplify this, we have delta square minus 3 delta plus 2 into y is equal to t. And we can see that this is an ordinary differential equation with constant coefficient. So we can solve this by the UC method. Let us find its auxiliary equation, which is delta square minus 3 delta plus 2 is equal to 0. Let us factorize this. Delta square minus 2 delta minus delta plus 2 is equal to 0. Taking delta is common, and from here taking 1 is common, we have this equation. From here we can get delta minus 1 into delta minus 2 is equal to 0. So we have two roots. Delta is equal to 1, comma 2. These are real and distinct roots. So yc, the complementary function, is equal to c1 e power t plus c2 e power 2t. And now let us find yp. So yp, as it is polynomial of order 1, so yp is equal to a plus bt. Let us differentiate this. Delta yp, this is equal to b. Now let us differentiate it again. We have delta square yp, which is equal to 0. Therefore, equation 1 becomes, from equation number 1, now we can also write equation 1 as delta square y minus 3 delta y plus 2 y is equal to t. So let us put values in this equation. Delta square y, that is 0, minus 3 delta y, that is b, plus 2 y,
the value of y is here. So we can put a plus bt is equal to t. And now if we simplify this, we have 2a minus 3b plus 2bt is equal to t. Now let us compare the coefficients on both sides. So on the left hand side, the constants are 2a minus 3b is equal to 0. And on the right hand side, we have 0. In the left hand side, the coefficient of t is 2b. On the right hand side, the coefficient of t is 1. So from here we get b is equal to 1 over 2. And now let us find the value of a from equation star. So we have 2a minus 3. The value of b is 1 over 2. So we write like this one. So it implies that b is equal to 3 by 4. Now let us put these values in 2. So 2 becomes yp is equal to a. Sorry, this one is a. A is 3 by 4 plus b is 1 over 2t. That is the required particular integral. And now the general solution y is equal to yc plus yp. Let us put values. We have c1 e power t plus c2 e power 2t. And the value of yp is 1 over 2t plus 3 by 4. And now let us re-put the values. So re-put x is equal to e power t and t is equal to ln x. So we have y is equal to c1x plus c2x square plus 1 over 2 t is equal to log x and plus 3 by 4. And that is the required solution of the given problem. That's all. In this video, we shall study the Laplace transform. Some of the contents of this lecture are given on the screen. In addition, we shall solve several questions to explain the concepts. Let us see the definition of Laplace transform. The Laplace transform of a function f of t is denoted by capital F of s or L of f of t, and it is defined by this formula. Laplace transform of f of t is equal to integration from 0 to infinity f of t e power minus st dt. So this is the basic formula which we shall use to find Laplace transform of different functions. Let us start from question number 1. Find the Laplace transform of 1, number 2 t, number 3 t square, number 4 t cube. Let us solve question number 1. To solve part number 1, here f of t is equal to 1. So put f of t is equal to 1 in formula number 1. Then formula number 1 implies that Laplace transform of 1 is equal to integration from 0 to infinity 1 n to e power minus st. So we can see that we just put f of t is equal to 1 on both sides of formula number 1. And now we have to just integrate, but this is improper integral. So you can also take limits h approaches to infinity and replace infinity by h, but we are using direct formulas. So integration of e power minus st is e power minus st divided by minus s, and the limits are from 0 to infinity. And now let us take minus 1 over s outside of the bracket. So we can write this 1 over e power st, and let us put the limits which are from 0 to infinity. Now put the above limit. So 1 over infinity, e power infinity is infinity, and minus 1 over e power 0 is 1. So from here we can obtain that this is minus 1 over s into 0 minus 1. And if we simplify this, we get that Laplace transform of 1 is equal to 1 over s. So this is the main formula of Laplace transform of 1. Part number 2 is to find Laplace transform of t. So let us write Laplace transform of f of t, which is the basic formula, equal to integration from 0 to infinity f of t e power minus st dt. And now let us put f of t is equal to t. So we have Laplace transform of t is equal to, integration is from 0 to infinity, tn to e power minus st dt. Let us use integration by parts. So we can have first function integration of the second function. And limits are from 0 to infinity. Minus integration, differentiation of the first function into integration of the second function dt. And now from here we can obtain that Laplace transform of t is equal to, taking minus 1 over s outside of the bracket, and here we have t divided by e power st, and the limits are from 0 to infinity. And this one is now plus 1 over s. Integration is from 0 to infinity e power minus st dt. And now you can see if we put infinity, this is infinity by infinity form. So we can use the L'Hopital rule here. If we use the L'Hopital rule, we can get 0, and now minus. If we put 0, again we have 0. And from here, this is plus 1 over s, and integration of e power minus st is given by this thing. Limits are from 0 to infinity. This is equal to minus 1 over s square. And now let us put limits. So if we put limits, you can write that this is 1 over e power st. The limits are from 0 to infinity. So this can be written as minus 1 over s square into e power infinity is infinity, anything divided by infinity is 0, and e power 0 is 1. So we have from here that Laplace transform of t is equal to 1 over s square. That is the basic formula for the Laplace transform of t. Now let us solve part number 3, in which we have to find the Laplace transform of f of t is equal to t square. So using f of t is equal to t square. In the basic formula, we have integration from 0 to infinity t square e power minus st dt. Again here we shall use integration by parts. So we have first function into integration of the second function, and the limits are from 0 to infinity, minus integration differentiation of the first function, which is 2t, integration of the second function e power minus st divided by minus s dt. And now if we further simplify this by putting the limits, we can see we get 0 minus 0, and minus, let us take 2 over minus s common, so this is plus 2 over s, and here we have 0 to infinity t e power minus st dt, and we can see that this is Laplace transform of t. If we put f of t is equal to t in the basic formula, we can easily get that Laplace transform of t is this thing. But we have already obtained, let me write it here, we have already obtained the Laplace transform of t, which is 1 over s square. So from this we can write 2 factorial divided by s cube. So we can say that Laplace transform of t square is equal to 2 factorial divided by s cube, and that is the required formula for the Laplace transform of t square. Now the fourth part is to find Laplace transform of the function f of t, which is equal to t cube. So let us use t cube in the basic formula. We have Laplace transform of t cube, which is equal to integration from 0 to infinity t cube e power minus st dt. Let us use integration by parts. So we have first function, integration of the second function. The limits are from 0 to infinity, minus integration differentiation of the first, integration of the second into dt. And now if we apply the limits, we can see we will get 0 minus 0. For the first term, this is obtained by using the L'Hopital rule. Minus, taking 3 over minus s common, so we have 3 plus 3 over s, and now we have 0 to infinity t square e power minus st dt, and we can see that this is 3 by s, and the remaining is Laplace transform of t square. If we use t square on both sides in the basic formula, we can easily obtain that Laplace transform of t square is this thing. So this is equal to 3 by s, and Laplace transform of t square we have already obtained, which is 2 factorial divided by s cube. So from this we can write that Laplace transform of t cube is equal to 3 factorial divided by s power 4, and that is the required rule for the Laplace transform of t cube. In a similar procedure, now we can write that Laplace transform of t power 4 must be equal to 4 factorial divided by s power 5. And if we further generalize this, we can write that Laplace transform of t power n is equal to n factorial divided by s power n plus 1. So this is the general rule for the polynomials. Question number 2. To find the Laplace transform of e power at, let us write the basic formula of Laplace transform, which is given by integration from 0 to infinity f of t e power minus st dt. Now put the value of f of t on both sides of this formula. We have Laplace transform of e power at is equal to, integration is from 0 to infinity, e power at n to e power minus st dt. And this can be written as 0 to infinity e power a minus s into t dt. Let us integrate this. We have e power a minus s t divided by a minus s, and the limits are from 0 to infinity. Now, under the conditions that s is greater than a, let us take minus as common. So we have s minus a t divided by a minus s, and the limits are from 0 to infinity. From this we have, taking 1 over a minus s outside of the bracket, we have 1 over e power s minus a into t. Limits are from 0 to infinity. This is equal to 1 over a minus s, and now if I put infinity, I get 0. Minus, if I put 0, I get 1. So we have minus 1 over a minus s. But we know that s is greater than a. So let us write this as s minus a. So from this we have 1 over s minus a. So the Laplace transform of e power at is equal to 1 over s minus a when s is greater than a. And this is the fundamental rule for the Laplace transform of e power at. Question number 3. Find the Laplace transform of cos at and then sin at. Let us solve part number 1. Here f of t is equal to cos at. Let us use the basic formula of Laplace transform, but take f of t equal to cos at. Then it is equal to integration from 0 to infinity cos at into e power minus st dt. Now let us put I equal to integration from 0 to infinity cos at into e power minus st dt. Let us say this is equation number 1, and now we have to use integration by parts. So we can write first function cos at, integration of the second function, and the limits are from 0 to infinity, minus integration, differentiation of the first. This is a sine at, but differentiation of cos is minus sine, so I write it as plus, and e power minus st divided by minus s dt. Now from here we can write that this is cos at divided by e power st, taking minus 1 over s outside of the brackets. The limits are from 0 to infinity. And now taking a over s minus a over s outside of the integration, we have sine at e power minus st dt. Limits are from 0 to infinity. Now again we will apply integration by parts. From the first term you can see we can write minus 1 over s, and now e power infinity is infinity, anything divided by infinity is 0, minus cos 0 is 1, e power 0 is 1, so we have this thing, minus a over s into first function sine at, integration of the second e power minus st divided by minus s. Limits are from 0 to infinity, minus integration 0 to infinity, differentiation of the first. So it is a cos at, integration of the second, and we have dt here. Now let us simplify this. From here we can get 1 over s and minus a over s into, now again if we divide by infinity with 0 and sine 0 is 0, so from this term we get 0. Now minus a over s can be taken as constant outside from the bracket, and we have a divided by s, and this is now 0 to infinity cos at e power minus st dt. From this we can get that I is equal to 1 over s. Let us multiply minus a over s, so we have minus a square divided by s square, and integration is from 0 to infinity cos at into e power minus st dt. But we can see from 1 that this thing is equal to I. So I will write I is equal to 1 over s minus a square divided by s square into I. I will write from 1. From 1 we can see this term is equal to I. Now taking I to the left hand side, we have I minus a square divided by s square, so it will become plus here. I is equal to 1 over s. And now from here let us take I as common and taking LCM. So LCM is s square. So we have s square plus a square. is equal to 1 over s. And from this we can obtain I is equal to 1 over s into s square divided by s square plus a square. Now from this we can get, cancelling 1s with 1, we have I is equal to s over s square plus a square. Now let us put this value. So we have Laplace transform of cos AT is equal to s over s square plus a square, and that is the required solution for this problem. In a similar procedure, if we want to prove that Laplace transform of sin AT, we will write in the basic formula. Integration is from 0 to infinity. Sin AT into cos AT is, sin AT, and now I'm using the basic formula. So this is e power minus st dt. Now represent this by I, and in a similar way like part 1, you can obtain that Laplace transform of sin AT is equal to a divided by s square plus a square. So we should remember these formulas. Let us study two properties of the Laplace transform. The first one is called constant preserving property, which means if a constant a is multiplied with a function f of t, then the Laplace transform of this is equal to a Laplace transform of f of t. The second property is called the linear property, which says that Laplace transform of a f of t plus r minus b g of t is equal to a Laplace transform of f of t plus or minus b Laplace transform of g of t. Here a and b are real constants. And now let us solve question number 4. To solve part 1, here we can write that cos hyperbolic AT is equal to e power AT plus e power minus AT divided by 2. And now let us take Laplace transform of both sides. So we have Laplace transform of cos hyperbolic AT is equal to Laplace transform of e power AT plus e power minus AT divided by 2. And now let us use the linear property, which says take 1 over 2 common and find Laplace transform of e power AT plus Laplace transform of e power minus AT, which we have proved that Laplace transform of e power AT is 1 over s minus a plus Laplace transform of e power minus AT is s plus a. And now let us take LCM. So we have 1 over 2 into the LCM is s square minus a square. and here we have to write s plus a minus, sorry, this is plus s minus a. And now let us simplify. Minus a and plus a, they will cancel. So we have 1 over 2 into 2s divided by s square minus a square. 2 will cancel with 2 and we get that the Laplace transform of cos hyperbolic at is equal to s divided by s square minus a square. So that is the basic formula for the Laplace transform of cos hyperbolic at. To solve part 2 in a similar way, we can write sine hyperbolic at, which is equal to e power at minus e power minus at divided by 2. And in a similar procedure like part 1, we can prove that Laplace transform of sine hyperbolic at is equal to a divided by s square minus a square. So that is the basic rule for the Laplace transform of sine hyperbolic at. Property number 3. This is called the first shift property, which says that if Laplace transform of f of t is equal to capital F of s, then the Laplace transform of e power at into f of t is equal to capital F of s minus a, which means that if we have to find the Laplace transform of e power at into f of t, the first step is to obtain the Laplace transform of f of t, which will be f of s. And now just subtract this a from any s in the solution of Laplace transform of f of t. So we will get f of s minus a. Let us solve question number 5. Find the Laplace transform of e power 2t into t cube and e power 3t cos phi t. To solve part number 1, here f of t is equal to t cube. And now let us find its Laplace transform. So Laplace transform of t cube is equal to 3 factorial divided by s power 4. Now to find the Laplace transform of this product, which is e power 2t into t cube, we have to just subtract 2 from s. So the solution is 3 factorial divided by s minus 2 whole power 4, and that is the required solution of this problem. Let us solve problem number 2, part number 2. Here f of t is equal to cos phi t. And now we know that the Laplace transform of cos phi t is equal to s divided by s square plus phi square, which is 25. Therefore, the Laplace transform of this product, which is e power 3t into cos phi t, this is equal to, just subtract 3 from s. So we can write s minus 3 divided by s minus 3 whole square plus 25, and that is the required solution for this problem. Now let us see the definition of unit step function or Heaviside function. It is a function which is denoted by u of t and is defined by u of t is equal to 0 when t is less than 0 and u of t is equal to 1 when t is greater than 0. Now let us solve question number 6, in which we have to find the Laplace transform of u of t. So by the basic formula of Laplace transform, we can write Laplace transform of f of t is equal to, integration is from 0 to infinity, f of t e power minus st dt. But here f of t is u of t. So let us put the value of u of t. So we have u of t, which is equal to integration from 0 to infinity u of t into e power minus st dt. And now let us put the value of u of t. When t is less than 0, it is 0, but when t is from 0 to infinity, the value of u of t is 1 from the above definition. So we write this thing. And now let us integrate this. So if we integrate this, we have e power minus st divided by minus s. And the limits are from 0 to infinity. Let us take minus 1 over s outside of the bracket. And we can write 1 over e power st, and limits are from 0 to infinity. So we have minus 1 over s, and when we put infinity we get 0, when we put 0 we get 1. So we can see that the Laplace transform of the unit step function is equal to 1 over s. So that is the basic formula for the Laplace transform of u of t. The shift unit function is denoted by u of t minus a with shift a, and is defined by u of t minus a is equal to 0 if t is less than a, and this is 1 when t is greater than a. Question number 7. Find the Laplace transform of u of t minus a. So here f of t is equal to u of t minus a. And now let us write the basic formula for the Laplace transform of f of t, which is equal to integration from 0 to infinity f of t into e power minus st dt. And now if we put the value of f of t, which is u of t minus a, we get that this is equal to 0 to infinity u of t minus a into e power minus st dt. And now we can see that from 0 to a, the value of u of t is 0 into e power minus st dt. And if we take from a to infinity, the value of u of t minus a is 1 e power minus st dt. So this can be written as, the first term is now 0 and the second term is from a to infinity e power minus st dt. Let us integrate this. So we have Laplace transform of u of t minus a is equal to, integration is from e power minus st divided by minus s. This is the integration, and the limits are from it is from a to infinity. Now let us take minus 1 over s outside of the bracket, and we have 1 over e power st. The limits are from 0 to infinity. This is from a to infinity. Now if we put infinity, we get 0. Minus, if we put a, we have e power as. So if we simplify this, we get that Laplace transform of u of t minus a is equal to e power minus as divided by s. So this is the general formula for the Laplace transform of u of t minus a. For example, if we have to find Laplace transform of u of t minus 4, what we will write? So this will be equal to e power minus 4s divided by s. That will be the required solution. Property number 4. This is called the second shift property. It states that if the Laplace transform of a function f of t is equal to capital F of s, and u of t represents a unit step function, then the Laplace transform of f of t minus a into u of t minus a is equal to e power minus a s f of s, where f of s is the Laplace transform of f of t. Now let us solve question number 8. Find the Laplace transform of t minus 3 into u of t minus 3. To solve this problem, here we can see that f of t is equal to t. And if we take the Laplace transform of f of t, which is t, then this is equal to 1 over s square. And now let us find the Laplace transform of t minus 3 into u of t minus 3. So according to the second shift property, this is equal to e power minus 3s into Laplace transform of f of t, which is 1 over s square. So the given solution is e power minus 3s divided by s square. That is the required solution of this question. Property number 5. Let the Laplace transform of f of t is denoted by capital F of s. Then the Laplace transform of t power n f of t is equal to minus 1 power n nth derivative of capital F of s. Now if we put n is equal to 1, we get this result. If we put n is equal to 2, we get this result, and so on. Using this property, let us solve question number 9. Find the Laplace transform of t square sine 2t. Let us say here f of t is equal to sine 2t.
And now if we take Laplace transform of f of t, which is sine 2t, then we know that this is equal to 2 divided by s square plus 2 square, which is 4. So now we can easily find the Laplace transform of the given question, which is t square sine 2t. So according to rule number 5 or property number 5, this formula, we can write minus 1 power 2 d2 over ds square of 2 over s square plus 4. Let us say we can write this minus 1 square is plus 1. So we can write that this is d square over ds square of 2 into s square plus 4 whole power minus 1. And now let us say this is 1. We represent g of s is equal to 2 into s square plus 4. And now let us differentiate this. So g dash of s is equal to minus 2 into s square plus 4 whole power minus 2, and our differentiation is 2s. So we can write that this is minus 4s into s square plus 4 whole power minus 2. Let us differentiate it once again. So g double dash of s is equal to minus 4. And if we differentiate this by using the product rule, we have first function, differentiation of the second function, s square plus 4 whole raised to power minus 3 into 2s plus second function, which is s square plus 4 whole raised to power minus 2. Differentiation of the first function, which is 1. And now let us simplify this. So we can write minus 4. Now 2 2s are is minus 4. So minus 4 s square divided by s square plus 4 raised to the power 3. And this one is now plus 1 over s square plus 4 whole power plus 2. And if we take the LCM, we can write from here, the LCM is s square plus 4 whole cube. So here we can write minus 4 s square, and here we can write plus s square plus s square plus 4. And now let us simplify this. So if we simplify this, we can get minus 4 into minus 3 s square plus 4 divided by s square plus 4 whole cube. And now if we put this value in 1, we get 1 implies that Laplace transform of t square into sine of 2t is equal to minus 4 into minus 3s square plus 4 divided by s square plus 4 whole cube. And that is the required solution of this problem. The differential formulas. Let us see the Laplace transform of f dash of t, f double dash of t, and so on. If we denote the Laplace transform of f of t by capital F of s, then the first formula is Laplace transform of f dash of t is equal to s f of s minus f of 0. The Laplace transform of f double dash of t, that is the second formula, is given by s square f of s minus s f of 0 minus f dash of 0. So we can see that the first two terms are obtained just multiplying these two terms with s and then subtracting f dash of 0. Laplace transform of f triple dash of t. This is the third formula, which is equal to s cube f of s minus s square f of 0 minus s f dash of 0 minus f double dash of 0. So again we can see that the first three terms are obtained just multiplying these three terms with s and then subtracting f double dash of 0. So if we have to obtain the Laplace transform of fourth order derivative of f, then that will be equal to multiplying these terms with s minus f triple dash of 0 and so on. Let us see the proof of the first formula. Here we use the basic formula for the Laplace transform, which is f of t is equal to 0 to infinity f of t e power minus st dt. And now let us obtain Laplace transform of f dash of t. So just replace f of t by f dash in the above formula. We have integration is from 0 to infinity f dash of t e power minus st dt. Now we use integration by parts. So let us say this one is first function and this one is second function. So we obtain first function integration of f dash, which is f of t, and the limits are from 0 to infinity, minus integration from 0 to infinity, differentiation of the first, integration of the second. And now from here we can write f of t divided by e power st. The limits are from 0 to infinity plus s 0 to infinity e power minus st f of t dt. And now if we use the limits, we can see anything divided by infinity is 0. And if we put 0, we have f of 0 divided by 1. So this is f of 0 minus plus s. And now we can see that the second one is formula for Laplace transform of f of t, which we can easily see from 1. So I will write from 1 we have this. And if we just simplify this, we get Laplace transform of f of t is equal to s, and this Laplace transform of f of t is denoted by capital F of s minus f of 0. And this one is the required formula for the given function. Now to prove formula number 2, we use the above result, star. So from star we can obtain Laplace transform of f double dash of t. This is equal to
we can write S Laplace transform of f dash of t minus f dash of 0. And now we can write S, let us put the Laplace transform of f dash of t from star, which is equal to S f of S minus f of 0 minus f dash of 0. So if we simplify this, we get Laplace transform of f double dash of t is equal to s square f of s minus s f of 0 minus f dash of 0, and that is the second formula. In a similar fashion, we can obtain formula number 3 and so on. That's all. Inverse Laplace transform, as it is clear from the name that it is the inverse process of the Laplace transform. If we are given a function f of s, then its inverse Laplace transform is denoted by this symbol. And we say that if the Laplace transform of f of t is f of s, then the inverse Laplace transform of f of s is equal to f of t. Let us see some useful results. We know that the Laplace transform of sine at is a over s square plus a square. So the inverse Laplace transform of a over s square plus a square is now equal to sine at. Similarly, the Laplace transform of cos at is s over s square plus a square. So the inverse Laplace transform of this is equal to cos at. In a similar procedure in the previous lecture, we have proved that the Laplace transform of e power at is 1 over s minus a. So the inverse Laplace transform of 1 over s minus a is equal to e power at. We have proved that the Laplace transform of t power n is n factorial over s power n plus 1. That is why the inverse Laplace transform of n factorial over s power n plus 1 is equal to t power n. And in a similar procedure, we can obtain all these results. And the first property is that it satisfies the linear property. Question number 1. Find the inverse Laplace transform of part number 1 and part number 2. To solve part number 1, we can write inverse Laplace transform of 6 over s square minus 4, which is equal to inverse Laplace transform of 3 into 2 divided by s square plus minus 2 square. Now taking 3 as outside from the inverse Laplace transform, we can write 2 over s square minus 2 square. And now we know that the Laplace transform of sine hyperbolic 2t is equal to 2 divided by s square minus 2 square. So therefore we can write that this is equal to 3 sine hyperbolic 2t, and that is the required solution. Now let us solve part number 2. In part number 2, we have to find the inverse Laplace transform of 3 divided by 2s minus 8. Now this can be written as the inverse Laplace transform of 3 divided by, taking 2 as common, we have s minus 4. Now from here we can take 3 by 2 outside from the inverse Laplace transform, and we can write 1 over s minus 4. Now let us see the property. We know that the Laplace transform of e power a t is equal to 1 over s minus a. Here a is 4. So therefore we can write this is equal to 3 by 2 e power 4 t, and that is the solution. Sometime we need partial fraction to find the inverse Laplace transform of some function. Let us see it in question number 2. To solve this question, first of all, let us factorize s square minus 3s plus 2, which is equal to s square minus 2s minus s plus 2. And this can be written as s into s minus 2 minus 1 into s minus 2, which is equal to s minus 1 into s minus 2. Therefore, the given question is 1 over s square minus 3s plus 2, which is equal to 1 over s minus 1 into s minus 2. And now let us use partial fraction. So this is equal to a over s minus 1 plus b over s minus 2. Let us say this is equation number 1. Now multiplying with LCM, we have 1 is equal to a into s minus 2 plus b into s minus 1. Now if we put s minus 1 equal to 0, which means that s is equal to 1, from the above equation we have 1 is equal to, if I put s is equal to 1 here, I get minus a, and the other term will be 0. So I get the value of a, which is minus 1. And now if we put s minus 2 equal to 0, which is s is equal to 2, we obtain 1 is equal to, the first term will be 0, and from the second term we get the value of b, which is equal to 1. Therefore, equation 1 becomes 1 over s square minus 3s plus 2 is equal to, a is minus 1, so I will write minus 1 over s minus 1 plus b is 1, so I will write 1 over s minus 2. And now let us take the inverse Laplace transform of both sides. So we have 1 over s square minus 3s plus 2, which is equal to, let us take minus outside, L inverse of 1 over s minus 1 plus inverse transform of 1 over s minus 2. Now we know that the Laplace transform of e power at is equal to 1 over s minus a. Using this formula, we have inverse Laplace transform of 1 over s square minus 3s plus 2 is equal to e power t plus, sorry, here will be minus, and now e power 2t. And that is the required solution of this problem. Let us see the use of this important property, which says that Laplace transform of integration from 0 to t f of v dv is equal to f of s divided by s. F of s is the Laplace transform of this function f of t. So the inverse Laplace transform of this property is inverse Laplace transform of f of s over s is equal to integration from 0 to t f of v dv. To solve question number 3, the first method is just use partial fraction and solve this question. But here I will use the mentioned property to solve this problem. Let us see, we know that the Laplace transform of sine hyperbolic 2t is equal to 2 divided by s square minus 2 square, which is 4. And now let us solve the above problem. So we have the inverse Laplace transform of 1 over s into s square minus 4. Now this can be written as just multiply and divide with 2. So we have 2s into s square minus 4. And now let us take its inverse Laplace transform. Now from here we can write that this is equal to 1 over 2 inverse Laplace transform of 2 over, I write it like this one, 2 over s square minus 4 whole divided by s. So you can easily write it like this one. Now here this thing is f of s. This is our f of s. So using the above property we write 1 over 2 integration is from 0 to t and 2 over s square minus 4. This is Laplace transform of sine hyperbolic 2v dv. And now the remaining is just a simple integration. So let us integrate this. Its integration is cos hyperbolic 2v divided by 2, and the limits are from 0 to t. And now let us put the limits. So this can be written as 1 over 4 and cos hyperbolic 2t minus cos hyperbolic 0 is 1. So that is the required solution of this problem. That's all. We shall use the method of Laplace transform to solve ordinary differential equations. Let us revise that we denote the Laplace transform of y of t by y of s. And we have proved in the previous lecture that Laplace transform of y dash of t is equal to s y of s minus y of 0. Laplace transform of y double dash of t is equal to s square y of s minus sy of 0 minus y dash of 0. So the second formula is obtained by just multiplying this with s and then subtracting y dash of 0. Now this formula can be obtained by multiplying this one with s
and at the end we have to subtract y dash of 0. Similarly, Laplace transform of fourth order derivative is obtained by multiplying this one with s and finally subtracting y triple dash of 0 and so on. So we shall use these formulas to solve ODEs with the help of Laplace transform. Question number 1. We use the method of Laplace transform to solve this problem. So we can write this equation is y dash of t minus 2y of t is equal to e power 2t. And now let us take Laplace transform of both sides. So Laplace transform of y dash of t minus 2 Laplace transform of y of t is equal to Laplace transform of e power 2t. So the first step is to take Laplace transform of each term. And now let us use the formulas of Laplace transform. So we know that Laplace transform of y dash is equal to s y of s minus y of 0 minus 2 Laplace transform of y is y of s, which is equal to Laplace transform of e power 2t. This is equal to s minus 2. And now let us use the initial value, and we know that y of 0 is equal to 0. So we can write s y of s minus 0 minus 2 y of s is equal to 1 over s minus 2. Taking y of s as common, we have s minus 2 into y of s, which is equal to 1 over s minus 2. Now keep y of s on one side and transfer all other term to the other side. So we have 1 over s minus 2 whole square. Now the last step is to take inverse Laplace transform. So L inverse of y of s, that is equal to L inverse of 1 over s minus 2 whole square. Now here we know that Laplace transform, since we know that Laplace transform of t is equal to 1 over s square. And we also know that Laplace transform of e power a t into t can be written as 1 over s minus a whole square. And here a is 2. So therefore we can write from the left hand side, we get y of t, which is equal to, from the right hand side we can get that this is equal to t e power 2t, and that is the required solution of. Now let us solve question number 1 with another method. We can see that this is a linear equation, and here p of t is minus 2. So finding integrating factor, we know that integrating factor is e power integration of p of t dt, but p of t in this case is minus 2. So we can write that this is equal to minus e power minus 2t. Now let us multiply our equation number 1. This is equation number 1. So multiply 1 with integrating factor, we obtain e power minus 2t into dy over dt minus 2y is equal to 1. E power 2t into e power minus 2t is 1. And now, according to the previous lectures, we know that it is d by dt of the integrating factor into the dependent variable. This one is 1. From this we can write d of e power minus 2t into y is equal to 1 dt. Let us integrate both sides. So we can obtain that this is e power minus 2t into y is equal to t plus constant of integration. And we know that the initial conditions are y of 0 is equal to 0, which means that at t is equal to 0, the value of y is 0. If we put these values in star, we can get that c is equal to 0. Therefore, from star we can obtain e power minus 2t into y is equal to t, and this can be written as y is equal to t into e power 2t, and this is the required solution. And you can see from both methods we get the same solution. Question number 2. As usual, we shall take Laplace transform on both sides of this equation. So let us start its solution. Taking Laplace transform of y double dash of t minus Laplace transform of y of t is equal to Laplace transform of 1. And now let us use the formulas. Laplace transform of y double dash is equal to s square capital Y of s minus s y of 0 minus y dash of 0, and minus Laplace transform of y is y of s. Laplace transform of 1 is 1 over s. And now let us use the initial conditions. According to the initial conditions, y of 0 is 0, y dash of 0 is 0. So we have s square minus y of s is equal to 1 over s, because y of 0 is 0 and y dash of 0 is also equal to 0. This is, sorry, let me write it again. This is s square y of s. Now let us take y of s as common. So we have s square minus 1 into y of s. This is equal to 1 over s. And if we further simplify this, we have y of s is equal to 1 over s into s square minus 1. If I further simplify this, I can write y of s is equal to 1 over s into s minus 1 into s plus 1. And now by partial fraction, we can write that this is a over s plus b over s minus 1 plus c over s plus 1.
Let us say this is our equation number star. And now just multiply with LCM. We have 1 is equal to A. Actually, what we do here we write 1 over S into S minus 1 into S plus 1 is equal to A over S plus B over S minus 1 plus C over S plus 1. And now let us multiply with LCM. So we have 1 is equal to A into S minus 1 into S plus 1 plus B S into S plus 1 plus C S into S minus 1. And now let us put S minus 1 equal to 0, which gives S is equal to 1. So we have on the left hand side, we have 1. The first term will be 0 and the last term will be 0. So if we put 1, we get 2b. And from this we can get b is equal to 1 over 2. This is the first value. Okay, now let us put S plus 1 equal to 0, which gives S is equal to minus 1. So you can see the first term will be 0 and the second will be 0. And in the third, if we use S minus 1, again we have 1 is equal to 2C, which gives C is equal to 1 over 2. This is another value of the constant. And now let us put the other value, which is S equal to 0. So we can see the last two term will be 0, and from the first term we get minus A, which gives that A is equal to minus 1. Because if I put S is equal to 0 in the first term, I get minus 1 into A. And therefore, now we can write star. Let us write star. So star becomes y of S is equal to A. A is minus 1 over S plus B. B is 1 over 2 over S minus 1 plus C. C is 1 over 2 over S plus 1. And now let us apply the last step, in which we take inverse Laplace transform of each term. So let us take L inverse of 1 over S plus taking 1 over 2 outside, L inverse of 1 over S minus 1, and taking 1 over 2 outside, taking L inverse of 1 over S plus 1. So from this we obtain that this is y of t, and L inverse of 1 over S is 1 plus 1 over 2, this is e power t, plus 1 over 2, this is e power minus t. And that is the required solution of this problem. To solve question 3, we shall use formula number 1, 2, and 4. Now let us use the definition of u of t minus a to write this equation in the form y double dash minus y is equal to u of t minus 3. And now, as usual, we are taking Laplace transform of each term. So Laplace transform of y double dash minus Laplace transform of y. This is equal to Laplace transform of u of t minus 3. And this implies that using formulas of Laplace transform, we can write s square y of s
minus sy of 0 minus y dash of 0, and minus y of s is equal to, using formula number 1, we can write this is e power minus 3s divided by s. And now let us use the initial conditions. Y of 0 is equal to 1, y dash of 0 is equal to 0. These conditions are given. So we obtain s square y of s minus s minus 0 minus y of s is equal to e power minus 3s divided by s. Taking y of s as common, we have s square minus 1 y of s, and transferring minus s to right hand side, we have s plus e power minus 3s divided by s. Let us divide both sides by s square minus 1. We have y of s is equal to s divided by s square minus 1 plus e power minus 3s divided by s into s square minus 1. Now it can be written as y of s is equal to s divided by s square minus 1 plus e power minus 3s. Let us write it as into 1 over s, and this is equal to s minus 1 into s plus 1. Let us say this is our equation number 1. Now we use partial fraction here. So we write 1 over s into s minus 1 into s plus 1 equal to a divided by s plus b divided by s minus 1 plus c divided by s plus 1. But in question number 2, we have obtained that the value of a is minus 1 over s, the value of b is 1 over 2 over s minus 1, the value of c is 1 over 2 over s plus 1. Putting these values in 1, we have y of s, which is equal to s over s square minus 1 plus e power minus 3s into minus 1 over s. So let us write this minus e power minus 3s divided by s plus, let us take 1 over 2 here, e power minus 3s divided by s minus 1 plus, taking 1 over 2 here, e power minus 3s divided by s plus 1. And now the last step is to take inverse Laplace transform of each term. So L inverse of y of s is equal to L inverse of s over s square minus 1 minus L inverse of e power minus 3s divided by s plus 1 over 2 Laplace inverse Laplace transform of e power minus 3s divided by s minus 1 plus 1 over 2 inverse Laplace transform of e power minus 3s divided by s plus 1. And now inverse Laplace transform of y of s. This is y of t. So let us write y of t is equal to. Now look at formula number 2. According to formula number 2, inverse Laplace transform of s over s square minus 1 is cos hyperbolic t minus, according to formula number 1, inverse Laplace transform of e power minus 3 s over s. This is u of t minus 3 plus 1 over 2. And now we are using formula number 4. So according to formula number 4, inverse Laplace transform of e power minus 3s over s minus 1. This is u of t minus 3 and 2. We know that 1 over s minus 1. This is inverse Laplace transform of e power t. But according to formula number 4, we will write e power t minus 3 because we have to write f of t minus a. A is 3 here. Now plus 1 over 2 u of t minus 3, and again look at here 1 over s plus 1. Inverse Laplace transform of 1 over s plus 1 is e power minus t. So we have to write e power minus of t minus 3. So that is the required solution of this problem. That's all.